So I think we can give it another minute, and then we'll get started. Okay, so good morning, everyone. My name is Eaby. I'm a PhD student at Stellenbosch University, and it's my pleasure to open this session on crystals with holes with Rob Carroll from the University of Southampton. So we have a fantastic lineup today, and I'm very pleased that all the speakers can be here in person, so thank you for that. And so in this introduction segment, we're just going to take you through some of the important principles when thinking about porosity in crystalline materials and some of the latest research in the field. So why should we be interested in crystals with holes? Porous materials are useful for a wide range of applications, such as separation, catalysis, molecular sensing, storage, amongst others. And if we think about chemical separations that are important, not only to achieve a greener future, but also to optimize the resources that we already have available, there was this very nice paper that looked at the 7 chemical separations to change the world, and all 7 of these can be done with porous materials. So it begins. Okay, so, there we go. You run through all my slides. There we go. All right, so scientists have been thinking about porosity for a very long time, and Aristotle was quoted saying that nature abhors a vacuum. Now, this postulate essentially states that there, in nature, effectively contains no vacuums, as a denser substance will inevitably fill that void space. And this principle is very nicely illustrated by an hourglass, where sand that's falling through the narrow aperture will collect and pack as efficiently as possible, only entrapping less dense air between the sand particles. And this principle has been shown to be true for particles that assemble to form a material. So it's easy to identify large pores visually if you think about something like a sponge, but there are a wide range of pore sizes, and alternative methods are inevitably necessary in order to identify their size and distribution. So we define the extent of porosity essentially as the ratio of the void volume to the entire volume of the material. And in crystalline materials, the voids adopt the symmetry of the host, or the lattice, and the distribution can be accurately determined if the crystal structure is known. So I'm not going to be going into too much detail about non-lattice voids. This topic will be covered during the session. But if we think about sort of a mechanistic approach to how a material might diffuse through, or how a particle might diffuse through a material, one might think that it's necessary for there to be these interconnected voids, and that, for example, it can pass through this region on the right, but not make it through the packed region on the left. But if you think about hydrates, for example, we know that this is not the case. So the seemingly reasonable definition needs a little bit of work. Unfortunately, Len Barber discussed this topic in detail in what is now a landmark paper on molecular crystal porosity. And from this work, there are essentially 2 criteria to just determine if a material or a crystalline material is porous. The first is that the permeability needs to be demonstrated. And as I mentioned before, permeability is synonymous with porosity. So where the guest solvent, in this case is illustrated by the red circle, can move in and out of the lattice void. And secondly, the inclusion of any guest or the removal of that included guest should not substantially disrupt the host framework. So we can also classify porous materials into 3 classes. The first one is termed conventional porosity, where you see interconnections. So this can either be 1, 2, or 3-dimensional interconnected voids. And as I mentioned before, that the guest that is included, if it is removed or included once again, it should not disrupt the host framework. The second one, which is seemingly counterintuitive, is porosity without pores. And that are these 0D or isolated pockets. And a good example of this is tertiary butyl calyxfluorine, where when sublimed, the molecule will pack such that there are these isolated voids. And if put in the presence of vinyl bromide, what will happen is that there's a significant structural change in including the vinyl bromide. And by our definition, this does not count as a porous exchange and a porous material. However, if you do the same thing with CO2, up to a certain pressure, you can include CO2 without any significant change, and that does indeed fit with our definition. And the final category, which is termed virtual porosity, is somewhat controversial because basically you take the structure and delete a molecule of your choice, and there is no set definition on which molecules you can or cannot delete. You assume that it would be the guest or solvent molecule, but in this case, if you do not prove that the crystal is permeable, then you have not proved that it is porous. So is it porous? Well, if you want to prove this, we need to keep our classification criteria in mind. And there are many techniques in order to prove that your material is porous. And the 2 basic criteria are to identify if there are voids and is it permeable. Now, I'm just going to give a representative example of these 2 questions. So to determine if there are voids, I'll use X-ray diffraction, and is it permeable, just using gas or vapor sorption. So once we have our crystal structure, we can then run a probe of a certain radius through to identify an accessible surface. And if you look at this case, we can see that we have these sort of chambers which are connected through these narrow sections here, and we would think that we have a 1D porous material. However, if we use a more appropriate definition of the probe, so the solvent accessible surface, we'll see that these chambers are in fact isolated and not interconnected. So in fact, this is a 0D porous material. So a lot of care has to be taken on how you define the porosity based off of the crystal structure. And once we've established that our system is porous, we need to determine whether it's permeable. So a very nice way to do this is just generating a sorption isotherm based off of a target molecule. So in this case, the material was exposed to a vapor pressure of a linear alkane, and you can see that there's, as with an increase in pressure, there's an increase in the uptake. And then when the pressure was released, the molecule came out without a disruption of the host, and that resulted in no hysteresis. You can see that there's no hysteresis in the profile. However, if you use a branched alkane, no uptake is seen over the same pressure range. So there are a lot of different mechanisms at play, and there's different sorption profiles that you can see here. You can gain a lot of insight from that. So this is typically how you would establish permeability. And as I mentioned, I'm not going into too much detail on this, and I'm going to hand over to Rob to discuss other aspects of porosity.
Yeah, so now that Alan's given us a bit of a grounding in the kind of fundamentals and how we define pores, I'd kind of like to go on to basically how we approach tuning porosity. And to start, I want to talk about discovery versus design. So this is a topic that's come up quite a bit when we've been talking just in general about crystals, but it's especially important when we're talking about porosity. So the first would be discovery, so a bit of more of an experimental approach. And it's the kind of thing where we'd be synthesizing libraries of molecules from some very simple starting materials. It wouldn't be an overview talk without a bit of an analogy, so I've put that almost to being exploring the old city, just wandering through the streets, not really having an idea of where you're going, but a bit of an idea that there might be something good around. And then that can be compared to design, so a bit more data-driven. We might not be synthesizing libraries of molecules, but we can then use structural databases to actually think about, are there common themes that we can then try and build on? And that's a bit more like if we saw an overview of the map from the Orid city, and we're thinking, okay, where might be good to go? One thing I do want to touch on with design is it's more computational driven, and when you think about computational things with porous materials, what we can often think about is, well, is it just stable materials that we can synthesize? But we're actually starting to move on a bit more than that, so Kim's going to come on to that. We can actually begin to talk about functionality from the beginning. So not just saying, is this material going to be stable, but what do we actually want out of it? Obviously important to note as well that we're never really going to be using discovery or design on their own. The two can drive each other, and when we're doing that, that's when we're really able to start influencing the properties we want, which would be sort of size and functionality as a general sort of rule for porosity. So the first class of materials I'd like to talk about is hybrid organic inorganic materials. That's a very fancy way of saying porous coordination polymers, of course, which MOFs are a subset. And these kind of materials are often going to be extended frameworks, so exhibiting permanent porosity. And the reason we're able to get this permanent porosity is because of the strong coordination between our metal centers and our organic ligands, and that's providing the stability we need to keep open these pores. One interesting defining feature about these kind of materials is that the synthesis and crystallization tend to be the same step. And that's obviously going to have a few consequences on then when we're actually designing materials, the kind of way we want to actually work with them. The first of which would be that our choice of building units is really going to define shape, size, and functionality of the pores we're working with. And this is kind of the idea of bottom-up design. So the smallest building units that we're using are then going to end up defining not only our pore sizes, but also our macroscopic properties. This is actually going to come up in Miguel's talk as well, of we can also just not defining shape and size, but functionality in terms of if we're putting really interesting molecules inside of as linkers, we can then end up getting some really emergent or interesting emergent macroscopic properties. I also want to touch on that influencing properties isn't just from the building units we use, but also of how they end up ordering. So in particular, talking about defects and disorder, which is Kim's going to come on to. So when we're talking about that, if we're not getting this regular array, we can actually get some really interesting properties as well. I've also included a bit of work here from Andrew Goodwin from the University of Oxford, who's also doing some really interesting work in almost disorder by design. Jason is also going to come on to reordering, so not only the materials that we start with, but if we're then inducing changes into the structure, we can get some even more interesting properties. So the next category of materials would then be porous organic molecules. These cover quite a wide range of variations, whether that's COFs or PMCs or porous cages. And because it covers such a wide range of materials, we actually get quite mixed bonding. So obviously for covalent organic frameworks, we'd have covalent bonding. But for the others, we can have a bit weaker interaction. So for example, aromatic interactions or hydrogen bonding. Just because we have these weaker interactions doesn't necessarily mean that we can't get large voids though. So Ongyun's going to show that even utilizing these intermolecular interactions, we can still get quite good stability. One thing to also touch on is that, again, variable materials have variable pores. So Alan talked a bit about describing the different types of pores, so whether these are extended frameworks or actually discrete cages that we can try and get into. But we are also able to influence that. So Len and his group showed off these materials, so we're able to firstly construct the framework and then also adapt between whether we have discrete or extended pores depending on the time of guests that we're putting in. And just to compare to the hybrid inorganic sort of systems, in these cases we can actually get a different step for synthesis and crystallization. And the first thought there might be, well, that means we can have more control over our crystallization. But an also interesting thought that comes up is, well, do we even need crystallization to have these functional porous materials? And the answer is no. And Kim's going to come on to a bit of that as well with the sort of amorphous MOFs. I do quite like the Tetris packing, which is shown here. It's some work by Andy Cooper. But we are still able, even if we don't have this long-range order, to get really functional materials. In terms of thinking about synthesis and crystallization being different steps, the one I always like to go to is cyclodextrin complexes. So being able to firstly synthesize the cyclodextrin, then grinding them or doing whatever method you'd like to include the complex, and then going on from that, you can crystallize. One feature that always was interesting to me when I was working with them was the distortion of the host and the interplay between interactions within the actual host as well as some sterics. And Concilia is going to give us a bit of an insight into that with the kind of intermolecular interactions that come up when we're dealing with larger macrocycles. So just to finish off, I want to finish on a few applications that will hopefully set up our speakers quite nicely. So the first being molecular machines. And this is obviously talking about movement within the solid state. Quite an interesting thing that we can use with porosity, and Miguel's going to come on to, is, like I've said earlier, using really functional or using movable rotors within the framework and utilizing the space that we've got rather than just trying to influence what's in the pore. We can then go on to the uptake of guests and separation. So Kim's going to tell us a bit, or give us a bit of insight from a computational perspective on separating oil fractions and why certain materials are actually better at doing that. We'll then go on to Ongyan, who's going to talk about selective uptake of gaseous mixtures, in particular some greenhouse gases, and, for example, or being able to not only absorb them, but also then selectively go through them. Concilia is then going to come on to talk about mimicking biological systems and giving some real insight at fundamental level of the intramolecular interactions which really define the systems we're working with, and hopefully then going on from that, maybe being able to improve or mimic the kind of systems that we'll see in nature. And then finally, Jason's going to come on to talk about stimuli response systems. And this is going to be structural changes with light, so getting that reordering of the structure, which can give some really interesting properties. And with that, I think it's time to introduce the first speaker. So we've got Miguel Garcia-Garibay from UCLA, who's going to be telling us about amphidynamic crystals.
Excellent. Well, let me start by thanking Alan and Rob for an excellent introduction to porous solids. I think that was really good. So thank you, guys. And of course, thanking Tomče and the organizing committee for a fantastic conference. So today is the last day, and I think we can already consider it a full success, even if today we totally blew up the section. So I'm delighted to be able to share with you, some of our thoughts on solid state solids and porous solids in particular, and how do we get there, and broadly, how do they fit in our way of thinking when we're talking about molecular machines. So the first question that I think most people would like to answer, we certainly do, is why crystals? We're talking about molecular machines, function, motion, etc. So why crystals, right? So we have a series of reasons why we think crystals are really, or could be, an ideal platform for molecular machinery. The first one shown here is that, the magic of crystallization, right? You bring a system from an incredibly large configurational entropy with many states, conformations, local configurations, solvent effects, etc., to one state where you basically reduce to a particular, typically one type of molecular structure. You have 10 to the 20 identical molecules in a precise organization in a given system. I think that's a really good starting point. Now, those crystals will be contained with the molecules that we have designed to have certain properties. So we have encoded order, but with order goes encoded dynamics, physical properties, and potentially function. And I'm showing here some of the molecules that we think of as potential candidates for molecular machinery. Now, as we all know, we've seen through this conference, the crystalline solids represent the convergence of chemistry, condensed matter physics, and material science. I'm not going to read the list of potential applications, but we all are aware that, again, the anisotropy and the order that we have in a particular solid, depending on the components, can result in a wide array of properties. And every solid, in principle, can have an application in material science. There are many opportunities to transduce energy and to store and transfer information. There are already machine-like opportunities there. And of course, the crystalline solid is the simplest system where you can see collective behavior and emergent complexity that can come through electronic or mechanical coupling. So what we see here is a diagram that shows some of the primary applications in material science, electronic, photonic, magnetic, and mechanic, that we normally think of how to manipulate within the context of electronic structure, like in ceramics, for example, or in metals. But we think that if we bring, in addition to the electronic structure, order motion, there are really interesting opportunities to bring a new paradigm into material science. And then, multi-scale order, right? What other system can you have where you can have the same level of organization over basically 10 orders of magnitude, right? What I'm showing here are some crystals basically imaged with an SEM that you can see some of those are about 50 nanometers. Maybe they can go as little as 20 nanometers. And on the large scene, you can probably recognize that there are people there, and this is in a mine in Chihuahua, Mexico, where you see selenite crystals that are as much as maybe 20 meters, right? And also, you can handle a crystal with your hand. You can orient it with respect to a polarized field. So a crystal gives you an opportunity to interface a macroscopic human operator with molecules, unlike no other system. And I think that is quite spectacular. And on this conference, we see beautiful examples of multi-scale property, right? The transduction of molecular level effects, or rather, changes at the molecular scale that are translated through thermal energy or photochemical energy into the macroscopic scale in the form of salient phenomena. So I think, the number of properties that we see are really, really amazing. So what I thought I'd do is I share with you a perspective of how can we think from a chemical perspective in terms of how can we define a machine from a perspective that could be useful to a chemist, perhaps a synthetic chemist. So I'm going to call a machine a structurally encoded order and dynamical object. And I have here a nice watch to illustrate that. So where do you start, right? You start with the structure. You need your blueprints that contain the structural information for many, many components that will become part of this particular machine. So we start with a structure that will encode some of the information that we need for the dynamics and the function. You execute the synthesis, go to the lab, make your various components. If this is going to be a complex system, there will be many components. In this particular case, it's about 200 components that you need to build a wristwatch. What you see, I'm thinking about entropy and order, right? So the simplest manifestation of entropy here is just the configurational entropy. In how many ways can you arrange 200 objects, right? So the configurational entropy here is just enormous, right? There is a reduction of entropy when you make all of these components, but when you have all of these components together, you still have a very, very high amount of configurational entropy. And at this point, if you have n components, you have 6n degrees of freedom, right? 3 rotational and 3 translational degrees of freedom for every component, and they're independent. So the magic begins when we have an informed assembly. There is something that brings all of these components together in such a way that they come to a single object, one machine that will have 6 external degrees of freedom, 3 translational and 3 rotational, and in the case of a watch, 1 degree of freedom that represents the function of this particular machine, right? So the reduction of entropy is just mind-boggling, and that wouldn't happen without a master clockmaker taking care of that particular event. So what happens then is that we can visualize this, that we have encoded time information for, let's say, 1 day, that you could look at it. We need 43,200 stereoisomers to encode that information. right? And just to make the chemical analogy, we can put it like that. So the energy gradient here is, of course, given by a wound spring that has, an energy, potential energy that is released slowly, and it takes us to this particular potential. And our machine will go through these many different stereoisomers, and we can decode the information of those stereoisomers. Right? So we know how to read that information. The information content is precise, and we are basically the objects of that. Okay, so what about at the biological level? Well, it is very much the same thing, right? So I have here a simple example, well, not a simple example, a very complex example from biology, ATP synthase. But we tend to forget, for instance, that, I'm showing on the top right all the different steps of ATP hydrolysis, ATP on the left, ADP on the right, so there is a hydrolysis effect there. Now, what we fail to remember often is that if the chemical potential of ATP is identical to the chemical potential of ADP plus inorganic phosphate, ATP synthase would be a completely random machine. It would be just back and forth. It would be doing a Brownian kind of jumping process. So what nature does, it provides a chemical potential, right? So we have a chemical potential in terms of a differential gradient of ATP and ADP, and then it goes through many cycles that go like that, right? So clearly, this would be, we go from ATP to ADP, so this is, this is a hydrolase reaction, but you can also have a synthase, and you just need to change the potential, the chemical potential, and then the function changes. And cells will use this depending on how they need it. And I'm sorry, I just didn't make a new image for this. I'll just use the mirror image. Anyway, so basically what I'm saying is that we can reduce or try to think of a machine as the combination of encoded structure and motion. So the structure will encode the motion. And admittedly, biomolecular machines are incredibly complex, so we want to reduce this further into something that is very simple and tractable. And we think, well, what can we have that is the highest amount of order that you can have? Well, it's, of course, arbitrary molecular crystals or arbitrary crystals. So at our first approximations, most crystals will have the least amount of molecular motion, right? We will not have translational degrees of freedom. We will rarely have rotational degrees of freedom. We will have a few, perhaps, conformational degrees of freedom. We will have most of the kinetic energy will be in the form of phonons or lattice vibrations. But we don't have a lot of large amplitude motion. What nature tells us in terms of what happens when we include motion into a condensed matter system, we have to use a structure. So plastic crystals typically are molecules that have a high symmetry. They have very high axial symmetry, and they typically display rotational motion about those axes. We know about liquid crystals, rigid cores, and floppy chains, and how they tend to organize in a way that you still have, you retain translational and rotational motion, but you just have average order. And then we have liquids where we don't have any order, and we have the fastest motion that you can have. And then we can have glasses where you have neither order nor motion. And then when we look at one-component systems, this is what we looked at when we started these projects about, maybe almost 20 years ago already. It's like, wait a minute, there's something missing on the top right. And that's what we define as an amphidynamic crystal, right? So it's a particular system where the molecular structure has been designed such that we will have certain degrees of freedom, even in the crystalline state, so that we will have a structurally encoded motion and in an order array, in an order system. So how do we do that? So we find that there are potentially 3 solutions to accomplish that, to prepare amphidynamic crystals. The first one is the most relevant to this particular session. When we have motion, because we have free volume, so we have what we call free volume motion that can happen in a porous solid, and in this particular case, we could have, for instance, a metal organic framework. Another potential solution is what we call volume-conserving motions. That is when, and we're looking at rotations. I failed to say that we're going to concentrate on rotational motion just to start with something that is more accessible and relatively simple. So if we're going to have a volume-conserving rotation, what that means is that as your rotor moves, there are no major changes in the shape that require a accommodation of the local volume in the structure. What it does here, however, is that the rotational motion of adjacent, say, rotors will be completely independent. And most of the times, unless you do something special, this will be Brownian rotors, unlike the ones I'm showing there, which appear to be inertial. The third solution, which is one of the most complex ones, is correlated motion, right? So where the motion of one object affects the motion of another object. And that's what we would call gearing. And this is something that we and others have found molecular gearing in the solid state accidentally, but I don't think there is, to this day, an engineered or designed molecular gear, and that's something that we're trying to pursue in my group. So these are sort of the three primary solutions. So free volume, volume-conserving motion, and correlated motions or gearing. Now, I'm going to talk to you about emergent properties and what we think is probably the simplest entry to what could be machine-like function. We feel that a compelling starting point is what we call dipolar arrays or molecular compasses. And as I show in this image, by simulated on the left different arrays of compasses, which are, of course, contain a magnetic dipole that can reorient in the direction of the strongest magnetic field, is that ordered arrays of dipoles will have a preferred macroscopic arrangement or collective arrangement. So a 1D chain will be spontaneously ferroelectric, but a 1D stack will be spontaneously antiferroelectric. And there are solutions in 2 dimensions and in 3 dimensions that where the ground state will be either ferroelectric or antiferroelectric. Now, in the image on the center, you see a photograph where we have a bunch of compasses. Well, you see that there is one on the left that is isolated. That compass is pointing to the magnetic north. So that's representing the behavior of the isolated object based on its own particular properties and the information around it, which is the S magnetic field. Now, if you look to the right, you see that a 1D array of compasses has an internal collective polarization that is stronger than that of the external field of Earth. So instead of being oriented to the magnetic north, to the Earth's magnetic north, it takes its own polarization. And I'm showing here with a small hexagonal or trigonal array that will be spontaneously ferroelectric also, and will have its own polarization independent, in this case, of the one that we would have. So this is what we mean emergent behavior, right? Something that is a property of the collective elements, and you would not see in the isolated elements. Now, here is an interesting example, right? So if you look at the arrow, I have a magnet that is close to that arrow, and I'm basically doing a little perturbation there. So what you will notice is that my little perturbation on one corner can be extended, in this case somewhat randomly, all the way to the top, right? So what that tells us that there are ways, there are opportunity to transfer energy and communication or communicate different parts of a particular crystals if we manage to introduce dipoles that are able to reorient in response to the external stimuli. This can be very nicely illustrated by this animation. It's work from Joseph Mikkel and Mark Radner, published already back in 2006, where you see one of many dipolar arrays that they looked at theoretically. And of course, what you see here is that a stimulus on one end of the dipolar chain will be extended and transported along the chain. So if you think about it, this is a collective motion that is transported to the array. So it would qualify as potentially as a phonon, but it would be an acoustic phonon with a speed that actually depends on the rotational motion or the rotational velocity of this. And to this day, there really are not many ways to control the velocity of phonons, which is just a kind of an interesting observation. Now, one important thing to consider in order to have the behavior we see on top is that the conditions that we need are the ones I'm showing in this diagram. We need that the energy of the dipole-dipole interactions with respect to the relative orientation of the two dipoles needs to be greater than thermal energy which needs to be greater than the activation energy for motion for that particular dipole. So that the conditions shown in the image are required. So the dark solid line will represent the dipole-dipole energy, which varies very largely as a function of dipole orientation. Thermal energy, of course, that will not change unless you change the temperature. And at 300 K, that will be on the order of about 0.6 kcals per mole. And then we need the activation energy, the potential, the intrinsic potential of your rotor to be below thermal energy in order for dipole-dipole interactions to be dominant. So that requires us to design systems where you have molecular rotors in the solid state with barriers that are less than thermal energy. If we accomplish that, then we will have a behavior where the rotation of one of those dipoles will be correlated with the rotation of another dipole, so that we can have the collective behavior that we're looking for. Okay. There it is. So if we want the dipole-dipole energy to interact, if we just take here, for instance, a point dipole approximation, we see that what we're going to need to maximize the magnitude of the dipole moment, the MI, and we're going to need to reduce the distance between the two dipoles in order to have the dipole-dipole interactions to be as large as possible, right? So large dipole-dipole interactions, short distances. But the distance cannot be too short, right? Because if the distance is too short, those dipoles will actually interfere with each other. So what we need to do is basically emulate the structure of a compass. What that means is that the dipole in that particular cavity must be, or that particular structure must be such that the dipole, the cavity where the dipole is at least the size of the volume of revolution of that particular object, as shown there. So that's the need for creating crystals with holes. Now, in the process of creating crystals with holes, it was an interesting process for us, to be honest, because we started to think about molecular crystals. So how do we approach this with a molecular crystal, right? So let's start with something simple. Let's think about two benzene rotors, and we think about the potential energy of having two benzene at a certain distance. And we see that there will be a tendency to have, let's say, have a parallel displaced dimer, as I'm showing here. So that's a sandwich dimer. And as you can see here, under those conditions, we obviously will not have the volume of revolution needed for either of them to move, at least not independently. You can have a crystal where you can have a T-shaped dimer, and now we have a condition where we could potentially have the rotation of one and then the other, have essentially a correlated or gearing rotation, but we cannot have independent rotation. So if we can find ways where you can have, let's say, pairs of benzenes that have this particular configuration, you could potentially think of having a sort of a primitive molecular gear. But the potential looks like that, right? So we have basically that at some distance, these two benzene begin to attract to each other. And of course, this potential is what makes it very difficult to make anything that is porous. As we heard earlier today, nature abhors vacuum because there is a potential, the van der Waals potential, the dispersion forces that will bring two things together, right? Even if you put out something at the volume of revolution of two benzene molecules, you're still very close to the part of the potential where it begins to get to go downhill. So that will be impossible to assemble unless you get some help, right? So now you can think about a scaffold that can help you put those two benzenes at a distance where they can rotate independently. But what if you wanted to have, and you can have solutions in terms of molecular crystals where that can be more or less accomplished. Now, what if you want two benzenes at a distance that is well beyond that of, where the two begin to attract to each other? That actually sounds like a pretty good idea, right? So now if you can keep them there will not be any attractive forces that will bring them together. And that's what porous solids do for us, right? That's why porous solids can actually exist, because the distance between the objects are beyond the attractive potential of those van der Waals forces. And that's how Now, the potential that we're using to keeping them is not the potential of the two benzenes interacting with each other, but it's a potential provided by, in this case, a particular framework, which happens to be a metal organic framework. And those are the various steps that we have taken. One interesting thing here, of course, is that as we go from right to left, we have an increase in the packing coefficient, right? So on the right, we have the lowest density, the largest porosity, and on the right, we have the least density and highest, the least porosity and highest density. Naively, we thought that, well, that should correlate with rotational motion, right? So there should be an inverse characteristic. And I think that that's reasonable to see. After a few years, we had enough examples of molecular crystals with different symmetries, different structures, as well as some porous solids, like some MOFs, and we could actually do an analysis of what is going on there. What we discovered was kind of interesting. I'd like to share it with you. Before I do that, let me spend just a few seconds telling you how do we measure rotational motion in crystalline solids. The simplest way to do this, as illustrated in this slide, is by using deuterium NMR. So if you look at these molecules, the rotator in the center is a benzene ring or a phenylene, and the 4 hydrogens have been exchanged for deuteria. So those 4 positions are isotopically labeled, right? What you see on the top is that if the rotational potential is such that there is no opportunity to rotate, all you have is a local libration, right? And a local libration is not detected by the deuterium NMR spectrum, which is a quadrupolar coupling pattern, or a PEG pattern. And the spectrum is very broad, and that tells us that there is really no motion, or that the motion is slower than about 1 kilohertz. In the middle, you see a case where the barrier for rotation is a little lower, is accessible thermally, and you can jump from one side of the benzene to the other, so you have a jumping or side exchange process. That means that the activation energy is still much more than thermal energy, but you have then that the spectrum, the deuterium spectrum, has changed in a way that can be predicted based on the trajectory of motion and the frequency of motion. So it's incredibly simple and incredibly useful. At the bottom, you have an example where you have inertial or rotational or continuous motion. And it may or may not be like that, so that looks inertial. And it's very hard to have inertial motion in the solid state, so more likely to be Brownian, right? It's going to take a few steps to the right, a few steps to the left. It's going to get confused and go at it again, and so on. But when you have a situation like that, you have a rotational frequency that reaches the moment of inertia. And what you see is that the spectrum becomes very sharp, very narrow, and with 2 sharp peaks. So this is a nice way to measure rotational motion. The other one, and I'm showing here some data that actually Luca Catalano obtained in my room when he visited. You can use spin lattice relaxation. It's a really simple and friendly method. You take your solid. In this case, you don't have to deuterate. All you need is that there is an element in the solid that has a significant dynamics, much different than the rest of the solid. So in this case, a bicyclo adapco in the center rotates very rapidly and is responsible for the relaxation of the entire crystal because the modulation of the magnetic field as it rotates, when it matches the Larmor frequency of the external field, causes relaxation. So what we see here is that in this plot we have the T1 relaxation as a function of temperature, and you see that there is an optimum, and the optimum occurs when the rotational frequency of the DAPCO matches the Larmor frequency of the magnet that you're using. So we can use temperature, and you can use different magnetic fields and probe the dynamics in a really nice way. Of course, you can also use X-ray diffraction and get an idea of, in this particular case, there is a phase transition. You can look at order, disorder. You can even use the thermal ellipsoids, right? And use the Donitz and Trublot method to use the ellipsoids to learn something about the rotational potential. Very good. So we came to this idea, right? So the prediction would be, okay, we can have rotational motion in the solid state from static, the rotational frequency would be 0, to the limit of inertia, which is about 10 to the 12. And then we say, well, we can have molecular crystals with packing density somewhere between 0.62 and 0.78, let's say. And then you can have porous solids let's say all the way down to about 20%, and the prediction would be that maybe it would look like that. Well, it turns out that it doesn't. It looks more like this. It's definitely biphasic. There's two areas. So, two questions. Why is it that we have some porous solids where the rotational motion is in the milliseconds, relatively slow? And why do we have some molecular solids where the rotational motion approaches, 10 to the 12? So, interesting effects. So let us take a look at the MOF really quickly. This is MOF 5, right? It's the most iconic of all MOF, which is benzene dicarboxylic acid. So we look at that. So we, in fact, collaborated with Omar Yagi when he was at UCLA. My students discovered that any method that we used, the rotational frequencies they was not moving because we were looking at the wrong place. Eventually, we discovered that, of course, this is a dicarboxylic acid, and there is conjugation between the central phenyl ring and the two carboxylates. So, in fact, the transition state is a second-order saddle point. You're paying a penalty for breaking conjugation not at one but at two sites at the same time. So the calculated activation energies are on the order of 15 kcals per mole over a wide level of theories. What we discovered experimentally is that it's about 11.3 kcals per mole. Right? With an pre-exponential factor of 10 to the 12. And this is important because the pre-exponential factor should match the moment of inertia, the one you can calculate from the moment of inertia, or the one that you can calculate for the torsional motion at the bottom of the well, that once activated becomes a rotation. So we learned, therefore, that there is something intrinsic in the structure, that the electronics of the rotor are going to be important. So we have two additional structures of MOFs, again, benzene dicarboxylates. In this case, we have one with bromine. The activation energy is a little lower, 7.3 kcals per mole. Then we have one with a 2-amino group. The activation energy is a little bit lower, 5 kcals per mole. And what's going on here is basically that when we have a phenyl ring, you can have a perfect planarity between the carboxylate groups and the phenyl ring in the center. But when you put orthosubstituents, you destabilize the ground state. And ground state destabilization brings you closer to the transition state, right? And the closer to the transition state you get, the lower the activation energy. So that was an interesting learning, moment for us. So what did we have to do to get to that point, to bottom off? Well, we had to remove conjugation, right? We knew that conjugation was going to be costly energetically. Remove conjugation, come to something aliphatic, and now you can have an opportunity. As you can see here, the structure of the bicyclooctane dicarboxylic acid is basically, by all means, is isostructural to that of MOF5. So what we learn here again is, that, and the other thing that we have, of course, is that we increase the symmetry, and the potential now has more minima and more maxima, and the displacement between minima gets smaller than in the other case. Here is some experimental data. So the synthesis is straightforward. That's the structure solution, which is, of course, beautiful, but I don't know if one can trust it 100%. But as you can see from the X-ray power diffraction, there is the power diffraction of what we call bottom off is identical basically to that of MOF5, meaning that they're completely isostructural. And when we go and do, let's say in this case, we've done spin lattice relaxation measurements using deuterium in the bottom off, when we find something spectacular, right? This is a crystalline solid where the activation energy for rotation in the center is only 120 small calories, which is really, at that time it was the lowest ever found. So we can model that and get a very precise information. We also obtain information with proton NMR, and this is really incontrovertible, really nice. So now we know what's happening there, right? We know that we need to be mindful of what's going on in the potential energy. Now, very recently, actually a couple of years ago, there was another paper by the groups of Angelina Comotti and Piero Sossani, who used the same principles to use a little smaller rotator, the same sort of framework, and they were able to show a slightly higher energy, and under some conditions, their calculations indicate that there could be, in fact, continuous motion. So there is really, beginning to be progress in this area. Now, when you have a molecular crystal, in this case, if you look at the structure on the left, the phenyl ring is linked by 2 acetylenes. So the rotation about the acetylene bond basically is non-existent, it's virtually zero. That means that the gas phase barrier is nothing. And the potential for rotation is going to be the packing energy of the crystal, right, as you can see on the right. So what happens here is there is a couple of things to happen. So this is an interesting example. These are 2 isostructural rotors with trial status. One has a phenylene, the other one has a bicyclo 222-octane. One is very slow, 800 rotations per second. The other is ultra fast, is 110 million rotations per second. So what's going on here is, of course, that in the case of the bicyclo 222-octane, we have a volume conserving motion, right? The potential has multiple energy minima, and the displacement is relatively small between those minima, and there is no change in the local volume as the rotator moves. So this can be appreciated also here when you expand, let's say, if you have a phenylene, which is a 2-fold rotator, the 2-fold rotator cannot be fit well into the cavity that you have in the crystal, so you need to have a distortion. The 3-fold rotator, the bicyclo 222-octane, can be circumscribed a little bit better, and a paracarborane with a 5-fold symmetry does it even much better. And you can see the progression of the barriers for large, 8 kcal per mole, 3.57 to 2.92. So we know that all of that group that you see here, that those are high symmetry molecular rotors. So these are the ones that are volume conserving motion. So what's going on with the rest, right? So that's the last thing we need to explain. What was going on here is now what I put here, what happens in the slow rotor, and you can do that through calculations, is that rotation relies on the coordinated, correlated motions of the neighbors, something that we call crystal fluidity. That means that the local oscillations of the lattice create transient cavities where rotation can take place. And we think that is a really good understanding of that. So, if you have high porosity, you definitely want to look for a low intrinsic barrier. But if you want high correlation, strong interactions, you want high symmetry and built-in crystal fluidity. Now, these principles have been used by others when thinking about molecular machines. There is a nice review from the Love group at Windsor, and you see here a couple of examples of rotaxane shuttles, and in the middle, an example from the group of Feringa, where their molecular motor has been built in a porous crystal. Let us get back to the title of my talk, right? So we're talking about actually now introducing a dipole, and the way we're going to do it is we're going to use a metal organic framework with a fluorophenylene as a dipole. We know that this is going to be a high barrier, so we don't expect spontaneous polarization or emergent phenomena, but we expect that we might see basically a paraelectric system. And one way to characterize it and to make sure that you can interface it with an external electric field is by putting your crystals between 2 capacitor plates. You connect the 2 plates to an AC field generator, and then you change the frequency of the field at a given temperature and scan it. What you see here, there is a family of curves at different temperatures, and what's going on here is that the maximum of that curve basically indicates the frequency of rotation at that temperature. This is otherwise known as frequency-dependent dielectric spectroscopy or broadband dielectric spectroscopy, and it's just a nice way to directly probe the dynamics of your system. We have frequency and temperature data, so with that, we can build an activation energy. In this particular case, we can also use deuterium NMR, and we can confirm that we are probing the same motion by the 2 methods. So this is a nice way to do it. But again, this is a paraelectric system, right? So in this case, all the dipoles are basically not minding each other because thermal energies are, because the barrier is too high with respect to thermal energy. So it becomes a Brownian rotor. Now, what we know that what we need to do is to remove that conjugation. We can do that by building a MOF with difluoro, in this case, bicyclo 222-octane. We meet the conditions that we need. The first that you think that you know, we have actually single crystals, which is an added bonus, so we can get a single crystal X-ray structure. The first thing that you notice is that the electron density of the fluorine is radially distributed along the rotational trajectory of this rotor. And it's also disordered on the two sides. Even though it's a difluoro, the fluorine can be obtained on both sides of the crystal structure. You see that the ground state dipole orientation is shown on the left. On the Eaby plane, we have what is known as an icing symmetry. And in the AC plane, we have a regular antiferroelectric symmetry. The icing symmetry, of course, is also antiferroelectric. It has no macroscopic polarization. And this is the data. This is really the key data. I'm going to describe the frame on the top left. So what we're doing there, we're measuring the capacitance on the system, right? So the ability of those crystals to store energy by aligning their dipoles with respect to an AC field. What you see is we start at about 275 Kelvin. We have a certain value. We're using 3 different frequencies. And then at that point, the dipoles are completely disordered. The system is paraelectric. And we begin to reduce the temperature, and then by virtue of a Boltzmann population, so as you lower the temperature, more of the dipoles will align with the field than against the field. You see an increase in the capacitance. And then something interesting happens at about 100 Kelvin. So what we have here is shown in this animation. We start paraelectric, lower the temperature, and then we have basically a disorder to order phase transition. Spontaneous alignment of the dipoles, which is exactly what we're looking for, which is really interesting. And it adopts an icing symmetry. The one thing that you might wonder here is, well, if it adopts an icing symmetry, that's antiferroelectric, has no polarization, the capacitance should go down to 0, and it doesn't. It takes you see, it's reduced, but it's a smooth slope. So to know what was going there, we had to look at calculations. And what we discovered is that in addition to the rotational motion, which is from, it's about 2 kCals per mole shown on the left, there is a distortion, a twisting of the bicyclooctane that provides another process to modulate a dipole moment. So it is that process, basically, that, as you see here, the difluoro group can go from the plus C to the minus C direction, and that provides a mechanism for the response that you see there, until we get to about 50 Kelvin, and then we finally freeze that motion, and then now precipitously the polarization or the capacitance goes down. So this is the very first example of a case where you actually do have an emergent process by virtue of dipole-dipole interactions. Very quickly, I can show you that work now in progress includes electric plus magnetic dipoles. And I wanted to share this because it's kind of interesting, right? We built this MOF with a tryptophan dicarboxylate layer, which is very dense, and that allows us to make really big cavities, as you can see here. We have a rotor, which is a nitroxyl radical, but when you look at the crystal structure, it's missing. There's nothing there, right? We call it the nitroxyl radical ghost. And this is one of several examples where the electron density is completely distributed over the radial trajectory, meaning that the motion is essentially, that there is no minima or maxima in the potential that is in any position possible. The beautiful thing here is that we can also dilute the radical with some diamagnetic pillar. In this case, we use a phenyl group as a diluent. And I will not have time to elaborate on this, but what you can appreciate here is that we can change the concentration of the nitroxyl, and by that, looking at spin-spin interactions. So at high concentration, nitroxyl concentration, we have a significant amount of spin exchange. We can reduce that by diluting the nitroxyl. What we can also do is we can vary the temperature. By doing that, we change the rotational motion of the nitroxyl. So again, we're beginning to have an opportunity to bring an electric field, a magnetic field, temperature, and be able to manipulate this in some interesting way. The other thing that is kind of beautiful thing to remember again is that a single crystal gives you an opportunity to take advantage of the anisotropy, right? That the orientation of that nitroxyl I can control in a macroscopic object with my hands by just changing the orientation. And in doing so, I can have that interface with another anisotropic effect, which could be, microwaves and a magnetic field and electric field. We think that there are potential opportunities for quantum sensing and quantum computing. Finally, so when you look at the bulk magnetization, we begin to see the emergence of something interesting, right? On the left, we see the simple, magnetism as a function of temperature, and it looks paramagnetic normal. That's at zero field. When you use a magnetic field, you change the magnetic field at 5 Kelvin, you see that there is no hysteresis, so there's no collective behavior that is measurable that way. But when you measure the magnetic moment, what you see is that, yes, there is an interaction. There is a weak magnetic interaction where the rotating magnetic dipoles begin to orient in a way that the magnetic moments cancel. So we think that this is all interesting. So we think that this fits very nicely in this particular image when the control and manipulation of the rotational motion and other potential trajectories in the solid state will give us an additional variable to manipulate material science properties. So, and then, the next thing, of course, is to interface mechanical motion with catalysis, for example, with chemical reactivity, and the potential is really amazing. I hope I convinced you today that there's the porosity of solids can be advantageous when you want to think about function. And I want to finish just by acknowledging the many people that have been involved in this research over the years. And I want to thank the funding agencies who should be represented here, particularly the National Science Foundation. As just yesterday, I got notice that my grant's going to be renewed. So that was good. So thank you very much. I'll be happy to answer any questions.
Yeah, we have a question over there.
Thank you, Miguel. I feel so empowered after your lecture. I think I want to change my research field each time you give a talk. The point you mentioned about quantum sensing and quantum computing, and it's perfectly fine if you don't want to disclose anything about that, but that nitroxyl is really, really disorder. Is there, what would be your approach or strategy to store information in such system?
Well, that is the big question, right? So I think there is really no clear solutions, So I think at this point, what most of the community are looking for is to tractable qubits, right? So something that you can have different quantum states that you can generate, you can read, hopefully use for some logical operation, and then regenerate again. And you need the coherence time of any magnetic interaction to be on the order of several milliseconds to have an opportunity to do these manipulations. So in the case of MOVs, we are a long way to even begin to get to that point. But on other areas, when we've been able to make radical Pershing crystals where we can have coherence times of up to milliseconds, and in those cases, I think there is potential for solid-state organic chemistry to provide a new platform for quantum computing that you don't have to be, at 10 millikelvin, that you can be at much higher temperatures because the magnetic interactions are stronger, the correlation times can be stronger. Instead of looking at nuclear hyperfine interactions, you can have a strong electron-electron interactions, for example. But we are very, very far in the case of MOVs. It's the first step of a concept that we really need to explore. Thank you. Yes.
Miguel, thank you as usual for a fantastic talk. I have two questions. So one is in the field, especially if you think about porous crystals as adsorbents, right? So then the role also of a guest there.
Yeah.
It's not really considered in the literature the role of the frequency in uptaking a guest, and if you can optimize it by kind of correlating the frequency and motion of host and guest. So I'd like to know your opinion about it. And the second is, it has been shown that some systems are high entropy systems, for example, like high entropy alloys, they can create basically or can show new properties. And I was wondering if we have a mixed ligand system, what would you expect could be also the effect if there is any possibility of engineering new systems?
Right. Thank you for the question, Luca. So the first question, I agree. Passive diffusion is extremely slow. Passive diffusion through small cavities is a very slow process, right? So what motion can do, if it happens to be to correlate with the translational motion, I think can indeed accelerate the uptake and the release. And I think in some ways this has been shown for different systems. The one that comes to my mind is one of my colleagues, Jeff Singh, developed a porous silicate with azobenzene, and he showed that transport, when azobenzene is cis-trans isomerized at a high frequency, it occurs faster than when you just let it be spontaneous. So I think there are opportunities to think about that. In terms of, I think mixed crystals are extremely underused, and I think there's so many opportunities to take advantage of that, right? So in a mixed crystal, you can have, a molecule that can, say, act as an antenna, and another can act as a relay, another that can act as the part of the function, and they all can coexist in the same lattice, in the same crystal. So I agree with you. I think that mixed crystals, whether random solid solutions or Koch crystals with the perfect, stoichiometry, I think there is a lot of opportunities to use that information for a number of applications.
Yeah, we have time for one more question.
Yes.
These systems should show some interesting thermal properties. Have you measured heat capacities and thermal conductivities?
We haven't done those measurements yet, Craig. So what I show you is basically all that we've done at this point. So we measured capacitance, and we've measured broadband dielectric spectroscopy, but we still have a lot to do. Thank you for the suggestion, though.
All right, great, thanks. If you have any more questions, you can ask in the coffee break.
Thank you.
So our next speaker is Kim Jelfs from Imperial College London, and she'll be discussing unraveling the effects of defects and disorder in porous materials through computation.
Thank you. Thank you very much for the introduction, and also, of course, for the invitation. So I'm actually not going to specifically talk about this. I've been guided by Pancha, who saw me speak at the GLC a couple of weeks ago and said he enjoyed the organic parts most. So I've taken out any discussion of inorganic and talking more about organic things. So instead, we're talking about exploring packing prediction. Some in porous, so I'll be sticking with porous theme, but also for some other materials as well that aren't technically porous. So in general, what we do in my group is computational chemistry and trying to assist using computation with the discovery of new materials. And in general, supramolecular materials that are built from organic building blocks. So these are sort of the main materials that we look at: porous molecular materials, porous polymers, in particular sort of doing the structure prediction of amorphous porous polymers for molecular separations, including in things like batteries. MOFs, where we focus again on the structure prediction. So actually we look at amorphous disordered MOFs, but I won't be talking about that today. And then also looking at organic electronics, and in particular we're interested in the interplay between structure and packing and function. So I will be talking a bit about that today. I wanted to just briefly mention that a lot of what we do actually is trying to avoid having to fully include consideration of solid-state packing, because it's really difficult if we're trying to look at doing screening of thousands of different materials. And so a key bit of software we have really focuses on the molecular structures. So our software is called SDK, or the Supramolecular Toolkit, and it's written in Python. And it makes use of RDKit, which is a sort of a set of Python libraries for chemistry. And they also allow you to do machine learning, which we do in some other areas as well. But so basically STK can take molecular precursors and then can arrange them into the structures of lots of different supramolecular systems or organic molecular systems. So we look at organic cages, linear polymers, and other organic systems, including COFs. And then that allows you to connect up with other codes that characterize their properties. So you could do screening. And it also has an evolutionary algorithm as an efficient way to explore a search space, sort of mimicking survival of the fittest in nature. And so that software is open source, and on GitHub we have YouTube tutorials to help people get started on it. And there's a Discord channel that you can join if you want some of my group members to help people get started. And so this is an example of the types of structures that STK can build for you. So it can build organic, porous organic cages. We've recently added metal organic cages, coordination cages, so we've been doing quite a bit for that. But it could obviously also therefore do sort of metal organic complexes like transition metal complexes. And it can build covalent organic frameworks. It could build MOFs, or I would say there's lots of other good codes out there for doing that. It can build retaxane structures, and it can include the chirality of those as well. And it can build linear polymers with a range of different sort of ordering within it. So I'll move on to looking at the solid state. So one of the systems that we look at quite a lot are porous organic cages. My interest in these originated when I was a postdoc with Andy Cooper's group in Liverpool about 10 years ago. So this is the sort of classic first set of cages that came from his group, cages 1, 2, and 3. Shown in a schematic here, these are made by an imine condensation reaction, reacting a trialdehyde with a diamine in each case. And they all have the same triamine, but have, trialdehyde, but have different diamines that creates a different functionalization on their vertex. So you sort of think of the cage 1 as not having any functionalization. Cage 2 is having methyls, a single methyl disordered on the position of the vertex, and then the cage 3 at the bottom having cyclohexane on the vertices. And on the right-hand side, you have a schematic image of the packing that you get with each of those cages. So we can see that the packing gets changed quite a lot by changing those vertices. So at the top, you actually have a non-porous solid-state structure with those orange voids representing those isolated pores. Although if you introduce a different solvent, you can do a solid-state switch to a different polymorph that does have porosity. But then the cage 2 in the middle has isolated voids again within the cages, but has an extrinsic channel, a one-dimensional channel going from top to bottom. And then the cage 3 has a diamondoid packing network. So each of the cages is tetrahedral with 4 windows, and in that case, each of those windows aligns directly with another window, and that's what creates that diamondoid pore network. So previously we've worked with Graham Day on doing crystal structure prediction of these systems, but what we have been doing in my group, and specifically this is done by the postdoc in the group, Emma Wolpert. So she has been looking at whether she can do coarse graining of the packing of these systems, so to sort of make this simpler so that you could potentially do it more quickly, but also look at what are the key interactions that drive the formation of different types of packing. So in this coarse graining process, you would imagine a cage shown on the left-hand side, but now represented as a hard particle, and in this case as an octahedron, which has 2 different faces that represent, so the blue and the orange there, and they represent the arene face and then the open window of the molecule. And so the way these simulations are then set up is that we first of all would have a Leonard-Jones potential that just represents the intermolecular interactions between the 2 particles. And then she has what's called these sticky patches that can be put on the different faces of the polyhedra. And she can tune the strength of those interactions. And the other thing she can tune is how large those patches are. So that's tuned by this variable sigma ang, which is just the size of the particle. So at the top you can the size of the sticky patch. So at the top, it's small, and at the bottom, it's larger. And that, therefore, means how neatly aligned the two particles need to be for that sticky interaction to be felt between them. So at the bottom, the particles could be quite far from each other, but still feel that interaction, or be less well aligned and still feel the interaction. And then finally, you have a torsional component that reflects the fact that as you would rotate the cages round, they would feel different interactions. So then she would set this up that she would have a large supercell. We're using the HUMD software that was developed by Sharon Glotz's group in the US. So she would load lots of particles in and start at a raised temperature and then gradually cool the temperature. So what we're seeing here is actually all the particles moving around, but they gradually tend to, if you want to call that nucleate, but to form these different clusters that have ordered packing. And so then she would examine these different clusters and identify the type of packing that you've got there and try to relate that to observed packings. And I should say all of this is currently unpublished. Emma's just been working on it this year. So what we were trying to look at is, okay, this is a really simplified model of the interactions, but can we see if we can observe again the previously experimentally observed phases of these cages? So here we've got, the CCDC codes for various different cages. So they're all cages that have this underlying tetrahedral structure, but have different functionalization of the vertices, so that they end up having different numbers depending on that functionalization. So on the right-hand side, we've got examples of the different packing. So you can see that actually there are actually quite a lot of different packing modes that are observed for these systems. You have different space groups, and you have different dominant packing modes. So whether you get a window-to-window packing being dominant, or window-to-arene, or a mixture of the two. So the first thing she did was to run the simulation with having the sticky patches so that you had the window-to-window modes being your dominant interaction. And the top in the sort of red, you see examples of these clusters that then had the packing that matches up with that cage 3 diamondoid pore network packing interaction. And all I want you to take from that plot that's on the left-hand side is that sort of there's a very broad set of different variables that you could have, and you still find that packing being observed. So it didn't really matter sort of what size, how large the sticky patches were, or what temperature you ran the simulation. That was clearly a very dominant packing, and that's also something that's sort of seen experimentally for that particular system. There's a large energetic gap to any other polymorphs we know from CSP calculations. So if we go back to this set of experimentally observed structures, so we've now observed those two key types of packing. And so next she would run the simulations where now she has sticky patches that mean that the window are attracted to the arene faces of the particles. And now we see a sort of range of slightly different phases. These are shown on the right-hand side, and you get the slightly different arrangements depending on exactly the size of the sticky particles. And so you get the window to arene, so that means the cages have a sort of translational symmetry if we were to go into the screen there. But what's happening as you change the size of the sticky particles is you're getting a slight rotation of them relative to each other. So that's a little bit easier to see if we overlay those hexagons that show that. And so on that plot, we've got the different colours where to tie up to those slightly different rotations. And again, a couple of these would match up to the experimentally observed phases. Now, there's one phase that we weren't able to observe. This is one seen for cage 3 beta or cage 4 alpha. And we do observe the solvated form of this structure on the left-hand side. So at the top is what we saw from Emma's simulations, and at the bottom is a representation of that packing in the solvate structure. And there is a red tetrahedron that represents the orientation of the cage there. So as I say, that left-hand one is the solvate structure. But when you desolvate that system, you get slight rotations of the cages. So that's seen with the different colours of the cages on the right-hand side. So we don't directly observe that right-hand structure, but equally that's one that's not directly observed with the full CSP calculations. So we believe that there's a sort of solvent templating effect that is leading to the observation of that phase, and that's why we don't see it. And then finally, if we include both arene and window-to-window sticky interactions, then we do, again, see this final crystal structure shown on the left and the right-hand side, our simulation of that packing. So if we go back, really, we're able to observe all the phases apart from that solvent templated one, and this is with a very simplified set of interactions. So as I say, this is sort of fairly new work, and we're still looking at it, and we've got lots of places we want to go with this, but it's reassuring that we can reproduce the sort of, or almost all, the ordered solvent-free phases. So we could potentially be using this to predict new phases of the material and looking at how to include solvent to template those. And we can also learn sort of key things about the interactions that are needed in order to get specific phases, what interactions you need between the two molecules. So now I'll sort of move beyond porous materials to some other work we've done where we do consider solid-state packing, or we do try to find ways to not consider it, to be more truthful. So I have a colleague, Matt Fugter, at the Department of Chemistry at Imperial, who for a long time has been looking at these helicene molecules, and in particular looking at them as in chiral organic semiconductors. So here we have an example of a helicene. So it's got axial chirality. So you've got the two opposite enantiomers. This is a 6 helicene with the fused aromatics. You've got both of the left and right-handed version. And so they'd been exploring these systems for a while and looking at the charge mobility in the solid state and in thin films. They would get completely different behaviour depending on whether you had an enantiomer or a racemic mixture that you were measuring. And they put this down to, well, this is the effect of the chirality. But what we were trying to help with by using simulation is to tease out the differences in the effect from chirality, the effect from changing the molecule, and the effect from the crystal packing, which obviously are difficult to tease out experimentally because every time you change one of them, you're changing all of them. So the first thing we did was to look at one of these systems. So in fact, it's not quite a carbohelicene as seen here. It has a single nitrogen atom. But this was a system where they'd seen that the racemic structure had 100 times higher hole mobility than the enantiomer structure. So, but they didn't know what the structure was in particular because they had thin films. So what we did was to do crystal structure prediction, a sort of technique I assume people are familiar with here, so getting various low-energy polymorphs and their relative energetic rankings. And then from those crystal packings, we were able to calculate their charge mobility using Marcus theory, and this is together with my colleague in physics at Imperial, Jenny Nelson. And so for that, we could get the charge mobility in each of the different dimensions for each of the hypothetical polymorphs. And this showed that the lowest energy enantiomer polymorph had a very different packing to the racemic structure, and that's why you had 100 times greater charge mobility in the racemic structure. So I'd sort of argue that it doesn't necessarily come from the chirality, it just comes from the difference in the solid state packing, although of course that relates to the chirality. So we wanted to explore this further. So we decided to, okay, let's just look at one system, don't change the molecule at all, and try to fully explore what is the influence of the crystal packing. So we chose the carbo-6 helicene. So what was known about that is that there's an enantiomer structure for that reported. Its code is hexel. But it doesn't have any racemic structure that's ever been reported. It's thought to only have an intergrowth structure. And there are no known reports yet of its charge mobility performance. So again, we did crystal structure prediction so that we could explore what are the different types of packing that you could get. So here we have our typical landscape for that with energy on the y-axis and density on the x-axis, and we see that typical trend where the more dense structures are lower in energy. And these are DFT relative energies. We work with Erin Johnson, who's at Dalhousie University in Canada. So she uses her XTM approach to get really accurate relative energies with a good consideration of intermolecular interactions. So these are coloured and have rings depending on the type of packing motif that they have. And so one thing we can see is that the lowest 3 packings all have the same types of interactions, and I'll show you those packing motifs in a moment. And then higher up you have a range of different packing motifs, but there's particular packing motifs like the one with the red ring that's really common. The lowest energy structure was hexyl, the experimental structure, so that's reassuring. The second lowest in energy is an intergrowth structure where you have the chains that are in hexyl, but they're arranged so that you have a different ordering of them. And that's lower in energy than the racemic structure, so that explains why a racemate has never been able to be experimentally observed. So on this next slide, this shows the different packing motifs coloured as we had them on the last graph. So where they're grey, that means that the molecules have all got the same chirality, and where you have cyan and purple, those are molecules of the opposite chirality. So particularly popular packing motifs, one is that one in X, that's green on the right-hand side, this sort of herringbone and with a translational symmetry. And then in red is even more popular, also having a translational symmetry, and that's observed in about 2/3 of the structures. So now let's think about how these different types of packing motifs relate to the function of those polymorphs. So here we have a plot of both the hole and electron mobilities that we have calculated from those hypothetical polymorphs. So hole mobility on the y-axis and electron mobility on the x-axis. So firstly, we can see that very few of the polymorphs have good hole mobility, but those that do tend to have those green types of packing motif going in one direction. So in particular, that green motif shown on the right-hand side. So clearly, that motif tends to confer good hole mobility along that axis. And then we see again, so we see that red packing motif with translational symmetry is very popular. More than 2/3 of all of the low energy polymorphs have that packing motif. We see that that packing motif is involved in having high electron mobility, but it doesn't always relate to high electron mobility. But in general, this carbo-6 helicene typically very often has good electron mobility, and these electron mobilities are actually very reasonable when compared to other organic systems that have had their charge mobility calculated in the same way. So that was looking at the influence of packing, and then Francesco, who was actually mostly doing experiments in Matt's group, did a similar sort of set of calculations, but in this case assumed we always had the same packing, so basically assumed the hexyl packing, but made changes to the molecule, but only very small changes to the molecule. So he just changed the position that the nitrogen was on the helicene molecule. So you could reasonably assume that you would plausibly have the same packing, but we have now made molecular changes, and so there are 16 different positions that nitrogen could be, and we then looked at the influence on the charge mobility. So we could see that you could change the charge mobility by an order of magnitude by moving the nitrogen atom to different positions. And we again found, much like we did with the previous set of hypothetical polymorphs, that specific packing motifs in one dimension tended to confer higher transport, and in particular for electron transport, that translational packing motif I already showed you tended to confer higher electron transport. So sort of at this stage, we felt like we'd been getting really nice insight via using the simulations on the interplay between the energy of the polymorphs, their crystal packing, and the function, being able to pull out separately the effect of chirality, molecular changes, and packing. So we'd seen that, you know, obviously this is a complex interplay, but there were clearly particular motifs that tend to favour good transport, and that's that translational packing motif in particular for electron mobility. And we could see that there is the potential to tune or optimise the function by making molecular changes. So at this point, we thought we're trying to do what we're always trying to do as computer modelers, and that's get out ahead and make predictions rather than to be rationalising what was already been observed. And so Julia, who was doing her PhD in my group, decided to do some helicene screening on a larger scale. So to take the carbo-6 helicene and to think there's lots of different ways that I could functionalise that molecule, and can I use that as a way to increase the charge mobility, in particular electron mobility, in these systems? Now, we can't do a full CSP if we're looking at lots of different systems. So what we did was to make the assumption that, okay, we see that the translational packing motif is found in 2/3 of the structures for hypothetical polymorphs, and also in 2/3 of the structures that are in the Cambridge structure database for helicenes. So we can make the assumption that it's likely that we can get that packing motif. So we will characterize our hypothetical molecules by making the assumption that they're going to pack with that particular packing motif. And so she could come up with lots of different functionalizations that she could do to that helicene molecule, and you could do that at different positions around the rings. And we considered both mono and symmetric difunctionalization. So the way her screening proceeded, so we had 1,300 different molecules that way, which is why we definitely couldn't run full CSP for all of those. So we start with the substituted helicene at the top left. We assume that those molecules are aligned with that translational packing motif. But we'd appreciate that if you've got different functional groups there, those dimer pair may sit at a different distance. So we at that point sort of scanned the distance, looked for the low energy sort of intermolecular interaction distance, and that would then give us a dimer in the arrangement that we would hope it would be if you crystallize that structure experimentally. And at that point, we can calculate J, the transfer integral, and we can also calculate the inner reorganization energy. And that then allows us to calculate this metric J over lambda. So we can just think of that as sort of regardless of your charge transport regime, that metric and increasing that number should relate to a better charge mobility in a system. But we could do that just by getting the dimer, assuming the type of packing we were having in the solid state. So she did that for these 1,300 different systems. So we end up with these plots. This is for mono substitution. We have the same one for di substitution. And so this plot is arranged. So on the y-axis, we have that metric, J over lambda. We're looking to increase that value. And on the x-axis, we have all the different functional groups arranged in order of increasing average value for J over lambda. And it's average because this is mono substitution, and there were the 16 different positions that we have considered. So we can see on the right-hand side that you're doing best where you have the smaller substituents, so sort of halogen, fluorine in particular. And then we have a couple of outliers, which are those diamondoid points, which are a dialdehyde and an acetylene functionalization. Now, the thing that's rather sad is that blue line is the value that you get from carbo-6 helicene without any functionalization at all. So we've now tried out 1,300 different functionalizations and essentially found out that nothing improved on just leaving the carbo-6 helicene at all, which the reviewers hated for this paper. They said it's pointless then, it shows that nothing works. But I thought it was pretty useful because it would take a really long time to synthesize and find that same answer out in the lab. And that the 6 helicene hasn't really been looked at experimentally either yet, as I said. So it's a useful hint that that would be really a very good structure to look at. And of course, similarly, you can do other sort of analysis of the data. Something else the reviewer hated, this is a paper that doesn't know if it's a data or chemistry paper. But with this data, you can look for trends. So this is not looking at the type of functional group, but looking at the substitution position. And again, you can see there are certain substitution positions that are more likely to increase your J over lambda value. But we appreciate that it's sort of not necessarily a great approximation to assume that you have a certain crystal packing. We know that these things are really sensitive to the type of molecule. So we took the sort of top 4 hits, so the top 2 based on averages, which is the di and monofluoro substituted systems, and then also the dialdehyde and the acetylene, which were those anomalies. And we took those and said, okay, let's now do the full crystal structure prediction calculations. So I'll show you those for the mono and difluoro substituted examples. So again, we've got our CSP landscape, and at the bottom, we've got some of the top polymorphs for those 2 systems. And this landscape is coloured green, where we did observe that expected translational symmetry motif within the structure, and then the ones that are in pink are where we didn't. So again, we see probably about 2/3 of the structures do have that translational symmetry, and quite pleasingly, it's even more amongst the lowest energy polymorphs, like for the difluoro substituted, all of the lowest 10 have that translational packing motif. And that did translate when we then ran the full mobility calculations across the whole cell axes to high mobility as as well. So this is a histogram plot comparing all of the charge mobilities of the sort of any polymorphs that are within sort of about 10 kilojoules per mole of the global minimum. So we see at the bottom this carbo-6 helicene that we'd ran before, and we see that actually in some cases we do get, particularly for the mono and difluoro substituted system, the very highest charge mobility is in fact higher, and the average is also better than it is for the 6 helicene, and pleasingly some of these high values are coming from the lowest energy polymorphs, so they are the ones that we could hope to be observing experimentally. So we would still say it's looking really promising to look at the fluorosubstituted systems, and that's what's going on now in the lab. But frankly, I mean, that does take them several years to sort of synthesize and then try to get nice crystals in order to characterize it. So yeah, that I will finish there. So in particular for this work, we've been trying to tease out the relationship between structure, energy, and function, and taking that learning to try to do screening, where we're trying to sort of skip having to do a full solid state consideration when we're looking at thousands of systems. I would like to acknowledge my group. I've obviously mentioned those that have done the work that I've talked about already, and my collaborators, and of course, funding bodies for the funding. And I'll also sort of acknowledge, thank you very much, Pancho, for the invitation, but also for making sure we had childcare, so both my husband and I could come here today, and to the Royal Society of Chemistry that also helped us with the funding for our daughter's travel. It's really easy to apply for their travel grants for attending conferences like this. And I'll also dedicate this talk to my husband today on his birthday. I hope this is the best present you could ever have, is this talk. Seeing as I couldn't fit anything else in the suitcase, so yeah, this talk is your birthday present, and enjoy. Thank you.
Thank you very much. Do you have any questions? Over there. While the mic is migrating to there, I've got a question. So you mentioned with the coarse grain model with the porous cages, you mentioned that one of the structures was the solvent included structure. Was that just based off of the packing? You didn't actually do include solvent in the model?
Yeah, no, we don't include solvent because we're obviously trying to get it as simple as possible. Yeah. But yeah, so we think that, I mean, you can't see that one as well in CSPs. We think that that's quite a high energy polymorph that is only being stabilized and being directed to with solvent inclusion. Yeah.
So my question then is, do you think you could include solvent into these models and get fairly accurate results?
Yeah, I mean, I'm not sure that we would try to do that this way. I think the way that you would do that within CSP, and where there's nice work, I think Aurora has done some, where you're effectively doing CSP on a co-crystal by including the solvent there. And I think what's interesting is what you could do, if you identified a really interesting phase when the solvent isn't there, you can do types of simulations that Graham Day has done on these before, where they then do a sort of Monte Carlo that looks at docking solvents in to try to find which solvents give the biggest stabilization energy for a particular polymorph. So you can use that way to find how you can direct solvent to a specific polymorph. But the stabilization energies can be really massive, sort of tens of kilojoules per mole. So that would sort of explain why you wouldn't therefore be seeing that on your really low energy CSP landscape.
Okay, thanks.
Kalle Ernst,
Hi.
University of Zurich. I mean, charge carrier mobilities of a solid are basically determined by interfaces, by domain boundaries. So we learned from Professor Eckhart that hexahelicene, for example, is crystallizing as a laminar twins. So have you ever considered to model grain boundaries between different enantiomers? I think the packing itself is not enough.
Yeah, I mean, I definitely agree. I mean, we definitely see where they have measured these charge mobilities experimentally, we're able to pick up trends like this order of sort of 100 times better for a racemic over an antipure. We also see in the calculations. So I think we're not trying to accurately predict the mobility, but to qualitatively predict the trends. But yeah, it's definitely true that the intergrowths and the grain boundaries are really important. We are not yet directly considering that here. We have been able to look at the structures as well, but generally where they've been doing measurements, they've been doing it with thin films, so they haven't again known the structure again, and it's not necessarily it's unlikely to directly relate to these crystalline polymorphs that we're looking at. But actually, again, if you compare with their GWACs, you can sort of see how some of our cells definitely relate to the structure that you've got. But yeah, I think you'd have to use an entirely different approach to be looking at the grain boundaries. But those types of simulations in other systems as well, like looking at sort of functionalized fullerenes and so on, do tend to help you explore the trends in the systems too.
Yes, thank you. Very, very nice talk. My question is almost follows on from the last one, really, that the potential for using your Python scripts is to go beyond the molecular into cluster modeling. Through cluster modeling, you get a tool that you can, in my area, you can use in formulation. So that one of the big scientific challenges is how can you know de novo how two crystalline phases will interact with each other, because in a drug that impacts on stability. So you measure the stability of a drug and then you formulate it and the stability changes. Why? And there's a solid state reaction going on. So I kind of wondered when I saw your nice Python script whether that was an area you considered or whether it's just a bit too applied.
Yeah, I mean, we definitely haven't considered directly that area because we do come more from the porous materials background. I mean, we do look at other systems in the solid state a lot in the structure prediction, like the porous polymers and looking at molecular separations in those. And what I didn't talk about today in metal organic frameworks, we look at sort of controlling the level of defects and the level of order and looking at how that relates to function. But again, we're looking at porous materials. But in theory, you can make the interfaces, and that's what we're looking at a little bit more, where we're looking at the porous polymers as well, is you can bring those together. And then our software is sort of the starting point for that in creating the sort of molecular structures that you then do sort of annealing and packing procedures on. But yeah, we have done that, but that's not an area in terms of the formulations that we work in.
Yeah, I mean, going back to Len's talk yesterday, on solid-state reactions, if you think about it, you have two reactants in a mill, and you really want to know the interfacial process going on between the two. And it just seems to me you've got the beginnings of a kernel of a modelling approach, or you've not applied it to that area, that could make quite an impact.
Yeah, I mean, I think it's, my gut feeling is yes, we can't then be doing that at the sort of atomistic level. So then I think that's where the coarse graining potentially comes in, that it could be good to try to be using that to explore different types of interfaces.
But you can, because if you work with organic systems, the interactions are all short range.
It's all in there, yeah.
But with organic, the delight of organic modelling is you can do that.
Yeah. No, we definitely could. We just choose to, we hone in on that. Oh, look, that bit's looking a bit crystalline. Let's see what that is. But yeah, definitely, it's already got the functionality there to do it.
Very nice.
Hi. So I was wondering, how about the electronic pictures of this in this system? So the charge transfer integrals, how they would be. And so I expect this system is really it has a very delocalized. At least in the ideal structure, but how about the distortions that a thermal condition will be? I mean, would you expect this to play an impact? And maybe you check what's the basically how the charge transfer integral are affected by different. I mean, besides the packing, I mean the nature of the HOMO and LUMO, for instance, and these things. Yeah, thank you.
Yeah, so obviously when we're doing the screening and we're just calculating the J, then we're not considering that. But then once you're doing the full Markov theory, then you are factoring that in to some extent. We spent a long time sort of looking at the HOMO and LUMO levels, visualizing them, because you sort of feel like there should be some rational, but I think that tends to not be very satisfying and is maybe a bit dangerous to sort of not over-interpret those things, yeah.
All right, well, thank you for the questions, and then can we all just thank the speakers once again for a fantastic set of talks. Yeah, so we're pretty much on time, so see you all back here at 11. Can all the speakers of the next session please just come up and test their laptops if they would like to do that. All right, see you at 11. Who is next for...
So welcome back, everyone. The second half of this session, we're going to kick it off with Ognjen Miljanic from the University of Houston, and he's going to be telling us about greenhouse gas capture in porous molecular crystals. So, Ognjen?
Before the talk, can I make a very quick announcement? If some of you late registered and you didn't get the chance to get the bag and all the startup package and you want it just also as a souvenir, just you can come see me and I will provide you one. And second, during the first boat trip, we found some lost sunglasses. No one claimed them. They are in a bag, in a case, French Connection case. In case someone lost it, they can come and see me again. Okay, thank you.
Okay, and then should be all good. Good.
Super. Good morning, everyone. It's always great to see so many of you still in the audience after several nights of Macedonian wine. And I will start my talk by echoing one of my teachers from UCLA, Miguel, and thanking Tomče for really great hospitality and generosity, first in inviting me here and inviting, I guess, all of us here, and then providing really what was a remarkable time. So you should be very proud. And now I'll talk about something not quite as happy. Greenhouse gases. Yeah, so we are here in this beautiful location which combines science, history, and nature. One thing that we should remember is that beautiful locations such as this one are very fragile, right? National parks and other places of great natural beauty under threat from us, really. And to bring this into focus a little bit, climate change is, without much debate there, the biggest civilizational problem that we face. And images such as these are becoming a lot more common now. And so all of these images have been taken in the past 5 years. On the top left corner is my hometown of Houston in 2017 after hurricane-induced flooding. This is actually happening right now in Eastern Africa, where drought, which was unprecedented, is driving farmers into really refugee status, even though there is no actual war. A couple years ago, this was the most devastating fire season in Australia, which was only to be exceeded by the most devastating fire season in California. And this is actually something that is also close to me in Houston. This is Louisiana, which is actually, this is not flooded, but Louisiana is the part of the world which is suffering the fastest land loss of the whole world. So every 1 hour, which is the time I'll take for my talk, it's a joke, right? Every 1 hour, Louisiana loses one soccer or football field off land, mostly due to saltwater intrusion from the surrounding sea. And this is a consequence of both energy industry and climate change. And so the changes in our climate are being caused by the changes in our atmosphere. And change in our atmosphere is not solid state, it's gas, right? These are the greenhouse gases that are major culprits of the observed climate changes. Carbon dioxide is the most potent one. It's the most potent one in absolute terms, but in relative terms, it is actually a relatively mild greenhouse gas, and this is why all the others are benchmarked against it in terms of global warming potentials, which tell you relatively to carbon dioxide how much worse a certain gas is in terms of causing global warming. You see that these values vary widely. Now, of course, they also vary in the vertical direction, but also in the horizontal direction, because these gases also have differing atmospheric lifetimes. And so depending on the time horizon, this changes, right? And so when you put all this together into sort of a simpler to understand graph, these are the carbon dioxide equivalent emissions in gigatons. And this is what is causing, this is the greenhouse gases emissions total. About 3/4 of it come from carbon dioxide. About 1/6 comes from methane. Nitrous oxide, which comes mostly from agriculture, is the remaining 6%. And then these F gases, which are various fluorinated gases that constitute really most of this table, are the remaining 2%, right? And so what I'll tell you today is two short stories about how we used porous molecular crystals, initially serendipitously, but now really by design, to capture various classes of these gases. And so the first, and so there's a lot of abbreviations on this slide. PMC stands for porous molecular crystals. CFC stands for chlorofluorocarbons. These compounds used to be known as freons, or they're still known as freons. And HFC stands for hydrofluorocarbons. We'll talk about those in a minute. And so we entered this, this arena, as many an aspiring young assistant professor would, by looking at metal organic frameworks first. And we were really focused at looking at sophisticated organic ligands, in this case extensively fluorinated organic ligands, as precursors to metal organic frameworks. And this is one of the materials that we made that turned out to be the most promising one. It is based on this trigonal tetrazolate or tetrazole, which then deprotonates, gives us this cluster, and then this translated into a crystal structure, which is shown here. This crystal structure took not one, but two synchrotron facilities, one in the US, one in Taiwan. And this was published some time ago. By the way, I have these QR codes. This is my latest fascination, so you can just take photos of my slides, and they'll take them exactly where I want you to take them. Okay. Now, to refresh your memory. Okay, so this material was quite porous. And as you can probably appreciate, with a lot of metal organic frameworks, there's a lot of talk about sorbing various gases. As you can probably appreciate, this is somewhat expensive, so not the greatest platform for sorbing something like carbon dioxide or hydrogen or something that's literally quite cheaper than dirt. And so we found a niche use for this material in the binding of some of these fluorinated gases. And so you see that some of the gases that repeat from the first table on the first slide are now tested as guests for this host framework. And the gravimetric uptake capacities are pretty good. They reach the highest point here with perfluorohexane, which is bound to the tune of 225% by weight. So this material takes up more than twice its own weight in perfluorohexane. Other than that, we didn't establish very strong correlation between structure and the adsorption level, except for one data point, and that is that gases with zero dipole moments, such as sulfur hexafluoride or tetrafluoromethane, they have very low adsorption capacities incommensurate with their size or molecular weight. And so the problem with this material was that we would do these sorption-desorption cycles, and after 5 or 6 of them, they would start losing crystallinity and eventually completely sort of dissolve into a muddy-like material. We don't have a rigorous explanation as to why this happened, but we have one that sounds pretty logical, and that is that these fluorinated aryl groups acidify the neighboring hydrogen, and so it's easier to deprotonate, and making this MOF is relatively easy. My students would kill me if they hear me say this, but once you make it, then we don't have the tetrazole anymore, we have the tetrazolate, and the tetrazolate is now less basic because of fluorination, and on account of that, this is not a very good ligand. And so, since we expose this network to a lot of mechanical stress by sorbing and desorbing eventually, and we don't do this at absolute zero, this falls apart. And so to circumvent this problem, we turned to one of our few strengths, which is synthesis. And so we wanted to replace this relatively acidic group, which is tetrazole, with a less acidic pyrazole, which upon deprotonation would have given us a more basic ligand that would then presumably solve our stability problems. And do exactly that. This is the synthesis. It is quite short. And starts with iodo-pyrazole, which is then trityl protected here at the nitrogen. And then we CH couple tetrafluorobenzene twice. First to this pyrazole, and then to triiodobenzene to give us this trigonal network, which sets up all of the atoms that we need. Then we simply exchange the trityl group for the Bock group to set us up to the very last step in our synthesis, which is solvothermal reaction. I think this community needs no introduction to solvothermal chemistry, so I'll skip it. But I'll just tell you how we planned this experiment. And so the idea was that we're going to have this material, we're going to heat it in DMF. This heat will thermalize the Bock group, install the free NH group here. DMF will also decompose at that time. We learned about that, about the sophistication of that process yesterday. But it will generate base and deprotonated NH group. And then we had the metal in there, which is supposed to coordinate and give us a metal organic framework. And so we do all of this, and then we get very surprised. We get crystals, we get single crystals. We take them to the synchrotron. And then my student, in despair, comes back and says, this is just starting material, right? However, so what we did here is we made a porous material. Actually, it's quite porous, but there's no metal to be found. So we made the MOF without metals, right? The ultimate heresy. Yeah? So what happened here? Well, the problem here was that this was a poorly planned experiment from the perspective of an inorganic chemist, because zirconium is quite oxophilic. And we do this in wet methanol and then generate base. So zirconium promptly precipitates as zirconium dioxide, which serves no purpose in this reaction. So I'm showing you this slide just for historic reasons. This works just fine if you cross out zirconium. So zirconium is completely unnecessary here. And so what happened here is just the first step of the proposed three-step sequence. We deprotected the Bach group, put an NH group here, and then this trispyrazole created a porous molecular crystal. And this is something that is not really supposed to happen because small molecules are supposed to closely pack in the solid state. And so what's holding this framework together is entirely non-covalent interaction. At each one of these trigonal junctions here, we have a triplet of hydrogen bonds between pyrazoles, and this is not very unusual. Most pyrazoles that are not crystallized from hydrogen bonding solvent will show a pattern like this. What is different about our molecule is that in the neighborhood of electron-rich pyrazole, we have the electron-poor tetrafluorobenzene, and they can pi-pi stack. And I'll need both hands to do this, so if my computer slips. So they'll pi-pi stack in this head-to-tail arrangement, where you will see that each one of our molecules will coordinate to the top and bottom neighbor on each one of the three arms of this. And so overall, there's 6 pi-pi stacking and 6 hydrogen bonding interactions per molecule. And while individually weak, they end up resulting in a framework which is quite stable. It's stable constitutionally. We tried that by using TGA analysis, and we only see weight loss at about 380 degrees, which corresponds to loss of 3 molecules of HCN, which is a known decomposition pathway for pyrazoles. In terms of structural stability, this material transforms into a new phase right about 280. We pinpointed this by DSC. And then this new phase, the high temperature phase, appears to be, it doesn't appear, it appears to be crystalline, but it's not porous anymore. And this is consistent with the literature because these extrinsically porous molecular crystals, which means molecular crystals which are porous because of inefficient packing rather than just macrocyclic structures in the molecule, they are notoriously polymorphous. And the most stable polymorph is typically not porous. And so our observations are consistent with that. Now, this material will also bind various greenhouse gases. The capacities are now lower because the pores are smaller, but we have solved our stability problem by completely doing a different thing. We can now do 20 cycles, and there's no loss of capacity in any one of them. Right? And this, of course, makes sense chemically because this is just pyrazole. And pyrazole and perfluorohexane, they don't react with each other, so there's no reason why they should ever compromise each other. In fact, this material, even though it's held together by non-covalent interactions, is superbly stable compared to MOFs because it's a weak acid, it's a weak base, it's not soluble, or it doesn't react with water, and so you can really boil it in dilute HCl for a week and nothing happens. This, actually, I meant to say this earlier, but this is all work of Teng Hao Chen, who was my former student, now a professor in Taiwan, and his co-worker at the time, B. Kavevichai, a person who has a less pronounceable name even than me. You'll notice also that this is a 5-hour-long cycle, and they did 20 of them, right? And so now they're married because TGA analysis, lengthy TGA analyses brought them together. They're both professors in Taiwan, so, you know. Anyway, so perhaps unsurprisingly, these materials will bind other small fluorinated things. Turns out that most of the inhalation anesthetics that they use in the clinic are small fluorinated ethers. And unsurprisingly, our material absorbs all of them. These look kind of identical to freons because to a chemist, these are very close to freons. But now there is an economic incentive to do this. A liter of a freon costs $5 to $10. A liter of something like this costs close to $500, and the hospitals will still vent about 50% of unused anesthetics into the atmosphere, where they contribute to global warming, but it's just a big economic loss. In the US, it's estimated that unused, lost anesthetics cost the economy $1 billion. Right? And so we started a small startup company, the idea of which was to see if we can use this adsorbent as a platform for recycling of anesthetics, because anesthesia is also mostly physical phenomenon. So most of the anesthetics actually leave the patient's body chemically unchanged, just effectively dirty, and so they would need to be repurified. So if you have any money that is just sitting and not doing anything, they're always looking for investors. But there's other features of these porous molecular crystals that I think this community is very, very well aware of, but they are unusual among moths and coughs, and that is that they are sort of rubbery. Porous materials are very often likened to sponges because they have pores, but if you really think about a function of a sponge, it's not its porosity, it's its squeezability that is the key to that function. And here, crystalline materials, with notable exceptions presented here, not terribly squeezable, and these are a little bit more squeezable than the completely covalently connected frameworks. And so upon guest entry into the pores actually shrink around the guest because there is now a new van der Waals surface that they want to get in touch with. But at the same time, they have to relieve that pressure somewhere, and they do it in the pi-pi stacking direction. And both of these changes can be measured by solid-state UV spectroscopy and by indexing powder X-ray patterns so that you get the unit cell parameters, which then tell a story of reversible and reproducible change in about 3 or 4% in all of these parameters. And so this may not be perhaps a terribly practical sensing mechanism, but there's a clear response to a guest as it enters the pores. This was also work of now a professor in Oregon, but then a graduate student, Chris Hendon, who was then at the time a graduate student with Aaron Walsh, and so we published this some time ago. Okay, so switching away from fluorinated materials, the second part of my talk will talk about another class of small organic molecules that we made that we now are exploring a lot more intensively as potential platforms for binding of carbon dioxide and perhaps even methane. And so the conferences are a great thing because you get to meet all your friends if you're a professor, and then you get to learn a lot of new stuff, especially if you're a graduate student. And so this is exactly what my student Xing Ji did at the conference on International Macrocycling Supramolecular Chemistry Symposium in Shanghai in 2013. And so he came back with all of these ideas, one of which was to try the reaction which takes a small aromatic dialdehyde, isophthalaldehyde, and under benzoin condensation conditions creates a macrocycle. Right? And so this obviously worked. It was published. However, this was an experiment that I not strongly, but moderately strongly discouraged, because this was tried in 1890, and it did not work. Right? This exact reaction was attempted, apparently producing only a dimer. Then it was repeated in the 1950s, and all of this is actually published unsuccessful experiments. In the 1950s, presumably the benzoin condensation of isophthalaldehyde resulted in the production of a polymer, which at the time could not be really characterized. And so I told him all this, and this is all the encouragement he needed. And so it turns out if the conditions for precipitation are adjusted just right to almost exactly 1-to-1 ratio of ethanol and water, this material will precipitate as a single compound, single diastereomer, of course, as a racemic mixture. And this is this selective precipitation is really the key, because if you have conditions which are too soluble, then the reaction is reversible and a mixture results in the solution. If you have a reaction that precipitates too quickly, a similar mixture happens just in the precipitate. And once you get it, then it's kind of game over, because these materials are very polar, they're very difficult to separate, and so on. Yeah. And so Xing then went on and did an experiment which appeared even less likely to work, where it takes terephthaldehyde, which seems supposed to polymerize, but it doesn't. It produces this material, which we call cyclotetrabenzoin. And we've seen a lot of stereochemistry in this conference, which I loved. So I have an appropriate quiz for the last day. Is this chiral or achiral? And apologies for the chairs laser pointing at them. Miguel. It's achiral, yes. But it doesn't have a plane of symmetry, right, which is the first thing that an organic chemist will look for. It does have an S4 axis, and so on account of that, it is achiral. It is, again, produced as a single diastereomer, and the yield is 20%, which in light of a single-step production doesn't seem so bad, but in fact, it is quite selective, because if you think about it, this compound has many regioisomers, where the OH and CO groups are switched, and each one of these regioisomers has several stereoisomers. And so there is actually, we drew all of them out, there is 40 different cyclic tetramers of terephthaldehyde. And so why does only this one come out? It comes out by precipitation, so it comes out because it's the least soluble. And it's least soluble one because it packs beautifully in the solid state. So if you take this structure and turn it on its side, it organizes into these nanotubal arrangements where the molecules are perfectly aligned. But what is holding them together is not the interactions within the nanotube, but those sort of this zipper of hydrogen bonds, of chelating hydrogen bonds, that connects it to the next nanotube over, right? And if you look at the structure, then you can see that this relationship repeats itself at each one of the four corners. And so when you take these nanotubes and turn them towards you, this is what you get. This is material. This is not a single layer. This is perfectly aligned, and so it looks very, very pretty. Because of this perfect alignment, it has a certain porosity, although it's very small and really not much more than surface porosity. Now, this material was, as I mentioned, very easy to prepare, but also very insoluble. And we wanted to test it in many different contexts. Essentially, all of them required its derivatization to something more soluble. And it took us an embarrassingly long amount of time to prepare the simplest alcohol derivative, an acetic ester. And this compound, of course, eliminated the hydrogen bonding, resulted in a material which is a lot more soluble. But also it gave us another surprise in that now the surface area has increased by more than tenfold. And for this, actually, the acetic ester is completely essential. So trivial derivative on the face of it, but only on the face of it. The reason for this is that now this becomes both intrinsically and extrinsically porous. It is intrinsically porous because it has this relatively rigid pore within the molecule itself. But this molecule is no longer a square. It's really a square with these little cones here because this acetic group is not really this small. It's much larger than this. And that object is just very difficult to pack in the solid state. Right? And so what we have now is the square-shaped pore, which comes from the molecule itself, and this diamond-shaped pores, which comes from the inefficient packing of those molecules. If we switch to any other ester than the acetate, then the larger acyl groups start filling up this pore, and our porosity starts going down. And so this was sort of an unexpected reward. Coming back to the expected one, the solubility of this material allowed us to study its potential as a supramolecular host. And so if you look at the dimensions of this pore, these two rings are separated by about 6.8 angstroms, which means that the guests, an aromatic guest sitting between them, would have a perfect pi-pi stacking distance to both the top and the bottom neighbor. The only problem is that the aromatic guest cannot enter this pore because the pore is too narrow. Right? And so we switched to a class of guests that is related, but not quite as studied, and these would be a linear pi electron-rich molecules, so molecules that are only one atom thick. And these are the crystal structures with three such molecules. This is carbon disulfide, and this is the sort of extended structure which shows the linear disorder of the carbon disulfide that really kind of resembles an insulated wire here. And these are the linear parts of larger molecules, the CN triple bond of acetonitrile and the CC terminal triple bond of propargyl alcohol. This is a work of Corey McHale and her undergrad assistant, Christina Stagemuller. And they have really produced a series of other structures with alkynes and acetylenes incorporated into the pores of this. And within this pore, this is now stabilized by interaction with all four walls because the pi electron linear molecule, pi electron rich linear molecule will now have equidistant interaction to all four of the benzene rings. And shortly before graduating and taking a job in the chemical industry, Corey has crystallized this material with the ultimate linear guest, and that is carbon dioxide. This is an experiment which sounds so improvised that it was never going to work, in my opinion. But I guess I'm very negative about the prospects of my group because whatever I tell them doesn't work, it does. And so she would take a single crystal of this material, put it in a thin glass capillary, and then just put as much dry ice as she could into this capillary, and then flame seal it. And as the dry ice sublimes, 9 out of 10 times these capillaries explode, but they're very small explosions, small capillaries. But the 10th one doesn't, and then carbon dioxide has nowhere to go, so it goes into the crystal, into 2 orientations. So there's this sort of vertical orientation, which is kind of consistent with our supramolecular reasoning, that is pi-pi stacking and all that stuff. But actually, the more likely one is this horizontal orientation, which has no close contacts with anything. So it just fits into these interstitial spaces quite nicely. I should point out 2 things. One is that because of this very unsophisticated jamming of dry ice in the capillary, it's very difficult to adjust stoichiometry in any measurable way. So we have a series of structures with different occupancies that really have, I understand, no fundamental reasoning, it's just technical. And this structure also, both carbon dioxides are not really always there. One has an occupancy of about 10%, the other one about 20% or so. So they're not there at the same time, but one of them is at the point. And there are certainly 2 available sites for them. Now, this material was quite inexpensive to produce, so Corey could, in a single batch, produce about 17 grams of this, and we estimated the cost unoptimized between $3 and $5 per gram, so pretty reasonable. And so we shipped these samples to Taiwan, where my former student, Teng Hao Chen, is now a professor. And so 6 years have passed since his first time on the paper, and during that time he migrated to the end of the author list. Right? He now studies really adsorption in the context of sort of practically relevant separation. And because this material was easy to produce on a moderate scale, their team could pack a column with it and then pass a mixture of carbon dioxide and methane or carbon dioxide and nitrogen to see the separation. And this is sort of an important point that I should perhaps emphasize. Our society produces 30 gigatons of carbon dioxide every year, or slightly more than that. So it's a chemical unmatched in scale to any other chemical. Steel, all plastics combined don't even come close, right? But that carbon dioxide is almost never produced pure. It always comes in mixtures, and almost always it is a minor component of the mixture. If you think about the output of a coal-fired power plant, it is mostly nitrogen. And so separation of carbon dioxide from nitrogen and methane is very relevant. And our material is sort of perfectly suited for this because of linear affinity for linear molecules, so it's pretty clear why methane should be excluded, but also affinity for molecules that have some polarizability, which explains why nitrogen is excluded. And these are the experiments that Teng Hao's team has done, and we have shown sort of separation in this pressure swing adsorption context, which is pretty relevant. And so this was published and actually featured on the cover of Angewete last year. In an experiment which is the collaboration is still ongoing, and so this is the work of Alexander Robles, who is a student in my group now. Together they have attempted now separation of carbon dioxide from carbon monoxide, so arguably 2 more similar molecules. This is also industrially relevant, and you see here that these effectively elution curves are very clearly separating them, right? So, and this applies to both 50-50 mixtures as well as more realistic mixtures where carbon dioxide is really an impurity in the carbon monoxide that is intentionally produced for industrial purposes. These pressure swing adsorption curves show that there is really the purity of outgoing carbon monoxide is really superb, so there's really no mixing. And this was published very recently in a issue of ACS Applied Nanomaterials that is very dear to me because it was a celebration of Fraser Stoddard's 80th birthday. We got one of the small covers. It was one of those covers that is not really a cover, it's just somewhere inside. Okay, so just one slide on the smaller cyclotribenzoin. Surprisingly, this compound, it cannot be oxidized without ring opening. So it kind of cleaves out here. It gives you this linear dialdehyde, which then oxidizes fully to carboxylic acid. But we played with its reduction, and reduction proceeds stereoselectively again if you use a very unsophisticated reduction agent, because the molecule is cone-shaped, and so the reducing agent can attack from only one side. And so this is a crystal structure, and this material organizes into extended structure which has very small pores. But within one of these pores, we have a pentamer of water molecules, sort of, and it's perfectly ordered. While we could not detect any hydrogens on the benzene rings using X-ray, which is expected, we could. All of these hydrogens are actually refined from experimental data, not calculated. This is known as the Walraffen pentamer, in bringing this together, these molecules do something that I, perhaps pompously, liken to protein subunit assembly. This molecule, of course, has very hydrophilic parts and very hydrophobic parts, but 6 of them come together in the solid state to enclose a cavity which is very hydrophilic because they just point all of their OH groups into that cavity and nothing else. And so this is what is happening with that cavity. This is our pentamer, so the one from here. And these are all the OH groups which have organized themselves around this molecule to surround it. I'll show you the same image, but color-coded to show you the identities of 6 different molecules. So there's a benzene ring from one and 2 OH groups, orange one, 3rd, 4th, 5th, and 6th. Yeah? What we're trying to do now is see if we can detect this sort of cluster in any environment that is not a crystal. So we're trying now very soft mass spectrum ionization techniques to see if we can lift it in the solid state into a gas phase and study its perhaps decomposition or hopefully stepwise decomposition as it happens. But sort of more pipe dreamy part of this is would be looking at materials that can capture larger water clusters. And why would we want to do that? Because that could be a way at looking at the binding of methane, right? So methane is a faster growing greenhouse gas in terms of emission, mostly because of larger exploitation of natural gas. But of course, in perspective from sort of supramolecular binding perspective, it is very difficult. It has no lone pairs, it has no double bonds, it has no polarity, so it really has nothing. But nature has already designed a supramolecular host for methane, and there's many of them. So these methane clathrates, methane hydrates, found in permafrost in the bottom of the oceans, have methane encapsulated, mostly to van der Waals interaction, in a water, what do you call it? The 20mer of water, so icosahedral cluster water molecules. And the problem with these is that they're stable only at high pressures, and so not really at root temperature condition. But if we could target that cluster of water molecules, then we could sort of, in an indirect fashion, target methane as the guest of a guest, right? And so this, of course, sounds great on paper, and apparently in my proposals, because some of them got offended. But the idea here would be that we would need to prepare a host which either has more OH groups, or they're more separated, or something like that. We're not really sure. This is one of the molecules with potential candidate. Last year, Andrew Eisterhold prepared first examples of larger cyclotetrabenzoins. Notice that in this case, the regiochemistry is switched, so the OH and carbonyl groups used to alternate, but now they're sort of symmetric. This material, even though we crystallize it as an acetate, so there is no hydrogen bonding, maintains this channel-like structure. Again, a consequence of being an awkward object that they cannot pack really well in a solid state. And so our hope is that maybe one of these would provide these larger cavities for encapsulation of larger clusters of water molecules. The other future direction would be looking at the dynamic character of the benzoin condensation. So benzoin condensation is reversible, and so this should be a material, this should be a very ripe platform for templating the synthesis of tetramer or not tetramer. And there certainly are other things in there, because if we analyze after the precipitating the material I talked about, if you look at the mother liquor, there is really evidence of trimers, tetramers, other tetramers, pentamers, and hexamers. At present, it is very difficult to isolate for us any meaningful amounts of these. But if we could, if we optimize this, which I believe we will, then this would really turn this nuisance at present into an asset. So all of that is a story for next ICOS. I will finish with thanking my students who have done this work. I've been really blessed to see to work with a very international group of students. They're the flags of countries they came from. You will notice there's no Macedonian flag yet, right? So it's, The people that have done this work have mostly moved on. So this is Maimoun Al-Rayani, who is a professor in Saudi Arabia now, Corey McHale, Mohammed Hashim, Qing Ji, who is interestingly a professor of wine science in China. Apparently, I trained him for that. And Teng Hao Chen. And now this is mostly work of Alexandra Robles. I will finish my talk by mirroring Miguel again, because I have gotten news of my grant being funded a month ago. But it started on July 1st. So this is actually my first expense on the new grant from the chemistry division. So the National Science Foundation has been very good to us, and they're now funding this work under the auspices of their critical aspects of sustainability program. So carbon dioxide plays pretty well in that. We are on Twitter, we are on websites, and if you'll allow me, I'll finish with a small ad for a conference, another conference that might have some overlap with this, and this is the third International Symposium on Porous Organic Polymers, which is happening in about a month and a half in beautiful Boulder, Colorado, so lots of mountains. This is the lineup of speakers, and if you're interested in attending, registration is still open, and if you twist our arms, we'll also accept abstracts. And so QR code, website, or just email me. Once again, thank you all for your attention. Thank you, Pancho, for the invitation, and I'd be happy to entertain questions.
Thank you. Yeah, we got a question down the front.
Yeah, thank you for a very nice lecture.
Thank you.
And happy birthday, by the way.
Thank you. It's my
and
birthday.
I have a simple question, actually. When you show some of the absorption profiles, I see some of the induction time quite long, and all of a sudden it jumps. This is for the, when you see the anesthetics absorption. Maybe I read it wrong. As a function of time, right?
Let me show you. Go back to this.
Okay.
So
yeah.
Okay, maybe I should explain the experiment. So we monitor the absorption of all of these guests through thermogravimetric analysis. So it's a gravimetric measure. And so this is our temperature program. We start at room temperature. We heat it up to remove the guests from the previous cycle. Then we leave it at the temperature for a little while. We turn the heating off. We cool it down. And then when it's cooled down, throughout this process, we pass in just pure nitrogen. And then when we're cool this down sufficiently, we switch this to the nitrogen which is enriched in the analyte of interest. And then absorption is very quick. So in all of these cases, it reaches the plateau in about 20 seconds. Now, those of you who might be familiar with the perfluorohexane will know that this is not a gas, it's a liquid. And so the way we enrich nitrogen is by simply passing it through a bubbler full of this material where it sort of picks up a sub-equilibrium pressure of this, but this seems to work. And then, of course, when we switch back and just continue in nitrogen, it's a dynamic experiment, so eventually it all goes out. But it's the last traces require some heating or vacuum.
I see, yeah. Thank you.
Hi. Interesting concept. So I have a general curiosity. So when you prepare all these molecules in lab and study, maybe you do it in the presence of this gas which you want to uptake. Mm-hmm. But how effective this will be when they are really need to be translated for applications in atmospheric conditions where there will be mixture of so many gases, not the selectively one?
That, of course, is an excellent point. And this is a question that sort of has a multi-step answer. With fluorinated gases, capturing them from the atmosphere is just hopeless. Because their concentrations are minuscule in the atmosphere. But the good thing about them is that they're all entirely synthetic. There's no natural sources of perfluorohexane. So it's entirely synthetic and entirely, and many of their emissions are point sources. So a lot of these materials are now being phased out as refrigerants, and so we know where they will be emitted from. And oftentimes it's not the emissions, it's just we want to be long-term storage and sequestration of them. With carbon dioxide, this, of course, is not a satisfactory answer. But again, carbon dioxide, since it shows up in these mixtures where its concentration varies from 0.04% in air to, let's say, 50% in biogas or in some natural gas streams, it is very likely that we will not have just one molecule, and no delusions that this might be one of ours, but we will not have one platform capturing carbon dioxide. So we will need very strong binders, if we're to pursue the direct air capture, and much weaker ones if we're going to look at the capture from this more abundant stream of carbon dioxide. In terms of our specific molecule, so this one, it appears quite robust to the typical side effects that we observe in flue gas streams. So moisture doesn't bother it, right? The heat doesn't bother it, so we can heat this in steam all we like. There's no absorption. And so these will be sort of these are the two influences that we looked at. So it's promising, but it's far from an exhaustive study.
Great. Well, if there's no more questions, I'd like to thank Ong Yin again for a great talk. And coming up next, so our next speaker is Concilia Tedesco from the University of Salerno, and she's going to talk about cyclic peptoids being a playground for non-covalent interactions.
Hi, everybody. And this morning, I will introduce you to peptoids. Peptoids are actually, get familiar with the stuff. Okay, so peptoids are like peptides. Actually, only the side chains is not attached to the carbon, to the alpha carbon, but to the nitrogen atoms. In this way, they cannot form NH carbonyl hydrogen bonds. And so we have tertiary, there are tertiary amides that can isomerize quite easily between cis and trans conformation. They are relatively new. They actually proved to be rather useful. And in this slide, I acknowledge the contribution of this small group, which is hosted at the University of Salerno. So they have been proved to work as artificial ionophoric antibiotics. They have been used as phase transfer catalysts. They also have been used to build glycopeptoid systems to be used as enzyme inhibitors. They show stable porous frameworks, but also single crystal to single crystal transformations. Of course, solvatomorphism and conformational isomerism. I first met peptoids when Francesco De Ricardis entered my lab with this beautiful NMR tube, full with really beautiful crystals, needle-like, very small, but with luck, I had at that time synchrotron beamline at ESRF, and I was able to get this complicated structure of a zwitterionic complex that actually, as you can see, contains 3 strontium atoms and 2 strontium ions, 3 microcycles, and 3 picrates on each end. So we can get rid of the picrates moiety and appreciate the coordination mode of these of the macrocycles. And if we look at the microcycle conformation, then you can readily spot that it looks like a crown eater. And this here indeed explains why these compounds are really used as phase transfer catalysts with performances comparable to crown eaters. And if you look at the peptide bonds conformation, it is, all trans peptide bonds. But this occurs only upon metal binding, because if we don't have any metal around, the conformation of these macrocycles is completely different. We have a cis-cis-trans, cis-cis-trans sequence of peptide bonds, and as you can see, the shape of the microcycle is rectangular and actually mimics reverse turn in peptides, and actually beta turns in proteins. Now, if we look closely at backbone conformation, we can appreciate actually that cis conformation is rather common, and also that there's a certain conformational stability for each, if you consider the macrocycles with the same size. So these are some of the peptides that we actually synthesized and characterized at the University of Salerno. There are 12 atoms macrocycles, 18 atoms in the macrocycles, or 24 atoms in the microcycle. And looking at the packing modes, we were able to understand the role of CH carbonyl hydrogen bonds. CH carbonyl hydrogen bonds provide backbone-to-backbone interactions, and they actually make the peptoids assemble face-to-face or side by side in a ribbon structure if the interactions occur on the long side of the microcycle, or they can have also a short side assembly if the interactions occur on the short side of the microcycles. But also chains come into play, and in fact we can have backbone to side chains, interactions, and the side chains actually act as pillars among macrocycles. And so we can have columns, tubes, and layers. And if we look at the solvent can be actually between layers or inside the tube. But it can also stay actually in between the columns, because there are forming channels. And actually in this example you can see how acetonitrile molecules form 1D channels parallel to the short cell axis. And what's interesting is that you can remove these solvent gas molecules, and actually what happens? It happens that upon gas release, the side chains move by more than 100 degrees to the equatorial plane and form a CH-pi zipper of propargyl side chains. And what's interesting is that this transformation is actually reversible. You can expose your crystal to vapor of acetonitrile and obtain back again the crystal, which actually is transparent as at the beginning, while after gas release, the crystal becomes darker. Now, we investigated the solvatomorphic behavior of this compound, which is based on a cyclic hexamer with 4 propargyl side chains and 2 methoxyethyl side chains. Apart from the acetonitrile solvate, we were able to obtain a pure form without any gas molecules, but with a different microcycle conformation. We were also able to obtain a methanol solvate, just adding a drop of methanol to the acetonitrile, and we got this completely new crystal packing with the microcycle in the same conformation. And actually, you can, of course, exchange the methanol and get an hydrate form. The hydrate form can be empty. This is a true, real, stable framework. And after, we actually also decide to take this empty form as a crystalline powder and load it with propane gas. And actually, you see, and we were able to solve the structure from powder diffraction data and locate the acetonitrile inside the channels. And here you can appreciate, just by looking at the cavity volume in the case of the guest-loaded sample, or to the void volume in the case of the empty form, the adaptability of the channels. Actually, the material prepares the space for its guest. And you go from just 10 cubic angstrom for the water molecules to 136 cubic angstrom for the propane gas. Now, Irenizzo, I mentioned you that at the idea, as I mentioned you before, at the idea to use cyclic peptoids as scaffolds for glyco-based systems. And so she prepared these nice compounds with the 36 atoms in the macrocycle. And actually, I was able, with luck, and of course with the help of a very, I would say, crystallizable PhD student, this is Giovanni Pieri, that I would like to acknowledge for his wonderful ability. To get this, the structure of all these compounds, and actually, in spite of different crystallization conditions, the microcycle conformation is always the same. So, what's special in this conformation is that you have the longest cis sequence of peptide bonds in the cyclic peptoids. You have 5 consecutive cis bonds. And here we can, if you look at the phi and psi value, you can see that actually you got right and left-ended PP1 helices. And next, we asked what are the stabilizing interactions for such a peculiar conformation. We got, actually, we looked inside the molecule, and we actually spotted short carbonyl-carbonyl distances between adjacent carbonyl groups. We also saw intramolecular CH carbonyl interactions. And by looking at the side chains, actually, it was possible to see that also side chains actually have a short contacts with the carbonyl groups to CH groups of the side chain. And therefore, we actually made this parallel between C5 intraresidues NH carbonyl hydrogen bond that actually was proposed in the in the early 80s by Toniolo and Benedetti, and very recently, Newberry and Rains actually evidenced the influence in the formation of extended protein structures. And so we actually would like to propose this new type of interaction, a C5-CH carbonyl hydrogen bond, where the nitrogen atom is actually, NH donor is actually substituted by CH bond donor. Finally, it's time for conclusions. NH carbonyl hydrogen bonds in peptides are substituted by CH carbonyl hydrogen bonds in peptoids. And actually, intramolecular C5 CH carbonyl hydrogen bond emerge as a general feature of all solid-state structure of cyclic peptoids. And of course, I thank my kid who actually provided the photo. I feel really like these compounds provide an exciting playground for evidencing the influence of weak interactions in molecular conformation and intermolecular interactions. And I would like to acknowledge funding from the European Union, who actually was allowed me to interact with the European Synchrotron Radiation Facility, the Institut Langevin in Grenoble, and also the laboratory of Lamb Arbor in South Africa, in Stellenbosch. And thanks to this funding, we were able to organize the first meeting on porous molecular solids in Stellenbosch in April 2015, and later on in 2018 in Vietri-sul-Mare. And so probably there will be a third one. And so stay tuned. Finally, I would like to thank you, Tomče, for building bridges. And if you're asking where Salerno is, Salerno actually is here in southern Italy and hosted the most ancient medical school in Europe. And this is my hero. She is Trotula de Ruggero. Trotula was a medical doctor in medieval times. And now, coming to Ohrid, I learned that Ohrid hosted the most ancient literary school in Europe. So finally, we need to rebuild bridges. Thank you. Okay.
Thank you, Consilia. Got time for some questions? I've got one to start. So you compared the intramolecular interactions you were getting in the peptoids back to the kind of things you'd see in the peptides as well, of when you do have the NH bonding there. Does that mean if you had like a dodecapeptide sort of structure, would they all exhibit cis or long chains of that cis kind of?
Okay, there are. Actually, there are 5 consecutive cis, and they all have this kind of interaction. Although it has not been really, sometimes it was overlooked, because I mean, okay, what's an interaction or a contact? So that's a long debate. So it's the field is open for, I mean, for discussions, I think. So yes, there are. If I understood well, you asked. Yeah.
For like so you show there on the left of when you don't have or when the N only has a hydrogen rather than being functionalized. So for like peptides, so kind of as peptoids versus peptides, would you see long cis chains for those as well if it's comparing as like a similar interaction?
No, in peptide you don't have, actually it's very difficult to get cis. You need a proline to have a cis. Actually a proline is per se, it can be also a peptoid residues because it has the both chains, both on the nitrogen atoms and on the carbon atoms. So with the peptides, you don't have such extended structure, but of course you have these PP1 helices. That of course are seen in peptides, but they are not so common at all. While we are used to collagen PP2 helices, where you have trans actually connection. Confirmation.
Thank you. Okay, just got a question in the middle there.
Thank you very much, Consilia, for this nice talk. My question is, so you show, of course, is a biological-based crystal with application, as you showed, in biological field. My question is, do you have data of biocompatibility of this material in tissue? So are really not toxic?
Yes,
do you have some data?
Yes. Indeed, when they were tested for antibiotics activity, they were also tested for red blood cell toxicity, and they absolutely do not show any red blood toxicity, and moreover, they are less prone than peptides to peptidases. So they are probably they would resist to degradation into the body. This is why also actually Ron Zuckerman and Kent Kirschbaum, who funded actually the field, are looking into. Yes.
Thank you very much.
Perfect. So thank you again, Consilia. So now for the final talk of the session, Jason Benedict from the University at Buffalo is going to be talking to us about diaryl ethene-based crystalline materials and the design and function of them.
Wonderful. All right, well, good afternoon. Thank you to the chairs of the session. Excellent sessioning. Thank you to Tomče for the invitation to be here. And I would also be remiss if I did not thank the person who canceled a few weeks ago and opened up the spot for me to come here and speak to you. So whoever you are, thank you. So this is how the title of my talk today was displayed on the website, Diaryl Ethene-Based Crystalline Materials Design and Fun, Kachung. And I took that as a not-so-subtle hint from Tomče to make sure I included a lot of fun. So in keeping with the theme of the session, holes in crystals, I promise a whole lot of fun. See what I did there? Thank you. Thank you. All right. Yeah, right. Okay, here we go. First, oh no, not a pointer failure. Oh, look at that. Here we go. First, I'd like to thank the folks that have been doing the work. These are my graduate students. I've also got a lot of great collaborators at National Labs. In fact, we just saw Yusheng's picture in Onions. I have a tough time with some of the names talk. But anyway, Yusheng Chen is the beamline scientist at NSF's ChemAC where we do a lot of experiments at home, but we also, some of the results I'll show you today, take place at National Labs. And okay, so we'll roll right into this. Chemical-assisted fun, all right? And so here we have a lovely little cup of coffee. And obviously this is caffeine, so this is something many of you have been having during the trip here. Also, the nightlife, a little beer sitting out on the Orchid patio, very, very nice. And a few of you may have seen this nestled away in the corner of the bar. This is a bunch of tobacco products for sale. And this, of course, would be related to the chemical nicotine. And that'll be the first part of my talk today, is actually a little bit about some nicotine research we're doing in my lab. And so it's related to vaping. So anyone out there, big vapors? No? Yes? No? Not? All right. It's all right. You're probably better off not being a vapor unless, of course, you're a smoker. But anyway, I digress. What is vaping? If you're not aware, this is a technology by which a solution of vape juice that contains nicotine is run through typically some fibers and heated up with a hot metal coil, vaporizes, and you suck it down. All right? And what is in a vape juice? Well, it contains a whole slew of things, a lot of propylene glycol, glycerin, generally a nicotine salt. It can be a free base of nicotine, and also flavoring agents, which contain all sorts of crazy compounds. And, so for example, here's the back of a Juul package, and you can see the ingredients. There it is, glycerol, propylene glycol, flavoring, nicotine, and benzoic acid. And I'll be talking a little bit about safety today, and it's interesting to note that nicotine itself, while it is a toxic compound, shown here, can be poisonous, it's actually not a carcinogen or a suspected carcinogen. It's toxic, but that's about it. And it definitely is an addictive compound. All right, and the thing is, with a lot of these things, they may be some food-safe ingredients, but people don't necessarily go testing what happens when you heat it up. And it's important to know that the coil of a vape device can heat to between 250, people run it at different heats, but it can typically run at 250 C, sometimes as high as 350 C, and that can cause a lot of undesirable side reactions. So you see here, GL is the glycerol, propylene glycol can dehydrate and cyclize to give benzene, which is a known carcinogen. The benzoic acid that's used in a lot of the salts can decarboxylate and give benzene. And so what this is doing is this is basically subjecting some of these users to benzene exposure in using vape devices. And so I had a great student join the lab where we started thinking about this, and people are adults, they can choose to do what they want to do, and if you're going to vape, being exposed to carcinogens is, not a good thing. And so is it actually possible to use crystal engineering to try and make vaping a safer experience? And so it turns out that there's some work out there. Here's some work done by Capucci where they co-crystallize nicotine with a few different coformers. And you can see here, for example, perfluorinated diiodo benzene and the like. While these are doing a good job of putting nicotine into the solid state, these are something you probably do not want to go vaping. It turns out, probably to no surprise, that the tobacco companies are quite active in this sort of a space. And so Devin, we came up with this idea that, hey, why don't we go looking at some different carboxylic acids and can we find some that are going to be safe, GRAS listed, so this is, in America, this is the generally regarded as safe, so GRAS listed compounds. And the idea being, can we combine these with nicotine to make stable nicotine solids? And when you heat them, will the GRAS listed compounds either stay GRAS listed compounds upon heating, or if they decompose, they'll decompose into further GRAS-listed compounds. And so here's the idea. So then Devin went to work and started making a whole slew of these things. So we now have a ton of these nicotine salts. All of them they're all GRAS-listed salt formers. And it's important to note if you heat up these materials, again, if the salt former degrades, it degrades into a GRAS-listed compound. So here's an example of it. Here's nicotine with 2,6-dihydroxybenzoic acid, very nice crystal structure. I won't show a lot of the structures today, but the idea here is that if you heat 2,6-dihydroxybenzoic acid up high enough and it ultimately decarboxylates, you basically get resorcinol, again, another GRAS-listed compound. So the cool thing here with having all of those structures is that they all have these tunable thermal properties. And ultimately, this was sort of one of our ideas for, again, creating vaping materials. Can we create materials with tunable thermal properties for potential devices? And there you go. We've got a real broad range of temperatures depending on which particular salt former was used. And we're starting, we're doing a few other analyses, but again, I'm going to go through this pretty quickly. But you can see that basically the delta melting point of the coformer relative, or the salt former relative to the melting point of the salt, we've got a pretty nice correlation here. And so this will allow you, if you really needed to dial in a specific melting point, that would enable that. And again, I'm not going into it too much today, but these salts are also extremely photochemically stable, which is important because nicotine, it turns out, will actually degrade in the presence of light and turn into you know, a few different nasty things. And so, again, at the end of the day, this is all about harm reduction to an end user. And I know that at this point you're all thinking, okay, that's all fine and well, but you know, the question I'm sure you're all really asking yourselves is, will it vape? Can you actually vape this stuff, right? You're making a lot of really cool salts, Jason, but hey, you know, can we actually vape this stuff? So it turns out there's actually a YouTube channel, Vaping Fool, who vapes all sorts of stuff. And again, I don't recommend anybody actually do this, but you can go follow this guy and see, you know, what it's like when you vape a Monster energy drink condensate. But anyway, so the question is, will it vape? The answer is, oh yeah, so, well, to answer it, we wound up buying an iStick Pico with side top airflow atomizer and a titanium bucket. So this is, you know, a device that actually is typically used by cannabis users, but anyway, if you have questions about it, I'm happy to answer. So anyway, the question of will it vape? Here we go. There's the device. We've got it set up, a really nice syringe, very, very precise and technical here. And here we go. This is Devin, and boom, we turn on the device, and there it is. A nice plume of, I forget exactly which salt this was, but the little vape cloud there, in fact, contains nicotine and the coformer. And so yeah, it'll definitely vape. So anyway, we're sort of excited about this because again, we hope that these are a way to ultimately make, you know, like look, if you choose to use these things, go for it. But hopefully it'll be a safer experience. So anyway, back to function. I'll spend a little bit more time talking about what is really sort of the bread and butter of my lab, and that is making dynamic crystalline materials. So we've seen at this conference a number of really nice examples of crystals bending, jumping, and everything like that, and that's one of the things we're trying to do in my group. And we also do dynamic in situ X-ray diffraction to try and monitor these things using single crystal X-ray diffraction. And we're particularly interested in diaryl or dithienolethene based crystalline solids. So here's a nice example of shining the light, and you get this nice spinning crystal. The lifting ball trick here with light. So these are all single crystals that are doing interesting mechanical things. This is a relatively recent example where they make a metal organic framework, and they can crush it up, shine the light, everything dissolves, shine the light back, and the crystal, the metal organic framework actually reforms itself. So some interesting examples. The basic chemistry here, so these are, it's a, oh, I forgot about my laser pointer here. We've got a suitably oriented hexatriene moiety that when you shine light on it, it cyclizes, forms a new carbon-carbon bond, and this is often accompanied by strong color changes, electronic structure changes, and so on and so forth. And when you shine light of another suitable wavelength, this will ideally ring open, and thus you have a nice reversible, often bistable photochemical reaction in the lattice. What we're truly interested in is ultimately trying to do ultra-fast time-resolved X-ray diffraction and spectroscopy to see how the local chemical environment of the crystalline phase impacts the reactions, the photochemical reactions on ultra-fast timescales. And so to do that, what we want are crystals that contain these photoactive chromophores and ultimately through crystal engineering, hopefully allow us to do nice systematic comparisons. So one of the first chromophores that we worked with, one chromophore this wasn't the first, but one of our more recent ones was this diphenyl compound. And we liked it because, so Trav came up with this molecule, we liked it because we had this nice connectivity, strain relief, water stability, and potentially some interesting photophysics, and a very scalable synthesis. So Trav got to work and started crystallizing this thing, and this molecule, absolutely no problem crystallizing. Crystal structure after crystal structure, co-crystals, coordination polymers, MOFs, you name it, tons and tons and tons of structures. There was just sort of one problem, and that is that almost none of these crystal structures are actually photoactive. In fact, for whatever as I'll talk about, this molecule does not like to crystallize in the photoactive geometry. So there's a few different geometries here for these diarylethenes. Oh, come on. Well, okay, here we go. So we've got the anti-parallel, there's basically 4 conformers, 2 anti-parallel and parallel, which are related to the orientation of the methyl groups of the thiophene, and only one of the anti-parallel conformers, AP1, this thing. Okay, well, AP1 is photoactive, the rest are not. And so when we did some, admittedly somewhat low-level elementary calculations here, but we basically were looking at the rotational potential energy surface of these molecules, and it turns out that the rotamer of interest is low in energy. However, in 13 of the 19 structures that we observed, we actually observed the highest energy conformer in the lattice. And so, we decided that, we have to really take a look at how are you going to rationally design these sorts of materials when you make a molecule and it winds up being photoinactive. And so, we're intending to mine the CSD, and so I'll skip through this a little bit about the scalar-based parametrization and just say that, like, look, we either need to figure out how to control this conformational flexibility, so we're hoping to do this through some advanced computational studies, or just eliminating the flexibility altogether. And so that's the idea in this, is to instead of starting with the ring open isomer, we will start with the ring closed isomer, which is a bit of a pain for the synthesis, but it's what we're doing. So this is Dan Patel. He's now an associate professor at Penn State Hazleton, and he made some really nice molecules, and these are these naphthoquinone diarylethenes. And the nice thing about these is they can be actually chemically ring closed, so we can make these in pretty high yield. And this is one of the first crystal structures we got of this compound. Very, very nice halogen bonded crystals, and it turns out when you shine the light, it's a little tough to see, but these actually crystals start expanding and ultimately slice themselves up like bread. And when you look at the crystal structure, you can see this is most likely a consequence of the ring opening reaction. Again, you've got very, very nice halogen bonded 2D sheets, and this ring opening is likely basically popping these sheets apart. So we feel like we're making some really nice progress now on actually having some photoactive crystalline materials. I have I have another example I was wanting to show, but I also want to try and stick to time. So I'll just say we have some more really nice co-crystals coming up. These, in fact, are highly reactive to X-rays, which we think is really, really interesting. And in fact, we're now in the process of a collaboration of actually getting the ultrafast transient absorption data started so that we can truly understand the fundamental photochemistry that's occurring in these systems on the ultrafast time scale. And so that's a collaborator, Jeff Rack, up there with his student Rajani. And with that, I will just wrap up and say thank you for your time and attention, and again, the invitation to be here, and I'd be happy to take any questions.
Thank you, Jason, for a great talk. Do we have any questions? I can start with one as well. In terms of, you said you found the highest energy conformer when you were crystallizing them. Do you reckon the crystallization method actually has anything to do with trapping those sort of things? So if you tried like a high throughput thing, do you reckon you could?
Yeah, we haven't tried anything specifically like that. So this is where we're hopefully starting up a collaboration with some computational chemists to really. I show 4 rotamers, but if you actually do really high-level calculations, that's a very complex space, and so there's likely a lot more rotamers. And it's also, these are gas phase calculations, so they may not, really accurately reflect what's lowest in energy. But at the same time, crystal packing forces can easily overcome the couple kcal per mole difference between these conformers. So, yeah.
Delia?
Hi. With your salts that vape, what's in the vapor?
What's what?
In the vapor, Is it now nicotine and the co-former, or?
Yeah, so in terms of exactly the nature of the particle, we don't know that, and that's one of the things that we're again probably going to be starting up a collaboration to actually look at sort of what the speciation looks like in the vapor. But the vapor doesn't contain just A or B. It actually contains both. So it's nicotine and the salt former, and in fact these vapors will condense and recrystallize. So you have that nice crystallization in your lungs, but they do recrystallize, and so sometimes we've actually seen we've gotten a different polymorph from the crystals that are grown by the vapor, but both components definitely go into the gas phase.
That's great chemistry, Jason. Congrats. So I was wondering, I'll ask you a question and then I'll make a comment.
Sure.
In the case of the closed diagonal ethynes, do you find the photo opening reaction to be unusually fast or efficient?
Well, when you say fast, did you say fast?
Fast.
Yeah. When you say, so there's the two things, right? There's the conversion of the bulk, right? And then there's the ultra fast time scale. And so we're sort of looking at both. It was up there briefly, but Trav's, unfortunate project, which is also didn't help it happen during COVID, was sort of the synthesis of photo-inactive photo switches. And so we've actually been producing a huge amount of photo-inactive materials. So we haven't had a chance to really directly compare rates and speeds and things like that.
Okay, so the comment is because we're looking at quantum chain reactions in crystals, and we think that some diagonal ethynes are going to be really good candidates, especially if you can initiate them through electron transfer. And yours seem to be, good donor receptor kind of, elements that could play a role there. So the timescale that I was referring to is the macroscopic observable timescale.
Yeah. We'll have to, I mean, it's clear, it's one of the things we're now studying right now is trying to get at some of these rates, but these rates are also a little bit tricky to get at. I mean, making any sort of quantum yield measurements on solids is hard. Yeah, so, but Jeff's good, and, hopefully we'll have some more information soon on that. Yeah.
Thanks.
Yeah.
Yeah, so I've got a question. So back to linking to Delia's question. So you've got the volatiles in the gas phase, and do you think that there's an opportunity to have some selective sorbent that could extract the non-nicotine volatiles in the device, perhaps some membrane or something like that that could remove it so you get a more pure substance, or is there an interplay with the other components that are necessary so that you don't get a too high a dose?
Yeah, so it's an interesting question. So one reason that salts are sometimes also, people like these things, is it can change the flavor, I guess. So, yeah, full disclosure, I haven't, tried any of my own stash or anything like that, so I can't speak directly to what these things would taste like, nor have I sampled pure nicotine. But supposedly, nicotine is sort of a very off-putting, the freebase has an off-putting flavor. So in fact, the salts can actually help, I guess, make it taste better. No. They can also help it taste better. So I don't know that there would be a huge incentive to try and just get pure nicotine into the gas phase. But you could also just take, some of these things and, the oils and have it go in.
Well, we can thank Jason again for a great talk.
All right, thank you.
And that's now the end of the session, so thank you again to all the speakers, and thank you for staying on time so we can get to lunch. Yeah, thanks.
Well, that's, I tried to throw some fun in there for you. We've had a couple companies, so not a lot. So, but I think we actually have, I don't know what standards, but we have Yeah. Oh no, yeah. There's a right there. Yeah. But that's, you know, it's going to be interesting to see what happens in this space because the NBA just banned jewels in the United States. So jewel products are off shelf. And it's even a little bit more interesting because this paper that shows cigarettes, they tested several devices, including jewels. And it turns out that jewels actually have no emissions, whereas these other ones, like, so you've probably seen vaping. I mean, right? There was that one kid who has this sort of cigarette-sized box and has a little cap on it. Those are the things that people can change the settings, turn it up, and those are the things that really do make things apparently. Again, I have personal measure, but they definitely make benzene in some settings are really a lot. So there's two things. One, low-end vaping to use these salts in traditional vaping solutions and just at a minimum get rid of the benzoic acid so that, you know, there's probably, again, the Juul device that uses benzoic acid, they don't produce benzene, but again, the Juul device might be, it's so heavily configured, right? I'm using one button, and that's it. Right. They control all the settings. Again, the benzoic acid is probably right in those devices, but it's just other devices random settings. They may also buy cheaper materials, different oils that they use. And for cheap oils, trace amounts of metals, right? They actually find mercury, arsenic, and those metals can also catalyze the decarboxylation rate, which is making more benzene. And so, so if I was going to vape, like I would, if I was going to vape, sure, I would actually choose like a Juul, right? Because it's probably one of the safest devices out there, which that's why I say it's sort of bittersweet news for Juul that they got involved. Because honestly, I really it probably took a relatively safe device product off the market. But apparently well, I was just talking to Mohammed a bunch at the terrace about this because he's all the time. Oh yeah. He's like, and that's why I didn't remember some of the details. I said, okay, Mohammed, I'm going to go back to my writing, I'm going to double check this paper and get back to you. And that's where I was like, look, actually, Mohammed, the rules are actually the same. It's only other ones that you really have to be careful with. And so that's why I said, in fact, you guys did this. I think it's bittersweet news to say that I'm on the market. But he was saying, because it was funny, right after my talk, so here you go. On the day I was speaking, Biden had done like a nicotine reduction in cigarettes. And then, like the next day was when Juul got banned, and my student was texting me, and Mohammed was like, Mohammed was telling me that one of the big things that actually got banned. So 30 hours? It's the fact that somebody did some sort of a survey, and it turns out that 80% of Juul users are under 18. Yeah. So it's now you're like, oh, that's interesting. So it's possible that I believe Juul can like appeal this and come back and stuff. Which given the money involved is probably exactly what will happen. Yeah. But again, for the time being, potentially a safe thing can go on the market. And what's for sale now, right? It's all these smaller companies making as cheap things as possible with God knows what is in these liquids, and so it's yeah. Yeah. No, when Devin started digging up the literature on all this, I was like, this is absolutely fascinating. And again, I think a lot of people wish nicotine didn't exist and people wouldn't do it, but people are also adults and yeah. Yeah, we'll take it. Just want to say thank you. Oh, no, we already got it. Yeah, we got it before the start. I know it was like driving off or something to say. Oh, thanks. Oh, we're not the... Yeah, there should be an I was thinking I think we've got the lunch as well, but it should be fine. It's the HDMI. Yeah. So how long did you say yes or no? It's not actually that long. I think we ended up getting them like a couple of days. It was good then, but it was like, because I received like a message from Felix like 2:30 a.m. like, hey Christian, see you later. We don't need to align correctly, it's not okay. Yeah, I don't know how. Why did I just get here? So we went. And then we went and saw. Sure, of course, if you have drinks, you need something. Yeah. Like they basically just covered them in like Nutella. So
se, brate, ime tvoje. Aj, donesi mu ovo ime, aj. Neknal ta puknal ti veke, nema litvej. Ovaj, nemam. Olka evo gazom. Ovaj, nemam. Što pojka od mene? Samo ti gado da se ja nema da nude. Što nema da. Misliš na vas? Koliko je sad od dve? кажа. Мало. Трести на суви. Знаеш каков е? Еј, собите се, значи, да ти е неугодно, да ти е незгодно, че е убаво да легнеш и да седнеш. Средено, фоајето, шанкот со другите маси. Ти кажи двата стратегии, рела. Свака го возбира, лајна, ови. Овие. Избираме лајна. Здраци! Тај онај е мъжки со научарчина. Онај мъжки со научарини. Але тој ми е генерација. Генерација ти е тој. Генерација си ти, бе. 73-та. Шо? 69-та. Јас не мислев 72-та, 73-та. Убојто, бе. Убојто. Evo, pa kako je čovjek gospod.
za na kraj toga. Po internetu kliknime na kraj.
Hello, good afternoon. Hey, Tomče, yes. Sorry?
Did you hear us good?
Yes, I can hear you. Yes.
Can you see good?
I can see very well, thank you.
Okay, thank you very much. You want something to try?
Yes, I will try my presentation so that I can hear the screen. Is that all right?
Yes, 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 it's correct.
So it looks like everything is okay, doesn't it? You can see my slides fine?
Yes, 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 you can see your slides in the full version. In full screen.
Excellent, good.
Okay. If you have some videos on your presentation, try to put them and try how to work.
No, I don't have any videos. No.
Okay.
So I think everything looks fine. Everything is all set.
It's very beautiful.
So what time do we begin? But does the session begin earlier?
We have just a second, sir.
Yes. I'm very sorry to but thank you very much for the opportunity to present on my way. I really appreciate it. So to listen to T calls, do I stay on here or can I leave here?
You can see everything online now. It's on YouTube. You have the links for.
Yes, I've been watching some of your lectures, so that's.
Okay, I was just told that also you can watch it on Zoom, whichever you prefer.
Yeah, maybe I'll see you on Zoom for this one and then I'll watch others.
Okay, sounds good. Let us try with the call because she's online.
So just stop the presentation.
Yeah.
Can you hear us?
Did you hear us?
си ја правиме плюс. Не, преведувачите што се во сала, му праќаме сега после на зумот. И за секој јазик припустав топ да ставиш, како преведувач. И све е тоа табли и комплицирано. Да. Не, слушаме, јас слушаме ние, па не слушате. Не. Каде?
Водите се поставени. Може за подпис ќе дојдам пред да почнете.
Да се уклучи пак конче.
Hello, can you hear me now?
Yes, perfect. We can
But
see you.
wait. Now it's a bit of a... do you still hear me?
Yes, it's very clear. We can hear you.
Marvelous. Now it's on my headphone. Yeah,
Yes.
that's exactly what I wanted. Because else it's more of a, let's say, an echo, which is not good.
Would you can test your presentation as well?
Sure.
Well, I was going to say, do you mind if we could stand up there together and I'll just like hold, and you can, yeah. But I was like, dude, I don't trust it. I don't trust it.
I share it in a moment. I so here presentation is, what is it?
Yeah.
Here. Okay, because I always share it in the very last moment, because then I know which screen I can have to share.
You could probably test it because you're at the break, but we want to test it first time.
Okay. So
Probably
now,
yeah.
yes, this goes down here, and now I can share. In a second, where is it? Here it is. No. I will be quicker later. So now this one, okay, and now share the screen. I have to share this screen, and I'm going to share it. Okay, you see my screen?
We see your background.
Yeah, it should be a blue screen with
Yes.
some items on it.
Correct.
Yeah, and now,
Perfect. Yeah, we can see.
and now I just see if I can click through it.
It's going well.
Yeah.
Perfect. I think you're all set with it.
Okay, fine.
So you can stay online if you want during the introduction and can't stop.
Okay, perfect. Welcome to the last session of the conference, which will be co-chaired with me and Jason. I can promise you that I will do my best to keep him from making puns. I'm not sure how successful I will be, but I will do my best. So today the topic is crystals and methods, but we will make it crystals, methods, and community. I will talk a little bit about the methods part, and Jason will talk about community. It is nice that the last session is about methods, because this conference, as you know, started with methods, with the workshop that we organized for the students, because of course the students are more important than PIs, that much is clear. And now we are finishing the conference on a very high note. Of course, before the plenaries, we are finishing with excellent talks that would be on methods that we all use. So the first talk will be from Kenneth Harris, and he will talk about structure determination of organic materials from powder diffraction data and opportunities for multi-technique synergy. Then the next talk is going to be from Ute Koop, and she will talk about electron diffraction, and of course she will talk about crystal structure solution and the analysis of sensitive organic molecules. After that, we'll have a break, and and Jason, I don't have the where the other talks.
Isn't it on the?
Okay, oh, yeah. there we go. And then Adam Milichuk will talk about in situ applications of powder X-ray diffraction, followed by Susanna Vart from CCDC that will talk about community and in the world of crystallography. Then we have Christian Koop that will continue the talk on electron diffraction, and we have one addition to the program. Christian Jaln will talk about structure determination of nano-sized crystalloids using electron diffraction, and that will be at 5 o'clock, so please hang around and stay for his talk as well. Before we start, I just want to say a couple of words about these methods. And as a solid-state community, we do use a lot of methods. And we cannot cover all of them in this 5 minutes presentation for the session. But quite interestingly, the two methods that we will talk about right now are powder X-ray diffraction and electron diffraction. To me, and this is my personal opinion, this is a very nice coincidence. Both of those methods are quote-unquote unconventional methods for structure determination. We all know that single crystal diffraction is the most commonly used method to solve crystal structures. These two methods really bring a lot of information and help whenever single crystals are not available. And I have to say that happens more often than not. The fact that a lot of single crystal structures have been solved and they're reported are because single crystal diffraction is more straightforward. I do think that there are many small, crystal structures of molecules that do not crystallize as single crystals, and they're just put under the rock and not reported just because they're a little bit more difficult to be solved. I do believe that we as a community should do better in advancing these alternative methods for crystal structure solution to a point that they will not be alternative anymore, but they will be as applicable as single crystal X-ray diffraction. It is another interesting parallel between electron diffraction and powder X-ray diffraction is that they are very complementary and they do work quite nicely in pair. I don't think that we should approach the development of methods with either we will use electron diffraction or we'll use powder diffraction, but we should do it both. I can name many advantages of each method. I myself will work with powder diffraction, and I do plan to continue working on electron diffraction in the future as well, because they are complementary. When it comes to powder, I just want to say one thing. If I ask you how many of you have powder diffractometers, I'm sure that 99% of you will raise your hands. However, there are not that many people in our community that solve crystal structures from powder diffraction data. I do welcome the developments of electron diffraction. It's an amazing technique and it will provide a lot of information. However, we should not forget powder diffraction, because electron diffraction in the next decades, it will not be part of all of our laboratories, but we all have powder diffraction at home and we can solve many crystal structures. So I do think that as a community, we should do better in starting to really apply this method more common than just calling it alternative. Okay, and of course, for the remaining of the session, the speakers will present excellent research done with both of those methods. The next 10 minutes I will give to Jason, who will talk about community in our community.
Thank you. All right. Yes, it's me again. Hello. Hope everyone had a nice lunch. Here we go. So I'll talk for a few minutes about crystals in the community. And actually, that was, I believe, the original title of this session. And unfortunately, there were a few cancellations. And and we brought in. Obviously, methods is very important, and so the composition of the session got changed up a little bit. But I do want to take a few minutes to talk about the crystal community. And so the theme here, the rebuilding bridges in the solid state research community. Well, you need a picture of a bridge, and this is a little time for trivia. Does anyone know what this bridge is? Yeah. Look, I promised you folks fun, and I hope you're enjoying this, because I am, and I know Panche is. Does anyone know what this bridge is, besides Panche? Do you know it? Oh, okay. So it turns out this bridge is a new road that's being constructed on the way to Ohrid, and I learned a great deal about this from my driver on the 3-hour ride from Skopje to Ohrid, and apparently this thing is they're now 8 years in and several $1 million over budget, and they got the project's being extended and going even more over budget. So he had a lot to say about it, and when it came to building bridges, they're clearly doing it in Ohrid, but maybe not as fast as the folks would like, or as cheaply. Anyway, in building bridges, who are we starting with? Well, us, right? This is the group photo that was taken just a couple days ago, and this is us as a community of solid-state researchers, organic solid-state researchers. And we need to either build or rebuild bridges. And so some of the folks, communities, people that we need to think about are bridges between ourselves. And I'll be honest, I think that generally speaking, we do a good job, because we have conferences like this where we come, we see each other's science, we talk, we network, and things like that. So, I think there are a lot, obviously we can build more bridges, but I think bridges to other researchers is something that, as research, we generally do a pretty good job of. One that's maybe a little trickier is bridges to the public, and that is engaging with the public and sharing with the public our science and why our science is important. At the end of the day, remember that certainly in the U.S., and I'm willing to bet in most countries, right, people elect their representatives, and their representatives ultimately determine funding and whatever. Ideally, whatever people think is important to fund, that's going to be what gets funded. And so if people don't think science is important, if people don't think science is real, that science matters, that's going to be reflected in what politicians think about science and science funding. And to anyone here who's trying to do science, you know that it takes money to do it. And this leads me to the third group of people that I think, as a community, we should strongly think about, a group with whom we should engage. And that is, politicians, decisions, policymakers. I'm actually currently chair of the board of directors of a nonprofit, the Society for Science at User Research Facilities. You know, we're an organization that directly advocates with policymakers to try and, you know, basically show policymakers the importance of national facilities. In this case, we're an American organization, so we advocate for U.S. User facilities. But that sort of stuff is really important to do. Again, if you don't show up in policymakers' offices and say, hey, these are the, you know, scientific breakthroughs that mattered, and they're being enabled because you funded X, Y, and Z, they may not appreciate that. And when it comes time to start spending all of those, all that various currency, again, if they don't think science matters, it's, you know, it's going to, that level of interest is going to be reflected in budgets. Now, in terms of engaging with the public, I was here a couple years ago and was part of this session where I talked about the US crystal growing competition. So this is my little piece that I do to try and foster an interest in science among kids in grades K through 12. And so if you weren't here, not familiar with it, this is, you know, as it sounds, a crystal growing competition for kids, and it involves kids, teachers, parents, lots of people, and they get a chance to grow a crystal and look at a crystal, see a crystal grow. And, you know, while, you know, I'm certainly, you know, don't look through the world with rose-colored glasses and think I'm trying to, you know, that absolutely anyone who participates in this is going to become a crystallographer. My hope is that they'll take an interest in science and, you know, maybe go into a STEM field or just even have a deeper appreciation for science. And I'll just quickly add here that, you know, I'm not the only one doing this. In fact, there are a number of these crystal growing competitions all around the world. So here are a few I've put on display. So Singapore runs really a pretty crazy crystal growing challenge. Some of the crystals that they grow and the quality of the crystals is amazing. But you can see here, Australia has a really nice crystal growing competition, Canada, and then the IUCR. The IUCR one was a little bit weird, but it wasn't actually like, well, anyway, I won't go too into it. But anyway, this is a way to engage with the public. And what I'll leave you with is, you know, this sort of figure. Again, I think we do a really good job on, you know, the research communication bit, but my laser pointer was pretty messed up last time. Let's try this. Here we go. Again, I think we do a pretty good job of research communication within our community and within each other, but it's these parts of the diagram here that I really think are important, and especially if we want to, I mean, we'll hear from Len later about visionary, you know, sort of science from, we'll hear from Len about, you know, visionary aspects of our scientific community. But again, I think that, you know, folks, probably we don't want you to lose sight of this sort of thing because it really is critical. It's going to be critical for training new scientists, for having new scientists come up the, you know, come up the ladder. And like I said, it's also really, really critical for science funding. And funding is what it takes to make sure that we can all do what it is that we love to do. And so with that, and so that's what I was going to say is if you're doing this stuff, if you are, you know, engaging with the public or engaging with folks or engaging with policymakers, when the next ICOS comes around, you know, talk to the organizers and consider presenting about what you're doing because, again, you might be doing some really, really fabulous outreach or engagement with policymakers, and if folks don't hear about it, they don't know about it, and you may be able to teach people some tricks that'll really benefit this community as a whole. So anyway, with that, I think we'll go ahead and get started, and Tom can introduce the first speaker.
Okay, so the first speaker of the session will be online, and the talk will be given by Kenneth Harris from Cardiff University. On structured determination of organic materials from powder X-ray diffraction data, opportunities for multi-technique synergy. Ken, the floor is yours whenever we get a connection.
Ken, just a second. Huh?
While we're waiting for Ken, we arranged to have the nice din of rain for everyone. So just sit back and relax. We'll get started here in just a moment.
You can start now.
Okay, can you hear me okay?
Yes, sir, we can hear you well.
Yeah, that's great. So first of all, thank you very much, Tom, for the kind introduction, and both Jason and Tom for their interesting words at the beginning of this session. So first of all, I'd like to thank Tomče for the very kind invitation to give this lecture, and secondly, to thank him for allowing me the opportunity to present the lecture online when it became clear that I would be unable to travel at this time. However, I'm really sorry I'm not in Ohrid in person, especially as I hear has been another truly outstanding ICOS conference. So what I want to do during the lecture is to talk about how directory diffraction applied to structure determination of organic materials. And in particular, what I would like to do is to emphasize the advantages of introducing information from other methodologies to enhance the process of structure determination. So I'll begin with a general introduction to structure determination from powder diffraction data, and then I'll focus during the lecture on a variety of ways that information from other techniques can be utilized in different aspects of the structure determination process. Okay, well, I guess we all know that it's challenging to determine structures of organic materials from powder diffraction data compared to single crystal diffraction data, as Tom pointed out in his introduction. The reason, of course, is that in measuring a powder diffraction pattern, the three-dimensional diffraction data that you would get from single crystal is effectively compressed into one dimension. So we have intensity as a function of a single reciprocal space variable with diffraction angle 2 theta. And one consequence of this is that there's usually significant peak overlap in a powder diffraction pattern, which obscures information on the intensities of diffraction maxima and therefore makes the structure determination process much more difficult. But the problem is especially severe in the case of organic molecular materials, which typically have large unit cells and low symmetry, which means there's a very high density of peaks in the powder diffraction pattern, and therefore the peak overlap problem is consequently much more severe. But in spite of this, since around the 1990s, the opportunities to determine organic structures from powder diffraction data have advanced significantly, and I hope I'll convey some of that to you during this lecture. So before we proceed, let me give a very, very basic overview of the different stages involved in structure determination from powder diffraction data, because I'll refer to these later in the lecture. So first of all, we have unit cell determination, which is the analysis of the peak positions in the powder diffraction pattern to determine unit cell. This stage is often called indexing. We then move to structure solution. And at this point, we know the unit cell, but we have zero knowledge of the arrangement of atoms and molecules inside the unit cell. And the objective of structure solution is to get an approximately correct description of the positions of atoms and molecules within the unit cell. And once we have that good approximation to the structure, then it can be improved to a much higher quality by structure refining. And in the case of powder diffraction, that's nowadays virtually always carried out using the retail profile refinement technique. But going back to the 1990s, the big problem was the difficulty of structure solution of organic materials from powder diffraction data, and there was a lot of activity in developing new methodologies in that direction. And that led to the development of the direct space strategy for structure solution, which follows a very close analogy to global optimization methodologies, and is nowadays almost always the technique used in the case of solving organic molecular structures from powder diffraction data. So I'll refer to different aspects of direct space structure solution during the lecture, so let me give you a brief overview of the basis of this methodology. So as I said, when we start structure solution, we already know the unit cell, we probably know the space group as well. And one of the great things about studying organic materials is that simply by knowing the molecular geometry, by simply knowing the molecule we're dealing with, we already have quite a lot of structural information. So what we would do at the beginning of a direct space structure solution is simply generate trial structures at random by putting the molecules at random positions inside the symmetric unit. And we know what molecule they are, and I'll come on to that in a bit more detail later on. So we have this set of trial structures, and we can automatically calculate the powder diffraction pattern for each trial structure. And then what we can do is directly compare the quality of agreement between the calculated powder diffraction pattern for each trial structure and the experimental powder diffraction pattern using the appropriate figure of merit. And in our work, we use the powder profile R factor, RWP. And on the basis of this comparison, we can determine which trial structures give a better fit or a worse fit for the experimental powder diffraction data. And using various algorithms, we can use this information to generate an improved set of trial structures. And we simply keep going round this cycle, generating better and better trial structures until we find a trial structure that we think gives an adequately successful fit to the experimental powder diffraction data, and that will be our structure solution. Now, coming back to the concept of knowing molecular geometry in the case of organic materials, this is really, what I'm about to say is really critical in underlying the success of direct space structure solution, because there's already a huge amount of information known about geometries of organic, bond lengths, bond angles, geometries of rigid units like aromatic rings and so on. And we can actually make use of all of this information very directly to help the direct space structure solution calculation. So we assume reliable bond lengths, bond angles, and other aspects of molecular geometry for the molecule of interest. And let's take this as an example. And the information we need to find, assuming that we know the molecular geometry, is simply the position of the molecule in the unit cell, the orientation of the molecule relative to the unit cell axes, requiring 3 angular variables, and a number of variable torsion angles to define the molecular conformation. In this case, there is 3 variable torsion angles. So the only structural variables we actually have to find in the direct space calculation, in this example, there's only 9 variables. And let's contrast the situation where if we didn't assume anything about molecular geometry and we treated each atom independently, that would require 36 variables, a much, much more complex search in direct space. So this is really a key feature underlying the success of direct space structure solution. So the idea is to find a set of structural variables given the best agreement between experimental and calculated powder diffraction pattern, corresponding to the lowest value of the figure of merit, in our case, RWP. And that's equivalent to exploring a multidimensional hypersurface to find the lowest value of the R factor, and that's equivalent to global optimization. So in one dimension, this is a one-dimensional hypersurface, if you like, and the aim, so this is R factor as a function of a set of variables, and each trial structure would represent a different point along this axis. And what we're trying to do is to find the global minimum. The set of structural variables correspond to the minimum of R factor. And of course, we're not dealing with one-dimensional hypersurfaces in our work. We're typically dealing with 10, 20, 30, even 40-dimensional hypersurfaces. So we need sophisticated algorithms to allow us to find the global optimum. A variety of techniques have been used in the context of direct space structure solution. Our work is focused on genetic algorithms incorporated in our program Eaby for direct space structure solution. Okay, well, with that as a basis, and I'll come back to some of these concepts later on in the lecture. I just want to give you some examples to highlight some of the scope. All of these are taken from our own work over the years, to highlight the scope of these techniques, as well as to highlight some of the areas where it may be essential to use powder diffraction data for structure determination. Here's an example of a solid-state polymerization reaction. The starred materials are very beautiful single crystal, but it breaks up into fragments during the polymerization reaction, and this structured product phase has been determined directly from powder diffraction data. Here's another example of this novel tetrahalide anion that was produced again from a solid-state reaction. As we heard in Francisca Emerlin's lecture yesterday, powder diffraction has an important role in characterization of materials prepared by mechanochemical methods. Here's the first example we studied 20 years ago almost, of a three-component organic co-crystal prepared by solid-state grinding, and the structure determined from powder diffraction data. A metal-organic framework, again prepared by mechanochemical methods, solved by powder diffraction data. And these techniques have been applied a lot in the pharmaceutical industry. Here's one of our early examples with liposome propionate, a new polymorph of this drug material, shown there, cimetidine hydrochloride, and structure determination of small peptides. Here's a pentapeptide, have also been achieved successfully using direct space structure solutions. So I hope that gives you a flavour of the scope of the methods. So what I want to come on to the rest of the lecture is to focus on ways in which we can actually utilise information from other experimental and computational techniques to really enhance the capabilities of structure determination of organic materials from powder diffraction data, as well as to give us more certainty, perhaps, that we've actually found rigorously the correct structure at the end of the process. So I want to consider a number of different techniques. I'll focus especially on solid-state NMR spectroscopy, periodic DFT calculations, and at the end of the lecture, I'll discuss about the complementarity of electron diffraction and powder diffraction, as indeed Tom highlighted in his introduction. But basically, any technique that yields some type of independent information about the structural properties of the material of interest will be of great value to us in assisting the process of structure determination from powder diffraction. So let me begin even before we measure our powder diffraction data and assess the quality of the powder sample we have prepared, because there are two issues that really make structure determination from powder diffraction data very difficult, or perhaps even impossible. And one of these depends on the phase purity of the powder sample. If the powder sample contains an unknown purity phase, then almost certainly indexing unicellular determination from the powder diffraction data will fail. So it's very important, therefore, to have independent ways of determining whether the powder sample is phase pure or not, or if there are impurity phases, do we have no structure? So let me give an example of this. We were interested to determine the structure of diphenyl phosphine oxide, shown here, DPPO. Here's our powder X-ray diffraction data. Looks fine, but indexing was completely unsuccessful. We measured solid-state phosphorus NMR, and here's the spectrum. One major peak and two minor peaks. This one, we know from various aspects of the solid-state NMR measurement, is actually a liquid phase, deliquescent DPPO. This is in the region we'd expect for DPPO, and this peak here corresponds to diphenylphosphinic acid, which is an oxidation product of DPPO. So a minor decomposition product is present, but this is a crystalline material, and here's the calculated phosphorus 31 chemical shift for the known crystal structure. But because in this case it is a known structure, then we can proceed with the structure determination process, treating it as a two-phase system, one known phase, and we determined here the unknown phase, the DPQ. Here's the final refinement, and here's the final structure. But in many cases, you know, if the impurity is an unknown phase of unknown structure, then that really limits the possibility of carrying out successful structural determination. The second issue, to do with the quality of the sample, is preferred orientation. And if there's preferred orientation in the powder sample, if it's severe, then that almost certainly means structure solution will be unsuccessful. Preferred orientation, as I'm sure many of you know, means that there's a non-random distribution of crystallite orientations in the powder sample, and that means that some intensities are increased, some intensities are decreased, and the relative peak intensities in the experimental data are different from the true intrinsic diffraction intensities characteristic of the crystal structure. As I said, if preferred orientation is severe, it almost certainly means one will not be able to solve the structure from the data. So what I'd recommend is we should aim to record powder diffraction data that's free from preferred orientation by appropriate screening of the powder sample before carrying out the structural determination process. So how do we do that? So here's certainly one way of doing it, and that is to measure a two-dimensional powder diffraction pattern. We do this on a single crystal diffractometer with a CCD camera using the same capillary that we are going to use for our powder diffraction measurement on the powder diffractometer. So we do this screening. We measure the Debye-Scherrer rings as shown there. The CCD detector is perpendicular to the instant X-ray beam as shown here. But the point is the following. If there is significant preferred orientation, then the intensity around the Debye-Scherrer rings is non-uniform, as shown on the left-hand side. Whereas if there's no preferred orientation, then if you look around each of the Debye-Scherrer rings, the intensity is completely uniform. And that's the situation we're aiming for. So if you've got a powder sample exhibiting the behavior on the left-hand side, I'd strongly recommend to go and find different ways of preparing the powder sample until you achieve this situation before progressing with structural determination. Here's an example. Tetracane hydrochloride hemihydrate. We encountered the situation shown on that left-hand side of the previous slide, and we prepared the sample to produce preferred orientation by mixing the powder with an amorphous material. And that significantly helped the situation and allowed us to successfully determine the structure in that case. Okay, so second in this section, I want to think about ways in which we can utilize other techniques to help us to set up the correct model for using in direct space structure solution. So we're assuming we've carried out successful indexing, and we're now about to embark on the structure solution process. So as I said earlier, we will generally know the organic molecule of interest, but we do not necessarily know the tautomeric form of the molecule in the crystal structure. And clearly this could have an important bearing on the correctness of the structure that is determined. I want to give two examples in regard to this aspect. First of all, polymorphs of meta-aminobenzoic acid. There are actually 5 known polymorphs. Form 2 was known, the structure is known in Form 2 before we started this work from single crystal diffraction. So 5 different forms. But what we need to recognize is that meta-aminobenzoic acid can exist either as the non-zwittrine with the carboxylic acid and the amine group as shown here, or as its zwitterionic form with an ammonium group and a carboxylate group shown there. So one way we can investigate the tautomeric form in each polymorph is to recognize that the 1s electron binding energies of nitrogen are very different in an amine and an ammonium group. And therefore, nitrogen 1s X-ray photoelectron spectroscopy can very, very clearly distinguish which polymorphs are the zwitterine and which polymorphs contain the non-zwitterine. the 1s electron binding energy is higher in case of the zwitterionic forms, and that corresponds to forms 1, 3, and 4 of this particular material. Solid-state NMR as well can be very instructive in this regard, and also for the 5 polymorphs of nicotine benzoic acid, a peak in this region, you see, corresponds to the non-zwitterionic forms. It corresponds to that particular carbon environment, and a peak shown with the green dot in this region here is very characteristic of the zwitterine, corresponding to that carbon environment there. So if we zoom in on this region of the spectrum, there's information that clearly distinguishes whether it's the zwitterine or the non-zwitterine in the particular polymorph of interest. The other regions are much less informative, like here it's hard to tell, here it's also pretty hard to tell which form we have. But that's an example of where solid-state NMR can be really informative, as I will also illustrate in this next example of structure determination of aloxazine from powder diffraction data. So aloxazine is the molecule shown here. There's actually 2 tautomeric forms, differing only in the position of this hydrogen atom, whether it's attached to this nitrogen or to this nitrogen, and this tautomer is called isoaloxazine. So we carried out the structure determination of aloxazine, got a nice fit to the powder diffraction data with a very satisfactory hydrogen bond arrangement, so everything looks perfectly correct using the aloxazine tautomer. But doing the same thing with the isoaloxazine tautomer gives an almost identical fit to the powder diffraction. Not quite as good, but really, really very similar, and also very satisfactory structure. And the only difference I'd like to highlight in this slide is the position of that hydrogen that I highlighted. So effectively, if that hydrogen jumped along the hydrogen bond, you would enter a converb between aloxazine and isoaloxazine, as shown here. So although there's a slightly better fit for the aloxazine tautomer in retail refinement, is not enough to give us confidence that we have definitely assigned this correctly. So this is a case where powder diffraction alone is insufficient to distinguish these two structures. So let's look at other evidence. And here's solid-state nitrogen-15 NMR. And under the conditions of our measurement, we only see peaks for nitrogen-15 environments directly bonded to protons. And there are 2 such environments. The peak separation here is 32.75 ppm. And what we can do is for each of these 2 crystal structures shown here, we can calculate using DFT methods reliable solid-state NMR data. And we can calculate what the NMR shift would be for nitrogen-15 in these 2 structures. And for the aloxazine structure, the separation between the 2 peaks is 34.75 ppm, pretty close to the experimental value. But for the isoaloxazine structure, it's really very different. So this is very convincing evidence that indeed the aloxazine structure is the correct one. And indeed, from DFT calculations, the relative energy is a lot lower for the aloxazine structure. And again, that gives us further support to conclude that the aloxazine tautomer is the one that actually exists in the solid material. Another very important thing in setting up direct space structure solution calculations is to know reliably the number of independent molecules in the asymmetric unit, which can be important in space group assignment. And this can be obtained very directly and independently of the powder diffraction data using solid-state NMR. I want to give just 2 examples. One-to-one co-crystal of benzoic acid and pentafluorobenzoic acid, the 2 molecules shown here. And here's a solid-state carbon NMR spectrum of the co-crystal. I'm zooming in the region for the carboxylic acid groups. This is for the pentafluorobenzoic acid. We see 2 peaks in 1-to-1 ratio. And this is for the benzoic acid. Again, 2 peaks in 1-to-1 ratio. And this tells us very definitively the asymmetric unit must contain 2 molecules of benzoic acid and 2 molecules of pentafluorobenzoic acid. And here's the final structure, which contains that feature, obviously. Another example, here's this highly branched molecule shown here. And again, the question is, how many molecules in the asymmetric unit? Here's solid-state carbon NMR spectrum at the bottom. I want to focus on the region around 100 ppm, which corresponds to the aromatic CH environments, indicated by these red dots here. So there are 12 such environments in the molecule, and if we had one molecule in the asymmetric unit, then we'd expect a maximum of 12 peaks, but certainly a lot of peaks corresponding to that particular environment. But in the actual spectrum, as you can see, we see only 6 peaks. And that leads us to the conclusion that actually the asymmetric unit is only half the molecule, containing 6 of these aromatic CH environments. And given the space group of interest, that would correspond to the molecule residing on a twofold rotation axis, and the asymmetric unit being only half the molecule. And all of this is really, really valuable information before we even begin our direct space structure solution calculations. Here's the final structure in that case, and again we can see the asymmetric unit shown here, with actually very different conformational properties for the two independent branches in this molecule. Okay, so let's assume we've run our direct space calculation. What can we do in terms of utilizing information at subsequent stages of the calculation? So I want to now focus on, I think, 4 examples of how we use other techniques and information from other techniques, either to directly help us during structure determination or to help with the final validation of the final structure obtained in the root level refinement. So one aspect that many people in the field are now taking advantage of is the ready accessibility of periodic DFT calculations. And we're using this in various different ways within the procedure for structure determination. So coming back to the overall scheme, unit cell determination structure solution, it's very common to apply DFT geometry optimization after structure solution to improve the quality of the model before entering structure refinement. And again, during structure refinement, it can be very advantageous to kind of have an interaction between the refinement process and geometry optimization, for example, to update the restraints that are typically used in the refelt refinement as the quality of the model gets better and better. And then once we feel we've had a satisfactory refelt refinement, again, DFT geometry optimization can be used as a robust test that the structure corresponds to an NG minimum, which is a clearly a requirement for any experimentally observable crystal structure. So let me give you one quick example of this. Structure determination of one-to-one co-crystals of ibuprofen and L-proline. 2 co-crystals, one in a non-solvate phase, one a quarter hydrate phase. Now these were fairly complicated structure solution problems. There were 2 molecules of each type in the asymmetric unit, a total of 33 structural variables for the non-solvate, 34 structural variables for the quarter hydrate. And here's the final structure of the non-solvate co-crystal. And I hope you agree this was a satisfactory refelt refinement in terms of quality of fit, judged best by looking at the difference plot at the bottom. So this is acceptable to us. Here's the structure shown on the right-hand side. And then as validation, we subject this structure to DFT geometry optimization, and the 2 structures are overlaid on the right-hand side, and there's very, very little atomic movement. And that confirms to us that the structure from the refelt refinement is acceptably close to an NG minimum to consider it as being correct and finalized. And likewise for the quarter hydrate, again, this fit was acceptable to us, and again, only minimal atomic movement upon DFT geometry optimization. What I want to come to now is exploiting solid-state NMR data in the structure validation process. And again, this relies on periodic DFT calculations to deliver information on NMR data from a crystal structure. And this really relies on developments in DFT methodology in recent years in the capability of calculating accurate and reliable solid-state NMR data for crystal structures, and especially the CASTET program is particularly reliable in this regard. And so this opened up the opportunity to develop a protocol where we can use both powder X-ray diffraction data and solid-state NMR data in determining crystal structures for powder samples. So the idea is as follows. Here's a powder sample, and in addition to recording the experimental powder X-ray diffraction data, we can record experimental solid-state NMR data. That can take many different forms: one-dimensional data for different nuclei, two-dimensional data of different types, two-dimensional NMR spectroscopy. But the point is we can then determine the structure from powder diffraction data as I described and subject to all the rigorous checks and so on. Let's assume we've determined the structure, given the good Rietveld refinement. But what we can now do using the DFT methods is to compute solid-state NMR spectral data. And that allows us then to compare the NMR data for the crystal structure we've determined here directly to experimental solid-state NMR data. So this crystal structure we've determined is being assessed both against the powder X-ray diffraction data in the Rietveld refinement, and now it's being validated against solid-state NMR data. So let me give you an example of this approach: co-crystal of indomethacin and nicotinamide. And the final Rietveld refinement was acceptable. Actually, it's a two-phase refinement here. There's an impurity of the pure phase of indomethacin present in the powder. But the co-crystal looks very much acceptable, sensible hydrogen bonding and so on. DFT geometry optimization was fine. But let's now calculate the solid-state NMR data. Here are the carbon-13 chemical shifts. On this axis, the calculated, and on this axis, the experimental, with a very acceptable correlation between the experimental and calculated values. And here's the proton chemical shifts, again, experimental and calculated. There were some known anomalies in CASTET at that time. That problem has been addressed. But in general, apart from those anomalies, then there's an acceptable fit. And even more robust is using two-dimensional NMR data. And here we're looking at the proton-carbon correlation spectrum, where on one axis is the proton spectrum, on the other axis the carbon NMR spectrum, and the peaks that we see in the two-dimensional spectrum correlate carbons and protons directly bonded to each other in CH2 and CH3 groups. And in black is the experimental spectrum, and in red is the calculated data for the crystal structure we've determined. And I hope you agree that this looks again like an acceptable agreement, and this is really very robust in terms of providing additional strong validation that we get a really good fit to the NMR data as well as the powder diffraction data. I want to now look at ways in which we could incorporate information from solid-state NMR directly within the structure solution calculation, and not only for validation, but actually to help us, assist us during the structure solution process. And here I want to focus on this derivative of deoxyguanosine, shown here. So a relatively complex structural problem, especially many torsion angle variables. But the point here was our collaborator Stephen Brown from Warwick University had already carried out a very detailed batch of 15 NMR studies in this material, and on the basis of J couplings between nitrogen 15s, he had deduced that nitrogen 7 and nitrogen 10, shown here, must be involved in an intermolecular NHN hydrogen bond. So with this information, it means that any structure solution that we obtain, or any trial structure in the direct space structure solution that doesn't contain this feature cannot be the correct structure. And that's really a strong basis for allowing us to focus in on what really was the correct structure. Here's the final Rietveld refinement, here's the final structure. Actually gives a novel hydrogen bonding arrangement that's not been seen before for deoxyguanosine derivatives. But here we can see that particular hydrogen bond between N7 and N10 as shown there. And here's the correlation of the carbon chemical shifts and the actually 15 chemical shifts calculated for the final structure compared to the experimental. And again, these very good correlations give us strong support that the structure is indeed correct. Okay, well, let me now come on to the final part of my talk, combining hydroelectric diffraction data and three-dimensional electron diffraction data. As indeed Tom said in his introduction, these two techniques are very complementary to each other, and we're fortunate that in the next lecture, we have the pioneer of three-dimensional electron diffraction, Eaby Carroll, to give us a lecture on her research as well. So we've been, in the last year or so, we've begun to utilize electron diffraction data in combination with structure determination from periodic diffraction data. So what I want to show you is this example, structure determination of the new polymorph of L-times, prepared by crystallization from the gas phase following sublimation. We call this the beta polymorph. There's already one previously known polymorph from single crystal diffraction. But the point here was that we simply could not index the periodic diffraction data. We later discovered that's because there was an impurity in the periodic sample, but we turned to electron diffraction to carry out unicellular determination and space group assignment. And the point is, as you know, electron diffraction is basically a crystal diffraction measurement on a microcrystal within the period. And if you can record sufficiently good quality data, then indexing unicellular determination is much, much more straightforward than it ever will be using periodic diffraction data. And so this opened the door to allow us to determine structure. So in the knowledge of the unit cell from electron diffraction, we actually carried out structure solution independently from the periodic diffraction data and the electron diffraction data using our eager direct space structure solution program. And both methods gave essentially the same structure. Here's a comparison of the two structure solutions, one from the electron diffraction data and one from the periodic diffraction data. And we carried out structure refinement using periodic diffraction data. Again, given the contrast and differences between the techniques, clearly with X-ray diffraction data we can carry out kinematical refinement, whereas dynamic scattering may have to be taken into account to get an accurate refinement from electron diffraction data. Here's our final periodic diffraction data, again an acceptable fit through the data, and here's the final structure, which looks acceptable from all structural criteria, very sensible hydrogen bonding, and so on. And final validation, you see solid carbon NMR data. So here's the experimental carbon NMR spectrum. You can ignore those peaks indicated with the red asterisks. They correspond to so-called spinning sidebands. And there are then 9 peaks in the spectrum corresponding to the 9 carbon atoms of the molecule. And then from the crystal structure we determine from the refinement, we can calculate using DFT what the chemical shifts would be. And I think you'd agree this is a very satisfactory agreement between the experimental and calculated solid NMR data. Subjecting the final structure to a DFT geometry optimization, again, this shows the final structure is really close to an NG minimum as we require. And we actually also carried out a structure prediction calculation here, and it turns out the beta polymorph is metastable with respect to the alpha polymorph. And there are a few other predicted metastable structures, but higher in energy than the beta polymorph. So I hope that illustrates, and I think this is really one major direction for the future, the advantages of combining electron diffraction data and powder diffraction data, periodic diffraction data in structure determination. They're very complementary. The disadvantages of one are compensated by the advantages of the other. So we should really be, maximizing the opportunity to use these techniques in tandem with each other. just one very final comment in my last slide or two, and that is, to emphasize that there seems to be quite significant advantages in using the direct space strategy for structure solution rather than using traditional techniques such as direct methods. And here we're focusing on very low resolution electron diffraction data for this covalent organic framework material, where even for data as low as 3.78 angstrom resolution, we could still obtain successful structure solution using the direct space strategy using the Eaby program. Here we see a comparison. In blue is the known structure of this material. This was a systematic study to explore the success of structure solution for data at low resolution, and in orange is the structure solution obtained using Eaby. So this may point towards the advantage of direct space strategy also in the case of structure solution from electron diffraction data. So what I hope I've done is to convince you that there's a great opportunity to carry out structure determination of organic materials from powder diffraction data, but the process can be enhanced considerably by taking advantage of information from other techniques, especially also in MAR and DFT calculations, and also now by combining electron diffraction data together with powder diffraction data in the structure determination process. So I'd like to thank you again very much for the opportunity to give this lecture and for your attention, but especially I'd like to thank all members of my research group, both past and present, who worked in this area, many important collaborators, past, present, and future, and also funding organizations. And thank you very much again for your kind attention. Thank you.
Thank you very much, Ken. Now the floor is open for questions. We have 2 questions there, one by one.
Try again. Hello, Kenneth. Simon Parsons here from Edinburgh.
Hello, Simon.
Hello. Yeah, nice talk. Thank you very much. Just a couple of questions. You referred to the structure solution using single crystal data obtained from electron diffraction. I guess it works with X-ray single crystal data as well.
Yes, it does. We've applied it to single crystal data. One thing we find, however, and fortuitously I have this slide here, is that the efficiency of direct space structure solution seems a lot better for powder diffraction data than either electron diffraction or single crystalline cloud diffraction. We're looking at this systematically at the moment, but don't completely understand the reason. So what I'm showing here is this is actually the tyrosine example, and we typically run 40 independent calculations, starting from 40 different initial random populations in the genetic algorithm. And here I'm showing the lowest R factor in each population as a function of the number of generations. And what we can see is after 100 generations of the genetic algorithm, 38 out of the 40 populations have found the correct structure, whereas for the electron diffraction data, only 7 out of 40 found it. So both data sets give the same correct structure solution, but it seems to be a lot easier to find from the powder diffraction data by direct space methods. So we're looking into that. We also have done single crystal X-ray diffraction, but it's similar to the electron diffraction in terms of the, let's say, the rate of convergence on the correct structure.
Right. That's a very surprising result. And I mean, I'm interested in this from the point of view of solving incomplete data sets, solving structures from incomplete high-pressure data sets. Yeah. And certainly the simulated annealing methods work quite well. And yeah, it'd be very interesting to see the results of that. Very quick last.
Simon, just to add a comment there, I'm not saying that it doesn't work well, because it does achieve success.
Right.
But it doesn't achieve it as quickly. And I think, really where we need to look is the actual detail of the hypersurface. And I suspect the hypersurface is probably a lot smoother in the case of the powder X-ray diffraction data, but that's a preliminary comment. And we, as I said, we looked at this systematically at the moment.
Okay. Just one quick second follow-up question is about the number of parameters. You were solving structures with 33 and 34 parameters there. I think that sounds very complicated to me. Is that, how do you find that the number of required generations or the success rate scales with the number of parameters?
Yeah, I mean, clearly, if the parameter number, basically the dimensionality of the hypersurface, if that increases, then the number of generations we require to find the correct solution will increase substantially. But we do things like increase the population size, for example. And there's various ways we scale the parameters that control the genetic algorithm depending on the number of variables. But yes, these are pretty challenging once you're up to 30, 40 variables, and the calculations do run for a long time.
Okay. Thanks very much, Kenneth.
Okay, thanks, Simon.
We have another question.
Yeah. Gabin Babode from University of Rouen-Normandie. Thank you for the nice presentation. I had a question about the structural refinement. You said that you can couple DFT calculations in the same time as refinement. And how do you proceed? Do you alternate between Rietveld refinement and DFT calculation, or?
Yes, no, so it's not a simultaneous calculation, it's all alternating. So once we've progressed to a certain stage of Rietveld refinement, we'll typically do a geometry optimization with DFT, which can improve certain aspects of the quality of the structure. And then, as I said during the lecture, we can then maybe update the restraints in the Rietveld refinement depending on geometric features found in that geometry optimization. So we would typically, in a typical Rietveld refinement, maybe at 2 or 3 stages, carry out a DFT calculation, and partly to check that everything's fine if it moves substantially away from where we are in the Rietveld refinement, and where the Rietveld is not taking it in the right direction, for example. So it's almost to provide a check at different stages of the Rietveld refinement, as well as I say, to provide input information on improved restraints for the Rietveld.
Okay, thank you.
Thank you.
Okay, so one more very short question, please.
Hi, this is Jessica Bruin from Nanoimaging Services, and I was curious if you've done any work combining the powder diffraction data with electron diffraction data. I'm thinking specifically for cases where you have low completeness and filling in that missing wedge with powder data, or using a powder pattern as kind of your reference point to scale electron diffraction data. Scaling can be challenging, those sorts of things, or refinement against both simultaneously. I don't know if you.
Yes, no, thanks very much, Jessica. That's a really good point. We're actually working on that concept of combining the two in a single calculation, at least for the structure solution. How easy it would be for the refinement, well, undoubtedly feasible, but whether it would be straightforward, I'm not sure. But certainly, there's absolutely no reason we cannot, readily utilize 2 data sets during the structure solution calculation. As I say, we're working on that at the present time. I think one of the issues, whenever you combine 2 data sets of that type, is how you weight one against the other. So with 2 different R factors that are not necessarily, you need to know how to scale one against the other before you combine them. But we're working on that.
Okay, let's thank the speaker again. Okay, so the next talk today will be given by Ute Kulp from Darmstadt, and she will talk about automatic diffraction tomography solving crystal structures of beam and vacuum sensitive organics. Ute, I hope we have you online.
Yes, I'm here. Hello.
Hello.
I'm about to share the screen. Give me a second. Okay. Here. Is everything fine? Can you see it?
Perfect.
Okay, marvelous. Yes. Yeah, I would like to thank you very much, Tomče, for your nice introduction. And yeah, sorry for not being in Ochit. Some weeks ago when we met at the EPTIC, I was so sure I will be there, and then things exploded. So sorry to all of you that it is an online talk. And thanks very much to Panche for the invitation, as well as for her patience with my new decision. I'm talking today about the automated diffraction tomography, which is now a 3D-ED method, three-dimensional electron diffraction method. And this is now the term we usually use in order to describe the overall method. Actually, Jessica Brun has given on Wednesday a very marvelous talk about the method itself. And here I would now like to compare the methods a bit and show you a bit the differences with the approach of the automated diffraction tomography and the micro-D, for example. So actually, that is a slide we do not, you know already actually. So basically, if we have a crystal, large enough, we can do single crystal X-ray diffraction. And if the crystal's getting smaller, we can do a powder diffraction. But there we have the problem that we have overlapping data. So actually the partitioning is a problem where you would want to know the intensities. Do you hear me still?
Yes, we do.
Do you hear me still?
Yes, we do. Can you hear us?
Okay, fine. Because it says it's bad audio quality. So actually here we have an overlap of intensities, and we cannot know which intensity belongs to what. The electron diffraction allows to address a nanocrystal. So actually, due to the interaction of matter in a Coulombic way, so from a charged electron to the core, to the nucleus of an atom, we have the possibility to investigate small nanovolumes and get data from that. So it is possible to do single crystal electron diffraction data. And in the beginning, you would people did do 2D diffraction patterns, orienting the crystal in a special way, and then analyzing the despacing and the symmetry of the pattern. What we are using for this is an electron microscope. Actually here the electrons are produced, then we have the illumination system, the sample here, and the magnification system, and the detector down here. You can do all kinds of imaging, so it is possible to get more information than just diffraction from the crystal, and you can do as well on the crystal spectroscopy, X-ray spectroscopy or energy electron loss spectroscopy. You can implement parallel illumination as well as a convergent illumination. So all kinds of imaging is possible, and here all kinds of diffraction is possible if you range from a parallel to a convergent beam. So, I have to do that. So if we summarize that, we can access nano-sized volumes, but at the same time, we will have problems. Dynamical scattering originating from the strong interaction with matter is a problem in interpretation of all kinds of informations, no matter if it's imaging or diffraction. And radiation damage might alter the samples. That is one of the focus I have in this lecture. If we assume now this Ewald sphere, which is drawn for Kappa radiation, and we assume this large Ewald sphere, which is drawn for 100 keV accelerated electrons, then we see that with the X-ray Ewald sphere, we will have one reflection after the other in reflection condition. If we now go to electron diffraction, we have the many more reflections in the condition actually sitting here on the surface Ewald sphere and delivering a diffraction pattern which shows many diffraction spots, for example, as a grid, and that would be an in-zone diffraction pattern. We have a problem with that because the in-zone diffraction may look nice, but here we have, due to the fact that we have very thin samples, which we need to have in a transmission electron microscope, we will have a spike function. And this spike function will give us an uncertainty where the reflection cuts the Ewald sphere. So you might have intensities from this position, from that position, or from the middle of the reflection. So this can be significant, can deliver significant different intensities. So, and that you cannot really orient correctly by hand. In former times, actually, the crystal was oriented. You have a defined diffraction pattern. As I said, we have the problem with the diffraction patterns which are difficult to orient. But if you look from a side along this line, which is the tilt axis, and you draw the diffraction pattern in this red line, and now you tilt the crystal, then you have many different diffraction patterns, and you can align them into a 3D space. In this way, several structures have been solved, and here I would like to mention Weinstein and Zivagin, and in Russia, and Doug Dorset later in the States, which did pioneer work on solving the structures. But these structures very often needed simulation in addition. So actually here force field calculations have been made in order to solve these structures. And this lasted about a PhD long to solve the structure. Some of the structures may not even have been possible to be solved. What would we want to improve? We want to improve the completeness of the reciprocal space, because this is the key for structure analysis. This is we do by increasing the tilt range. We do by using fixed tilt steps, and this is done, therefore we need dedicated tilt holders, but we can do the tilt series manually and automated. The data quality is, for example, by reducing the beam damage, and automation speeds up the data acquisition very much, in addition in using better cameras, faster cameras. Data handling, so you will have a quicker analysis. if you do this, and you can use off-zone data in order to use, and this therefore you need the 3D reconstruction of the reciprocal space. So here we have the same plot I showed you right in the slide beforehand, and the red dots are the ones of the data which you would get if you would use zones which are oriented. And all the yellows you were missing. So the idea is that we would want to scan the reciprocal space in order to fill the gaps, in order to get more data. In addition, it is better to do that because here you would be able to enhance the number of reflections further. So how do we do that? We select a crystal, we take an image, we take a diffraction pattern, put it on a stack, make a tilt, find the crystal back, make a diffraction pattern. So we switch between an imaging mode, which we call the crystal tracking mode, and that we do in microstem mode. This is different to the microED because that is done in TM mode. But here we have the possibility to change focus just by changing focus to get into diffraction mode and using nano electron diffraction or nano beam diffraction, how it is called. So getting all these diffraction data, we can do a 3D reconstruction, and because we do that, we can use off-zone patterns, or the other way around. Because we have off-zone patterns, we need to do a 3D reconstruction. This is basically enhancing the number of reflection, and off-zone diffraction data is much less dynamical. The reconstruction is done by EADT or PETs, and here I would like to say a word about the illumination and the connection with the imaging mode. So here, this is the illumination system, and here, this is the sample. Here we have the second condenser lens, and if you take an aperture here, which is larger, and you would illuminate a wide range of the specimen, you would want to select that with selected area electron diffraction aperture in the back imaging plane of the objective lens. If you do nano electron diffraction, you would take a small C2 aperture, and the small C2 aperture would allow here to just select the place where you want to diffract on the sample by putting the beam there. So in general, this is possible doing SAED TM imaging, so like it is done in the microED case, but we saw that we have a high background contribution if we are going for very small crystals. And there is a certain uncertainty in the spot position. The NAD, the nano electron diffraction, allows to exactly select the position, and the crystal tracking will be done in STEM mode by just following the crystal by electron beam shift. This can be automized by a crystal tracking routine. This STEM, microstem imaging, combined with nano electron diffraction is pretty fast and allows to just select the range on the crystal which is necessary to look at. If we want now to reconstruct the data, we have a certain routine. I'm not going through the routine here, which means we take the raw data, we want to correct for the shift of the diffraction patterns. We want to correct for the tilt axis of all these diffraction patterns, which is done in difference vector space. So basically, you're looking to all the difference vectors of the reflections of in 3D, and there you would then all the vectors point to to some directions, and the vectors which point into the same directions would show actually a certain axis in reciprocal space. And the stereographic projection of this sphere is this pattern here. This we can get nice cell parameter analysis, and from the tilt axis we can reconstruct the reciprocal space and find special features, for example, twinning, as it has been shown here. The data, the intensity data, which will be extracted like I showed you right now, can be improved by electron beam precession. So here we have a tilt, an alpha tilt, which is very small. Actually, we take a tilt of 1 degree, and the beam is precessing around this perpendicular axis, which means that the Ewald sphere is somehow rolling, precessing over the reciprocal space, covering a certain wedge which is integrated and where the missing data is taken. In general, this is the general approach, and the barium sulfate has been used from us for proof of principle. But nowadays, many structures have been solved. For example, that is one of the earlier structures we solved. The large mineral structures, now we have minerals solved with up to 360 atoms in the asymmetric unit. And this is the material where I would want to focus a bit onto, because I would like to discuss about beam damage. Here is an example about a structure which we analyzed, which is an incommensurate structure, just to show you that this is very nicely visible in the reciprocal space, in the 3D reconstructed space. Come on. Yeah. In addition, with the fast ADT, we have the chance to address tiny crystals, which may be even agglomerated, and here find even very light atoms like fluorine. And here, for example, in the PDI, that is an example of a very thin platelet, which was only visible in STEM mode and not in TM mode, because they were so thin that they were about 20 nanometers in thickness. The space group is P63 over MC, and this is the structure. It is actually reduced, the space group, and here you can see why, because the lithium atoms we could detect here, which are partially occupied, they are sitting on different heights in the crystal structure. So this slide is only to show you that even light atoms can be detected. Now, as I promised, I'm coming to beam damage, and beam damage is important to look at. Actually, we have two ways of a beam damage. One is by ionization. Ionization beam damage is accumulative, which means you cannot avoid it, and every exposure you make adds beam damage to the sample. So what we try to do against that, we use fast imaging in the STEM mode, and we shift the beam, which is a small beam, along the crystal in order to have new places for diffraction. Another beam damage is temperature dependent and can be reduced by cooling the sample with liquid nitrogen. And why is it so important? It is important because the high resolution reflections, they drop first, Here, that's the high resolution reflections, and sometimes the low resolution reflections are even increasing, and that is a problem because this is destroying the chance for structure analysis. So here, this is what we can do against that. We can cool the sample, increase the contact to the grid in order to get rid of the temperature better. We can implement delays. We can use fast data acquisition and a small beam size, which would reduce as well the ionization beam damage. Another damage is vacuum. Vacuum effects, here, for example, is a polymorph of caffeine. They clearly exist. Here you have two morphologies. One is a hexagon, and then here we have the needles. And you see, even not putting the beam onto the sample, the hexagons disappear. So what we had to do at that point, we had to cool the sample outside the TM and then transfer it into the TM in order to not allow it to sublime in the microscope. To summarize here, the 3D ED methods are started with the ADT actually, which are just slices. The RVD methods, they did tilting, larger tilts, but very fine slicing by tilting the beam itself. The precession electron diffraction, ADT or PEDT, used by Palatinus, Lucas Palatinus, they integrate by using the electron beam precession, but that is still a bit time consuming. Then we have the continuous rotation of the crystal. This is only possible by fast detectors. And now the fast ADT, which I talked about already, is the method which allows crystal tracking automatically and is fast, not as fast as the micro-ED, but fast in order to allow as well for looking onto organic materials. I'm skipping that. The micro-ED actually showed here nicely in different Tim Grüne here and from Gonen actually here, nice structure analysis of organic materials with detailed information as well on the hydrogens. And I would like to compare that a bit in terms of what we did with the carbamazepine. And I would like to draw your attention here onto the crystal size. So the carbamazepine here could be solved from 150 times 100 nanometer crystal, and here the data is not merged at all. What is the drawback from our slow CCD camera is the extremely high R values, even here in the R internal. So that has been a problem, and that is clearly the hint that direct detection cameras improve structure analysis with electron diffraction significantly. Here it is just to show how important completeness of the reciprocal space is. I said a completeness is the key for structure solution. Here, this is a structure solution with just a 40-degree ADT data set, and here 2 atoms are missing. So this side, for example, we could assume we have here the 2 atoms sitting. If we are going to this side, yeah, we could assume that we have the atoms here sitting, which would lead to 2 absolutely different structures. This one being wrong, which is even a structure from literature, but this here, showing a better, more enhanced hydrogen networking, is the structure which it was possible to solve with 100-degree ADT data. So that is how important it is. And why is that though? Because the potential, the atomic potentials, they smear out because information is missing in the reciprocal space, which leading to sparse information in atomic potentials. And additional here, if we look onto this sketch, we see that hydrogen's atom should be better visible in electron diffraction data. And this is just an example I show you because this structure, I tried to solve it actually in 1997. It has been solved now by fast ADT, and this is a triclinic structure. It's a new polymorph. And here you can see a very nice dimeric pattern where you see the hydrogen potentials for this very well. This hydrogen is not very nice, but yeah, maybe we could improve the data at that point. Coming back to tiny crystals, you would need to have a very good tracking routine to stay onto that, but we could show that with tiny crystals, even with a 20 nanometer thick crystal here of vaterite, we could solve the structures. But in this slide, I would like to draw your attention to the calcium carbonate hemyhydrate, which has been solved on this tip here. Going further along this needle would lead to only polycrystalline diffraction. So we had to stick to the very tip of this crystal. Nevertheless, it was possible to solve the structure of a calcium carbonate hemyhydrate and with an absolutely good defined position of the water. Another example is from a cultural heritage object, which has been corroded. That was given to me from Sebastian Bette, this material. And here it is a hemyhydrate, it's actually a calcium acetate. And I just show you that to show you how beautiful these structures can be, which one can solve with electron diffraction. It has been solved beforehand with powder X-ray diffraction and has been had to be confirmed. And here the water inside the structure could be distinguished very well with electron diffraction. If it comes to porous material, we very often have gases inside the channels, inside the pores. And here we have the organic material inside, which stays nicely during electron diffraction. But here we have, in this morph, we have water inside. And here we could solve only the activated structure because in the vacuum, the water disappears and only the activated structure was accessible from electron diffraction and was refined later with Riedfold. Another example here is a zinc morph, which as well was dehydrated in the vacuum, and we could see that right away in the vacuum, in the TM, watching the first structure analysis or the first data sets we get, and then watching the data sets later, and we could see that the beta angle changed up to 109, from 103 to 109, and this change, from this change we could tell that there has been a change in the TM already. This is a structure. I'm not going into that because I would want to focus more on the effects. But here we could see still some water positions left over, which have been more defined inside the structure. And this is the last example. Again, it's a dehydration already here in the first hour. But here we could solve both structures, the hydrated and the activated one. And it's very nicely to see that we have here the kappa coordinated for the hydrated structure with oxygen, whereas the structure loses the water here, which is coordinated at the kappa, and it's just plane, planar coordination. This data, because this is very difficult to know which state you are in, has been confirmed and had to be confirmed by Rietveld refinement. And this is now the reason, the point where I would say, I would like to emphasize that the Rietveld refinement, if you have powder data available, is very important, as well as the comparison of every structure you solve with 3D ED with the powder data, because you never know if your material has been changed or if you're looking on another structure which is not describing the bulk. Okay, so that is what I wanted to say. This is the group, the people who were involved in the development and people who did the new research now I showed here. And I want to conclude and say that 3D-ED is able, no matter which method you're using, to give you reliable crystal structure analysis of nano-sized crystals. It's showing very well light atoms like hydrogen, lithium, boron. I did not show, that's why I enlightened that here a bit, it's absolute configuration determination, that's possible as well, and I did not show the twinning superstructure modulation disorder, not in detail at least. But I would like to tell you, take care of changes in the sample. In terms of vacuum effects, in terms of beam damage effects, compare it with the powder and go through your analysis with an open eye. And with this I would include, and I think 3D-ED has a very nice future, what you can see here in this graph. Thank you for your attention.
Thank you very much. Okay, now we have time for questions. Okay, we have 2 questions, please.
Hey, Uti, fantastic talk. This is Jessica Bruin from Nanoimaging Services. Hi. I'm curious about the zinc MOF that you discussed, or the beta angle change and dehydration in the microscope. And earlier you had mentioned that cryocooling prior to insertion in the microscope can help with that. And I'm wondering, was this cryocooled first and still dehydrated, or?
No. This has been done by a student, a PhD student, which just started. And that was a training material. So it has not been performed now, the cryotransfer. But this has been cooled, but not cryotransferred. So that's the next step. But yeah, as I said, the people need to be trained, and we like to use the MOFs as a training material.
Beautiful, thanks.
This is Simon Parsons here from Edinburgh. I'm interested in why the ADT method gives you improvements over simple rotation in the beam. What is it that ADT is doing that you're not? What are you accessing in ADT that you're not accessing in a simple rotation?
Yeah, the simple rotation is not the problem. The simple rotation we can apply as well. But we do not have a fast camera, therefore, yeah, it's not possible at the moment, but we could do it. That's not a problem. The point is the nanobeam diffraction. So actually, in micro-ED, you take a large beam, and if you have a tiny crystal, then you illuminate a very, very large area of the carbon. So you have a lot of background inside your data, which you do not want. That is one of the key points. In addition, if you have a larger crystal and you would illuminate the whole time, because you illuminate above of the selection, the selected area electron diffraction aperture, you illuminate your sample with a white beam, and it's not just the place where which you have chosen. So in the whole time, the beam is on the crystal. The advantage of the continuous rotation is that it's extremely fast and it's using direct detection cameras or CMOS cameras, so which is, actually, CMOS has still a background, direct detection is a reduced background. So actually, you will have the fast data acquisition is the only benefit, but if we would combine the two, then it would be much better even.
Okay, thank you very much. That was very clear. Thank you.
Yeah.
We may have time for one more question. If there are no questions, then we will thank the speaker again for an excellent talk. We're running a little bit late on the coffee break, so please be back at 3:40 and we continue with the session. Again, let's thank the two speakers for excellent presentations.
turn. Oh, maybe we should.
Okay, good afternoon, everybody. We'll start the second session of the second half of the session, this afternoon's session. And so our first speaker is Adam Michalchuk. He is a senior scientist for at the Federal Institute for Materials Research and Testing. He enjoys researching the origins of mechanochemical activity, and his talk today will discuss how he uses and develops time-resolved methods based on using synchrotron sources to learn about mechanochemical reactions. Adam, the floor is yours.
Well, thank you very much for the kind introduction. Before I start, just to lend my thanks to Tomče and the whole team for what's been a really fantastic week so far and continues to be both scientifically and socially. So thank you very much. And indeed, thank you for the opportunity to speak at the conference. So as I said, my name's Adam. I'm from the BAM in Berlin, Germany, where we're looking at trying to develop new methods based on synchrotron approaches to follow mechanochemical reactions in real time in situ. Now, I don't need to go into too much detail about mechanochemistry because we've had a few talks already over the last couple of days. But I just want to start by I think, maybe highlighting where I find it so fascinating is the fact that mechanochemistry is arguably the oldest form of chemistry that humans have been able to control. And this dates way back to prehistoric civilization when we were creating fire through this tribal chemical processes of rubbing stones and flint together to generate fire. And there's a lot of evidence of mechanochemistry in various forms over the millennia. But it wasn't actually until the early 20th century when William Ostwald finally defined mechanochemistry as a real branch of the chemical sciences, right alongside these other traditional disciplines of chemistry. So, we've had this around for thousands and thousands of years, but we've only really been studying it for about 100 years. Now, again, we've seen a lot of this over the last couple of days, so I won't dwell on it, but the idea for those who perhaps have forgotten is that we take these dry powders, we put them in some mechanochemical reactor, a ball mill, or one of these other types of devices, and we shake it around, and we hope that mechanical stress, that dynamical mechanical stress that we're applying to the system is enough to drive some chemical or physical transformation. And there's really a lot we can do, both in terms of making new materials, multi-component crystals, metal-organic frameworks, you name it, we can probably make it, and some chemistry, both covalent chemistry and non-covalent chemistry, and even some complex chemistry up to, for example, prebiotic reactions. And it's the fact that actually in all of these cases, we're able to just mix together these dry powders. We're really able just to combine these dry reagents in this mechanochemical device and drive the chemistry forward. And that's really made the community open their eyes a lot, particularly in the organic solid-state community, that this is really a groundbreaking technology that is going to lead towards new dimensions in sustainable and environmentally benign processing. Now that said, I've said we've had this for thousands and thousands of years. We've been studying it for about 100 years or so. But the reality is we really don't actually know much about it. We still don't really understand how it works. And we've heard a lot over the last few days about crystals being the cemetery or the graveyard for molecules. But actually, I think the culprit goes much further back to Aristotle, who says that basically solids can't react unless they're fluids or if they're dissolved. And I think that it's this comment that's actually directed the way that we've studied chemistry, we've studied physics over the millennia. And it has led to a lot of our understanding. We know if we want to get chemistry, we need to have molecules mixing at the molecular level. We know we need to get collisions. We know that these collisions between molecules need to have enough energy to drive the reaction forward. But at the same time, it doesn't take a genius to realize that if you put a powder on the table, these particles aren't going to spontaneously jump up and around and smash into each other and cause chemistry to happen. So how is it that our reactions in and between solids can actually happen? So I'm not going to dwell too much on this today, but the idea is we do have some ideas. We've come up with some theories over the years, and we saw with Helena's talk the idea that one of these materials can deliquesce, for example, and actually when you bring two solids together, something can dissolve, and the reaction can happen in a solution phase. Likewise, we all know about eutectic formation, and there are many cases in molecular organic systems where bringing the two powders together, you actually form a eutectic melt at the interface, and it's actually in that liquid phase that the reaction is going to happen. And so actually what looked to be a solid-state transformation perhaps isn't a solid-state transformation at all. In other cases, we also need to consider gas phase processes. So this is an old example of a so-called mechanochemical reaction between two organics, where it turns out that the reaction isn't solid state, but actually you get the sublimation of one of these starting reagents and effectively nucleates on the surface of the other reagent. And you can see in the microphotographs the reaction zones on the surface, so it becomes a topological transformation in the product phase. So again, maybe Aristotle wasn't actually so wrong after all, maybe particularly in the organic solid state, that we do need to be considering some of the fluidization processes that can lead to the mass transport and the diffusion that we need for chemistry. That said, I think at the end of the day, this is still a big black box. We have some theories, we have some ideas. I certainly don't want to claim that all of these solid-state processes actually are fluid phase processes. I have absolutely no grounds to say that. But I think it is very clear for any of us in the field that this is really a black box. If anyone's interested in looking more at some of the discussions around the mechanisms, we've just published a review on that, so I welcome you to take a closer look. But the big problem then comes from the fact that because we don't really understand how these processes happen and how these reactions are going to happen between them, we can't begin to understand how we can control them. And this becomes a really big problem if we want to take these laboratory reactions, these laboratory processes, and translate them into an industrial setting. We don't actually know which parameters to be playing with. We don't know, does the jar material affect the reaction? Does the material of my ball affect the reaction? Does the frequency affect it? These are all parameters that are new in mechanochemistry that, again, we really don't have a handle on. And so we need to get to grips with this before the technology is really going to become a viable technique. So then this comes down to how are we studying mechanochemical transformations? How are we actually studying these reactions and trying to find out about them? Now, historically, and even today, the main approach to studying mechanochemistry is the so-called ex situ analysis. So what we do is we take our ball mill or some other mechanochemical reactor, we stop the reaction at some given time, we then take the jar out, we open the jar, we somehow have to extract the powder, that's probably scratching it out of this milling jar. We then have to prepare it onto some analytical slide, so in diffraction onto the diffracting plate, and then we stick it in the diffractometer to collect our diffraction. So that looks pretty typical, pretty conventional for anyone who does experimental chemistry. But actually, it turns out that these processes are not so benign at the end of the day. So you think we're opening the vessel, and we're exchanging the atmosphere from what was inside the reaction zone with the external atmosphere. We then have to somehow mechanically treat this powder and to prepare it for diffraction analysis, and then we have to undergo a relatively lengthy analytical procedure. So we then have to make the assumption that the material we're analyzing at the end of this process is somehow representative of the material as it was inside the milling jar during the reaction itself. And it turns out what we're starting to realize more and more is that is a very, very bad assumption to make in many cases. So one of the most striking examples, I think, came in the mechanochemical synthesis of this HCOST1, this metal organic framework, where the group looked at sampling the reaction profile using ex situ analysis. And so what was done is, the reagents were mixed stoichiometrically, put into this milling jar, and at 5 to 10 second intervals, this milling jar was stopped, opened, and some sample was taken out and analyzed by diffraction. And what they saw is that the starting reagents pass via some intermediate, which they called intermediate 2, and this intermediate 2 then converts further into HCOST1. Fine. But then they went and they did this by in situ analysis. They didn't stop the mechanochemical reactor. They didn't remove the powder from the vessel. They simply followed the reaction as it happened using in situ diffraction. And now what they're seeing is that the starting material goes directly into a different intermediate product, or different intermediate phase, the intermediate 1, before it transforms into HCOST1. So now what we're seeing is that just by changing the way we're analyzing our powder, we're changing the apparent mechanism that this reaction is passing through. We've also done some work in organic co-crystals, so I haven't put the chemistry here, but it's not important. And what we wanted to try to see was whether or not this process of actually scraping the powder out of the vessel might also influence the reaction. So what we did is we did 2 very simple experiments. We did the first where we ball milled for 20 minutes. We then opened the vessel and sort of broke up any tablet that might have formed in the ball mill. We ball milled again for 20 minutes, again broke up the tablet, and ball milled for a further 20 minutes for a total of an hour. Then as a comparison, we did the same thing. So we milled for 20 minutes, but we let now that the vessel just relax. So the temperature profile was very similar. Again, milled for 20 minutes, and again for a further 20 minutes to get the same amount of time. And what we get if we analyze the 2 different powder diffraction patterns are 2 very, very different products. We see in the case where we break up the tablet intermittently, we get an enormous conversion, a very significant conversion to the final co-crystal product. Whereas if we don't break up the tablet intermittently, we actually don't get formation of the product we wanted, but we're starting to see some different Bragg reflections. So again, simply by changing the way that we're analyzing and treating the powder intermittently, we're changing the apparent mechanism of this transformation. And finally, as most of us know, if we've created a powder in the lab, we can't just walk down to the diffractometer and it's not going to be available at the drop of a hat. You usually have to wait for some hours, maybe a day or 2 before you're going to get access to the diffractometer to actually measure your sample. And it turns out that itself can be a big problem. So there are the so-called aging processes in these organic systems, and I think Helena also talked about this the other day. But the idea is that if I have to wait some hours to analyze my powder, the transformation can progress with time. And so what this then means is that the composition I'm seeing from my final powder after some hours of waiting may again not be representative of what I had in the ball mill in the first place. So again, are we really seeing what we want to see through ex situ analysis? So this has then led to this field and a lot of interest now in trying to develop methods to analyze these reactions in situ and in real time. So the idea that we can really follow the transformations inside the ball mill or inside a mechanochemical reactor without having to stop it, without having to perturb the powder, and really trying to get to grips with how these materials are reacting. And there's really been a lot of developments over many decades, particularly in the last 10 years or so, with the use of synchrotron radiation. Unfortunately, I don't have time to go over most of these, but Franziska Emmerling and I have written a couple of texts overviewing the field for the last couple of years. So you're welcome to take a look if you're interested in the broader picture. But I'm just going to focus today on 2 of our more recent developments in X-ray diffraction and X-ray spectroscopy. So the first example of in situ X-ray diffraction actually came from Tomislav Frišek back in 2013, where they took a ball mill, they stuck it at the synchrotron at the ESRF, and they fired X-rays directly through the milling jar to try to collect the diffraction patterns in real time. And they chose as their first system this mechanochemical formation of this metal organic framework. I think this is ZIF-8. And you can see really nicely the evolution of the diffraction profiles in time. And you can see the growth of different Bragg reflections and the loss of some of the product reactant phases. And indeed, just by following the relative intensities at that time, they've mapped out an approximate kinetic profile for the reaction. So I'm going to start by shooting myself in the foot a little bit here, and just give it one caveat before I go much further. And just say that when we're doing these time-resolved in situ X-ray diffraction experiments, our setup looks schematically something like this, where we have, of course, the X-rays coming from the synchrotron, pass through some optics and some shaping kit, and then it has to go in and out of our milling jar before it's going to diffract onto the detector. That might come as no surprise, but that really means that it imposes the limit on the fact that we have to have an X-ray transparent milling jar. And typically what we use is PMMA, so polymethyl methacrylate, some plastic compound, for these measurements. And what we're starting to realize very recently is this might not be as benign as we hoped it was. So others have also published some of the things within the last sort of 6 months or so. Yelena Boldareva showed an example, and Thomas Afishik also showed an example, but of course here I show ours. So we were looking at the polymorphism, the kinetics of polymorphism between these two organic co-crystals from this green phase to this blue phase. And of course we started with a stainless steel jar in the laboratory, which is what we normally use. And you can see that this polymorphism requires an enormous amount of milling time. So it's about 15 to 20 hours of ball milling before we can get the conversion of these polymorphs. And then we wanted to do this in situ, so we prepared our sample in a PMMA jar, and we did the same reaction with the same materials, and we find that the conversion happens in 3 hours. So this is an enormous, enormous difference in the kinetics just by changing the material of the milling jar. I can tell you that I think nobody yet knows why these different materials have such a drastic impact on the kinetics, and in some cases also on the apparent mechanisms. But it does throw the caveat that we need to be a bit careful in interpreting laboratory mechanochemical experiments using time-resolved in situ methods. That said, and I know I've shot myself in the foot a little bit for the rest of the talk, but we are still, and the field is still progressing using plastic jars, hoping that internally at least it's consistent to try to give us some information as to how these reactions should progress in real time. So with that, I'm just going to start with a couple of really quick examples on how we've used used time-resolved and in-situ methods in an attempt to try to understand some of the control features that sit underneath mechanochemical reactions. So trying to understand which parameters might exist in order to manipulate and to control the kinetics and the mechanisms of our reactions. So I'll just focus first on one of the examples we've done recently on trying to look at frequency. So it goes probably without saying that increasing the milling frequency increases the rate of your reactions. That's probably not surprising, and that's not what I'm going to show you here. So we took a ternary co-crystal system. So it's a co-crystal between isonicotinamide, pyrazinamide, and glutaric acid, and we wanted to try to understand how this reaction progresses in a ball mill. So what we found is that if we take A plus B and we ball mill that, we can get the binary co-crystal. And if we take that binary co-crystal and we add C, we can, of course, obtain the ternary phase. Likewise, if we take B plus C, we ball mill it, we can get the binary phase. And if we add A, we can turn that into the ternary phase. Not so exciting. But what we wanted to ask then was what happens if we add all three of the starting materials together at the same time in the same ball mill. So what we did is we started our reactions at 40 hertz, and we stuck it in the ball mill, and we put it at the beamline, and we followed the transformation. And what we see after about 6 minutes of ball milling is the simultaneous appearance of both the binary phases and the ternary phase. So it's hard to say whether the binary phase is an intermediate or a competitive product, but it is certainly present in the ball mill as one of the reactant phases that's eventually consumed to form the ternary co-crystal at the end. But what was quite surprising is what happened if we increased the milling frequency to 50 hertz. And what we now see is that the starting materials go directly to the ternary phase, and there's actually no formation, no presence of the binary phases whatsoever. So again, just by changing the milling frequency from 40 to 50 hertz, we seem to be suppressing the formation of this binary phase as an intermediate. Again, we're still looking at trying to interpret and understand better why that's the case. But again, we're now starting to see, using these time-resolved methods, that frequency may not just have an influence on the kinetics, but also on the apparent mechanisms of these reactions and these transformations. In another case, we wanted to look a bit more closely at particle size. So we know in solution chemistry, of course, the reaction is driven by the bulk composition of what you've dissolved in solution. And many then thought that in a mechanochemical reactor, it should be very similar. I'm putting a one-to-one stoichiometric mixture of powder into the ball mill. It shouldn't really matter what state that's in. Eventually, that should go, or that should all progress in a stoichiometric manner towards the final product. So we wanted to test that a little bit, again, using these time-resolved in situ methods. So we started looking at this glycine oxalic acid dihydrate system because it's quite interesting as it has two different stoichiometries for the salt product. There's a one-to-one co-crystal or salt and a two-to-one salt. And so we wanted to see how we might be able to influence that by manipulating the particle sizes of our reagents. So we start just with out of the jar, we just took the two powders, mixed them in a 1-to-1, and we followed the transformation. And perhaps not surprising, you can see that the reagents are consumed, and you get maybe a small amount of the G2O, so this 2-to-1 salt forming as an intermediate, but it goes towards the stoichiometric product in the end. Fine. And indeed, so we then did some microscopy, and I don't show the images here, but we have approximately equivalent particle sizes in this case, and we can see if we analyze, if we look at the diffraction profiles in the early stages, we can see the Bragg reflections that correspond to the 1-to-1 product forming. But then we thought, okay, we know that reactions in the solid state can only progress at the interfaces between our particles. So what happens if we keep the overall stoichiometry of our system as 1-to-1, but we change the local stoichiometry by trying to change the particle size? So let's take this glycine phase and let's make it smaller, and then add it into the mixture instead. So we ground up the glycine particles to make them smaller, we added them into the mixture, and lo and behold, what we now see in the early stages of our reaction profile is not formation of the 1-to-1, but actually formation of the 2-to-1 co-crystal. So again, by changing the particle sizes now that we're putting into our ball milling reactor, we can change very much the apparent mechanisms and the apparent dynamics of this transformation. And again, I stress that this is one of the areas that the kinetics of mechanochemical reactions are really very, very different than the kinetics of solution phase processes, because we're no longer interested in the bulk composition of the mixture. We are interested now in these interfacial processes and what the structure and the composition of the interfacial processes are in actually guiding the transformations that we're obtaining. Now, on that same light of looking at the interfaces and how we might be able to control things using these interfacial processes, we were quite interested also in actually, do we need impact at all? Can we still drive this chemistry forward simply using friction between our particles? And so we did some work on this so-called resonant acoustic mixer, and this device is really quite cool because it uses an acoustic wave to sort of push the sample, to push the particles around in very intense local mixing zones and get I guess, shear between the particles. And we wanted to see then, can we actually drive co-crystallization using this device instead of a ball mill? And our case was using carbamazepine nicotinamide. In this case, we did liquid-assisted grinding, so we had 20 microliters of water, and we wanted to see then, can we form the 1-to-1 co-crystal in the end? So this is the time-resolved diffraction images. So on the left, you see what we obtained from low intensity, so very low interfacial shear between the particles, and if we go to a high mixing regime. So again, you can't tell very much from those, but I think hopefully you can agree that those are very different than one another. And then we can look a little bit more closely, and we see actually at low intensity mixing, we don't get the co-crystal at all. What we get is we get an interaction between one of our starting reagents, so carbamazepine, actually with the water that we've added into the system, and we simply get growth of a carbamazepine dihydrate complex, so not the final product that we wanted. But instead, if we do this reaction at higher intensity mixing, we do get formation of this dihydrate, but that dihydrate is consumed, and we can push the reaction then towards the co-crystal product. And so we can actually use the change in the intensity of this interfacial shear processes to dictate which outcome, which product we're able to obtain. And again, we think this has a lot to do with the structure of the interface between our particles. So we think that at low intensity shear, at low intensity mixing, we're effectively creating this sort of structure of surface of a dihydrate around our starting material and actually restricting the rest of that material from subsequent reactions. And it's not until we get to higher mixing intensities that we're able to break off that surface layer and actually drive the reaction further towards the co-crystal product. So once again, we're within this regime that it's not about the total composition of the powder we put into our mechanochemical reactor, but it's really about somehow trying to dictate and trying to control the structure and the composition of those interfaces between our reagents. So with that, I just want to say, I think concluding this part, that I've probably not provided any answers whatsoever. But I think it's very clear that by now starting to use these time-resolved and in-situ methods, we are starting to realize more and more the types of questions we need to be asking. We're starting to recognize the difference between solution chemistry and mechanochemistry. We're starting to identify a whole plethora of new control features that we really need to be taking into account that we hadn't been aware of before. And so I think this is really a very young field and something that we have a lot still to explore. That said, we have actually learned something, I promise, and I'll try and jump into one tiny feature of the mechanochemical kinetics that we've learned something about quite recently using new developments in our time-resolved in-situ diffraction. So if you look at a typical mechanochemical transformation, and I think Francisca also showed something similar the other day, they tend to look something like this. So you tend to have a rather prolonged induction period, and then at some point in time, the reaction starts, and then you get to your plateau once the reaction is completed. But that, for many who come from a solution background, might be quite confusing. Now, how is it that you can have these enormous induction periods without any chemistry happening, even though the conditions in the ball mill have effectively not changed to any degree? And just in case you don't believe me, this is some experimental data, so I didn't just draw a curve in PowerPoint and try and trick you. So we studied mechanochemical organic reaction with some colleagues in Cambridge, and you can see some really incredibly long induction periods in these transformations. So depending on the intensity of the ball milling setup we're using, we can go anywhere from about 10-15 minutes, even up to close to 3 hours in our induction period before the transformation starts. So that gets us thinking, what on earth is going on? What is the origin of this induction period? So we've been recently looking at this, again, in terms of co-crystals. They're quite nice model systems. We're looking at the polymorphism between two organic co-crystals. Again, this green polymorph to this blue polymorph. And we did a lot of ex situ analysis, and you can once again see that there is a conversion between the green and the blue polymorph, and that the time required to go from the green to the blue polymorph is really quite significant. At high frequencies of ball milling, it's somewhere around maybe 2 hours, and if we reduce the intensity of that ball milling, we can actually extend it out to something about 20 hours. So these can be really, again, enormous induction periods in these systems. But then we turned to thermal analysis to try to get some understanding of what's actually happening. And so what we're starting to see, and this goes back to what James Mack showed the other day, is it turns out that as we're treating these materials systematically, hitting them again and again and again, we seem to be storing energy in these materials in terms of defects. And actually, Panche had a really nice paper on this with the flexible crystals not so long ago. But the idea here is that as we systematically increase the defects or the entropy in these systems, we're actually increasing the internal energy, we're destabilizing these materials, if you will, step by step by step by step, until we actually lead them to when they're no longer stable and push them over some reaction barrier towards the transformation. So again, someone asked the other day something about metastability in mechanochemistry, and I think it really depends now on what your definition of metastability is. Because once again, in these processes, we're really not at an equilibrium state of our materials. We're in highly activated, highly metastable particle states, I think, of our crystals. So we're always dealing with these metastable issues in mechanochemistry. But anyways, so what this is starting to tell us is that if we want to try and understand this kinetic profile and this kinetic effect in our ball milling reactors, we need some way to actually be able to identify what is the particle structure and what is the size of our particles during ball milling. And it turns out that's really not so superficial to do, because anyone who does powder diffraction knows that you want diffraction to come from a single point, otherwise your diffraction profiles are incredibly distorted, and there's really not much you can do from that. And this becomes a real challenge when we deal with ball milling because we have this three-dimensional sample vessel that we're shooting through. And it turns out we end up with diffraction from the front of the milling jar and the back of the milling jar. And so actually all of our Bragg reflections become split when they hit the detector. And so it looks something like this. So this is what we've collected using just a NIST silicon standard, where we pass the X-ray beam through different positions in the milling jar. And you can very quickly see that the shape of the scattering that comes from the silicon standard is really not ideal. And the closer we get to the center of the milling jar, the less ideal it becomes. So we did a lot of work in trying to identify how to minimize this effect and how to interpret the data that looks something like this. And so I'll go through that really quickly. So the idea, what we then started to think is we need to come up with a strategy effectively to minimize the splitting in our diffraction profiles. And so we came up with new milling jars, and I won't go into the details of those, but what we started to find is that before we do any mechanochemical reaction, and it perhaps is sort of not so shocking, but it wasn't known in the field at the time, is we really need to map out the structure of that milling jar using the X-ray beam. So basically we take that jar and we pass it horizontally through the X-ray beam, and we look at the intensity of the X-rays on a diode behind the jar in order to map out the change in the density of the material that's passing along the X-ray beam. And so you can now very, very easily see, here's the outside of the jar, if we then come to the wall of the milling jar, then you have the inside of the milling jar and the other wall, and then again we're outside the milling jar. So we can very accurately now map out the structure of that milling jar. And if we put a silicon powder inside, you can very quickly see that the moment I move away from the very edge of that jar, the splitting becomes quite apparent. So what we then started to think, okay, we need to make sure that before we do any of our milling reactions, we need to align the jar as close to that edge as we possibly can. Now that doesn't come without its problems, because close to that edge we also capture less powder, so the intensities become a real problem. But we're hoping that by doing that we can at least get towards some quasi-ideal diffraction. Then what we started to think, okay, can we explain what this diffraction profile looks like? Can we actually come up with a function now to describe this split diffraction peak? And so we started to think, okay, we need somehow to describe that there's going to be effectively a sample at the downstream end of the milling jar, there's going to be a sample at the upstream end of the milling jar, and then there's going to be some sample that's sort of sitting between the jars that's also going to diffract. So actually, we need to come up with a profile function that has, roughly 3 scattering components to it, S1, S2, and S3. And then what we did is we came up with a split TCHZ conventional function that's split, where we can now treat each of these extreme profiles independently. And then we found that actually just fitting then the residual intensity in the center with a Gaussian function actually works really, really well. So it's just by fitting with 3 functions this profile, we can actually capture really nice intensity, a really nice description of the profile function. And again, we mapped that all out using a silicon standard, and we've quantified that and qualified that quite robustly. But I think what's more exciting is not what this function looks like, but actually what we can do with this function now. So again, it's organic solid state, so we wanted to see what we can do now with some organic co-crystallizations. So we started with, again, we're not very exciting with our chemistry, but we started with this theophylline benzamide system that Franziska again showed yesterday, and we did neat grinding to form a co-crystal between those materials. And so what you can see in the in situ data, you can see now the loss of the reagents, and you can see the formation of the product phases. And because we now have a really good description of the profile, we can actually do really very high quality refield refinement for quantitative refinement. But what I think is very striking here is that we again have a very, very prominent induction period. So we can see now, even during the ball milling, for the first 6 or 10 minutes or so, actually nothing is happening. And it's after that time that we're getting the transformation to occur. But now what's really important is we don't just have a quantification for the phase composition. Because we now have an accurate description of the peak profiles, we can actually extract a lot of the microstructural information as well. So now what we're able to show actually is that this induction period is not as benign as once was thought from these in situ methods, but really is matching what we're seeing with these ex situ analysis. That this whole process now is really dominated by the comminution and the activation of our materials. And there seems to be a critical size, around 100 nanometers, that the crystalloids have to reach before we're getting the onset of a reaction. And I only show one example of this here, but we do have a number of other examples that also show that it's around 100 nanometers that these particles become activated enough for mechanochemical reactions to occur. So we're starting to see now new mechanistic insight into some of the microscopic origins of mechanochemical reactivity. But what was quite interesting for us, again, is what happens then if we add a small drop of water. And what we can then see is that, again, the reaction profile goes, but now we get interaction of our benzoic acid with the water, and we form, theophylline with the water, and we form initially a hydrate phase. So we no longer have an induction period in this reaction. And it turns out that it's that hydrated phase that then reacts with the other reagent, and it forms then a different polymorphic form of the material. But what I think is really striking here, not only do we get a different polymorph, we can guess because of the presence of this hydrated phase, but also we no longer have a comminution limit, because this hydrated phase never actually exceeds the 100 nanometer limit that we're starting to observe. So again, we're really just scratching the surface of what the types of mechanistic detail we can get using time-resolved in situ diffraction, but we are already starting to identify some really, I think, exciting new microscopic features of these transformations that we didn't see before. Now, I just want to finish on the diffraction side with one last piece of development. And the idea here is that many people in the organic chemistry world, they turn to us when we say you should try ball milling, and they say, my material's too expensive or it's too toxic. I don't have 100, 200 milligrams to stick in a ball mill. And so we thought, can we do these mechanistic investigations using the amount of material that many of these chemists have? But again, as I alluded to earlier, typically the diffraction intensity you're getting from these in situ methods is simply too weak. And so, we've typically used hundreds of milligrams. So we went away again and we spoke with our engineers really very nicely, and we said, can you come up with a design for a new mechanochemical jar or new milling jar that has extra thin walls? So they managed to make us milling jars that have something about 0.3 to 0.5 millimeter walls, which sounds really dangerous if you put a ball in that and you shake it around, but somehow they don't break. And using those jars, we were actually able to maximize the scattering intensity in our sample, and we can actually now do these mechanistic studies down to only 10 milligrams of material in our milling jar for organic compounds. And just to show you, again, I won't go into the details of this, but we're able to get, again, really high quality Rietveld refinements and even relatively good quality microstructural information at the 10 milligram scale. So this is really, I think, opening new dimensions now into the types of transformations and the types of reactions that we can analyze using time-resolved and in situ methods. So I'm going to turn, for the last few minutes, towards X-ray spectroscopy. And this is really a very, very new dimension in time-resolved in situ methods in mechanochemistry. So I'm just going to scratch the surface and just sort of hopefully whet your appetites a little bit for what's coming. It's very exciting for us, so I hope you're also excited by it. But anyways, for those who are perhaps not familiar with a setup for X-ray spectroscopy, it's actually really very simple. We take our polychromatic beam from the synchrotron. We then monochromate it to a single incident energy. We pass it through an ionization chamber to get the intensity of that initial beam. That goes through a sample, and then we pass it through another ionization chamber to get the intensity after the sample. So very, very simply, we can use the ratio of those two to understand how much of that particular energy is actually absorbed by our material, and then we can get the absorption profile from the sample. The other way to do it, and the way that we had to do it initially for various technical reasons, was through fluorescence, again, where you take a monochromatic beam, and you pass it into the sample, and you monitor the fluorescence that's coming from the sample as you scan the incident energy. But the important thing that I want to highlight here is that both of these conventional setups require a monochromatic beam of X-rays passing through the sample. And so we have to, in order to actually get the entire X-ray absorption spectrum, we have to systematically scan the monochromator and scan the incident energy of that beam. So we started, I know this isn't organic, and I apologize, but there are some organic molecules at the bottom. So we started looking at the mechanochemical synthesis of gold nanoparticles of course, at the gold edge. And we did a tandem setup where we can now look at the X-ray fluorescence and the X-ray diffraction with a number of different reducing agents. So what we can then follow during mechanochemical reaction, during the ball milling, is we can actually now see the redox processes occurring and the rate of those redox processes in the gold species. So we can monitor the conversion of gold 3 to gold 0. And using X-ray diffraction, and we can follow the formation of the nanoparticles in real time. So we're now getting both the electronic processes and the structural processes simultaneously during ball milling. And then we were able to compare, and I won't go into details here, but we were able to compare different reducing agents, both in terms of the reduction kinetics and the crystallization kinetics. And we're starting to see some really interesting things here. So anyone working in nanoparticles, we're starting to see that actually the rates of reducing agents in the solid state can be very, very different than the rates of the same reducing agents in the solution phase. And again, so I think this is quite exciting for those in that field, but I won't dwell on that here. The important part is that the time resolution is absolutely abysmal. So because we have to scan the incident energy coming from the monochromator, and because inherently the absorption process is quite weak, we're getting very, very slow time resolution. And in our case, it was on the order of about 15 minutes. So not so useful. But very, very recently, we've come up with a different strategy based on the so-called dispersive X-ray spectroscopy. So what we can now do is we can take the polychromatic beam that comes directly from the synchrotron, we can just direct that to our sample, we can pass that through the sample, and then we can use a bent crystal afterwards, and we can then resolve the energies spatially from diffraction onto a CCD detector. And what that then allows me to do is actually tell you exactly how much of each energy has been absorbed by the sample as it passes through. And I can now obtain the entire X-ray absorption spectrum as a single pass through the sample. So now what we can do, so I'll show you, so again, that's sort of quasi-organic, but we followed the mechanochemical synthesis of the CYP8 compound by monitoring the zinc absorption edge. And now what we can do is we can actually follow the mechanochemical kinetics with 10-second resolution. So we now have a technique that we're just about ready to publish, but you can see the formation here with the formation of ZIF8 with this peak that's forming here in the Zanes region of the zinc edge. But we can now follow the redox processes in mechanochemistry at the same time resolution as the crystallographic information. So I think this is a brand new dimension in mechanochemistry that we're really excited to explore. And I do just want to shout out, I don't have data to show you, but we can also do this with purely organic compounds. So I hope that we can show you some data on that next time. So with that, I think I come to the end just by saying mechanochemistry really has been with us since the dawn of time. That said, we still really have absolutely no idea how these processes work. In order to do that, I am convinced that we really need to be continuing to develop these mechanisms, these methods that are going to produce new data to allow us to identify what these mechanisms are. And it's only in this way that we can really begin to develop ideas for how we can control these and really translate them into industry and hopefully achieve the IUPAC goal of changing the world for the better. So with that, a lot of people I need to thank, in particular Paulo Oliveira and Anna Bujanic, who've been helpful on the spectroscopy side, Julio Lampronti, Paolo Mazzeo, and Anna Bellinger from the diffraction side who've been heavily involved, and of course Helena Bolderiva and Franziska Emmerling who've been involved throughout the years in these processes. And with that, I thank you all very much for your kind attention, and I look forward to discussion.
Okay, thank you, Adam. We may have time for one or two quick questions.
Very nice, thank you. I wonder about the energy accumulation stage. I think that one of the options that is just roughening the surfaces and breaking small pieces. Now, you didn't explain, as far as I understand, this shape of the XRD, the double peak, the opening of a double peak. And I think I remember that this is a kind of a rainbow effect that you have from a large distribution, a broad distribution, you get divergence at the edges. And this also fits the effect of roughening, of significant roughening. So it's just a suggestion. Take a look at that.
So quickly, this here, you mean?
Yeah.
Yeah. So this we've mapped out. So this we know is actually results from scattering at different parts in the milling jar. So we don't actually see a change in the shape of this function.
This is from the jar itself? So
this is from a silicon standard in the jar. This is from nothing else. So this is truly just the fact that there's scattering happening from two very geometrically different positions in the jar. So we're actually splitting that Bragg peak geometrically.
Okay. And have you ever checked the roughness of what happens physically to the
So that's we're working on that now. Yeah.
Okay.
So hopefully in a few months we'll have something more to say to you.
Very interesting work, but as I pointed out yesterday, I think what you're dealing with is surface chemistry and thermodynamics, not mechanochemistry. And all types of our chemistries, thermal chemistry, electrochemistry, and so forth, the energy directly enters the molecular electronic modes. And in mechanochemistry, that means a shock wave going over a molecule. And that takes about 40 picoseconds on a much different time scale that you're working on. And I would argue that you should use different terminology like grinding chemistry or probably a diffusion-free chemistry.
So I mean, I fully agree with you, and I fully understand that. And there's been a lot of discussion. So we were just at the International Mechanochemistry Conference a couple of weeks ago, where this exact topic came up. And so there's the old mechanochemistry community who very much share that opinion, and then there's I think the newer community who's pushing towards generalizing the definition of mechanochemistry away from a pure mechanochemical reaction, more towards any transformation that is somehow facilitated by mechanical energy. It's a debate, and perhaps we can discuss it afterwards, but I'm very aware that the mechanisms are to be discussed.
Kevin Roberts, University of Leeds, lovely talk. Given that polymorphic stability is size dependent, and also it's pretty well known organic materials amorphize as you mill them, I was surprised that you don't do the pre-characterization of the mill of the reactants separately first to see how they behave under intense milling conditions, and then you'd be able to separate what's in the reaction and what's in the intrinsic materials property. Does that make sense?
So you mean you would mill independently each of the components to see how they behave and then mix them together?
I mean, if you can take a pile of alumina, titania, phthalocyanins, if you want to get the metastable polymorph, you mill it.
Yep.
So materials naturally change their polymorph because the balance between the bulk-free energy and the surface-free energy changes. Yes. I mean, that's how we make materials. So, so not to do that, wasn't aware whether you would be pre-characterizing the reactants individually.
We've done quite a lot of work, particularly with Anna Bellinger and Jeremy Sanders in Cambridge on this particular question in organic polymorphs. And it's exactly what we're seeing, that the characteristic polymorphs come out with very characteristic particle sizes. So we are working on that and trying to understand where the relation is between essentially the cause and effect in are we reducing the particle size and that's causing the transformation, or is it, again, as also been discussed, is there this non-mechanochemical process and the nucleation is happening, and then actually that's then leading to the particle sizes that we're seeing. So we're trying to figure out if it's sort of a chicken and egg question, and whether it's the mechanochemistry that's driving it, or whether that's just sort of hindering reaching a thermodynamic state.
Do you think that's related to the debate of stainless steel versus PMMA?
Sorry?
I mean, well, stainless steel's got a very polar surface of oxygen ions, and PMMA is enormously dispersive. Where Van der Waals interactions, I just wonder if that plays a role.
It very well could. And as I said, so these phenomena, I mean, the first time something like this was reported was last year. And there's only been 2 or 3 other examples that have popped out recently. So, it seems perhaps very naive, but I think for our community, it's very new phenomenon that we're really trying to understand. I mean, so we've done some work also in the stainless steel where we've added PMMA powder, and we don't see the same effect. So it seems maybe it's a bit more complicated than that. But we are working on it, but very early days for us to try to understand.
Thank you.
Okay, let's thank Adam again. All right, our next speaker is on her way up. It is Susanna Ward. She is the head of data and community at the CCDC. And so she manages the team that curates the CSD and also oversees the education and outreach aspects of the center. The title of her talk is Fun and Engaging Ways to Explore the Wonders of Crystallography Using the CSD. And so she's basically going to be sharing with us some of the details about their education and outreach activities and how they teach people about the CSD.
Okay, great. Thank you, Jason, and thank you, both of you, for organising this session and inviting me to talk. And special thanks to Panche and all the organisers. It's an incredible location. The sessions and the talks have been fantastic. And as my first ICOS, it's been really nice to meet the community, and it's been really engaging. So thank you very much. So as Jason said, I'm going to be talking about fun and engaging ways to explore the wonders of crystallography. And to do that, we're going to be using the Cambridge Structural Database. And we may also answer a few questions about chocolate along the way. So I am from CCDC, or the Cambridge Crystallographic Data Centre. We're a non-profit organisation, and our charitable objective is the advancement of chemistry and crystallography for the public benefit. One of the primary ways we do that is to curate and distribute the Cambridge Structural Database, or CSD for short. So that now contains over 1.1 million structures that have been shared by scientists worldwide. As we heard on Wednesday from both Kevin and Jessica, it also includes a CSD drug subset, and it also includes a couple of hundred electron diffraction structures. Alongside the CSD, we also produce scientific software, so that's really looking at enabling you to gain new insights from the data, and we engage in collaborative research, often in collaboration, so that's trying to help advance structural chemistry. What I'm going to be talking about today is our mission to promote crystallography for the public benefit. So we engage in lots of E&O activities globally, and how we communicate about what we do is really important. We want to try and do it in engaging, exciting ways, so we hopefully create a new generation of structural scientists. And we also want to help people discover an ocean of truth. So our founder, Dr. Olga Kennard, had a passionate belief that the collective use of data would lead to the discovery of knowledge which transcends the results of individual experiments. And in a lecture she gave at Birkbeck College in 1995, she also said that the great ocean of truth is still in front of us, and that we'll continue to discover new aspects of that truth. So I hope we can help you discover those aspects of truth, and I also hope the CSD can help answer a mountain of questions. So it can help answer things like, why are some tablets so big that they're difficult to swallow? And importantly, why has my chocolate bar become grainy and no longer snaps when I break it? So to take you on our journey of education and outreach, this talk is going to have 3 parts. I'm going to be talking about outreach and teaching, and then how we train others on the CSD, and then we're going to conclude by looking at some of the collaborations we have with our community. So first up is outreach. Our outreach activities really focus on engaging inquisitive minds. So we try and do this through things like science festivals, and we have hands-on activities using the wonders of crystallography. So here are some photos from the Cambridge Science Festival back in 2019. You can see some CCDC staff helping and some of the activities that we included. We also learned that if we can engage young minds to engage other young minds, it's really powerful. So this is Oliver Lightfoot. His dad, Matt, works at CCDC. He spent the day teaching people about one of our activities. And the next day, him and his sister demanded that Matt takes them to the Science Museum in London. So I think that was a win. The other way that we were engaging or trying to engage the public in structural chemistry was during the International Year of the Periodic Table. So we partnered with the British Crystallographic Association and the Diamond Light Source in the UK, and we created a periodic table linked to structures in either the CSD, the PDB, or the ICSD. Each of the pages about the elements and the structure were contributed from members of the community, so they drafted them, and I think the youngest contributor was probably 12, 13 years old, and it really did range in a varied number of contributors. Each of the pages was linked to and from other educational material to further learning as well. And to try and increase the engagement, we decided to add an element of competition. So we teamed up with the National Crystallography Service in Southampton to create a card game so people could learn about the elements and the crystals. This was featured at a number of Southampton science and engineering festivals, and the cards can be customizable, so you can add your own structures to them as well. In that journey, we learned that naming is really important, so this game would have been called Top Trumps. That didn't quite translate very well at the time, so it's now called Battle Cards. And we also saw again that everyone loves cats on the internet, and so even cats got involved in playing the game. Unfortunately, the pandemic meant that we had to do some virtual adaptions when the in-person event stopped. I don't quite know how to get these videos working. So we converted our battle cards to a filter on Instagram, so people could play on Instagram. And we also switched up our Science Festival activities to home learning activities. And each of these home learning activities had accompanying videos. So this is a video as part of our Crystal Adventures home learning activity set. And this was created by Tanya Menon, who is the daughter of one of our deposition coordinators. So she had great fun creating some crystals, and she even got her teddy involved too, which was lovely. So alongside these videos, we created some handouts. So this one shows or introduces polymorphism using Lego and chocolate. So we thought it was really important to try and use material that people would have at home, but we also know that everyone's homes are different, there's different situations, so making sure that the handouts were relatable as possible, and we had those accompanying videos if people couldn't get the resources. So in the handouts, they have step-by-step activities, guided questions, experiments, definitions, and to try and see whether people have learned along the way, they've got kind of fun activities, so they've got word searches and quizzes as well. So I mentioned that our Crystal Adventures home learning has got some videos. They form part of a wider portfolio of educational videos on our website. So we have videos and playlists that cover a range of different topics for a range of different school ages and undergraduate learning. They all have captions, descriptions, guided discussion, and subtitles. And you can see one of the videos here. So this is Introduction to Symmetry and Operations and Point Groups. This is one of our most popular videos on our YouTube channel, and it was created in collaboration. So a PhD student from Cambridge University created the video, Rosie Lester, and she then has gone on to create 3 other videos for us based on the periodic table. So one of the latest ones is Elements in Science Fiction. So we are on social media, but YouTube isn't the only social media platform we do. So one of our most popular features across our social media platform is Future Structure Friday. This started in 2012 with the aim to share with the community some of the latest insights from the database and to celebrate advances in structural science. It's kind of our way to promote and celebrate some of the amazing structures in the CSD in fun and engaging ways. And you can see some of the posts here, so we do try and tie it into some worldwide events too, so you can probably guess which events they were. We do see an increase in views to the underlying data too, which is really important. And so through that, we can see that crystal structures can be really powerful for teaching chemistry and science, and the CSD can play its part in that. About a decade ago, we collaborated with Greg Ferenc to create a teaching database. So this is a collection of 750 structures selected with educators for education. They're freely accessible, and they're carefully chosen structures to help teach about a range of subjects, so fundamental chemistry, symmetry, drugs, metal-organic frameworks, and lots of other subjects too. So these can be used to complement teaching. They've got nice visual examples from real life, and it can help aid practical exercises for students as well. If you're new to the teaching subset, then we've also got some inspiration and examples. So some of our collaborators have created teaching modules, and most of these employ the teaching subset. Over the last couple of years, we've been trying to engage more with some of our educators in the community to help kind of advertise what they're doing more. And we've created a CSD Educators series. So we now have 15 blogs and 15 videos featuring lots of people that I hope you recognize, including Jason, who gave a fantastic talk about the crystal growth competition. So this series celebrates the educators and gives them a platform to share their experience in STEM education, and in particular in structural science and their journey with the CSD. Importantly, it's also a space for other educators, so they can hear the stories from the community and be inspired as well. One of the contributors to our CSD Educator series was Mike Ziller. So Mike created the database of educational crystallographic online resources, or DECOR for short. That's a collection of crystallography lectures from different authors. And he started the project at Temple University, but then we started hosting them in 2020. So if you've got a lecture course and looking for slides, then it's a great place to look, or if you've got slides to contribute, then we'd love to hear from you. So that's outreach. We're now going to look a bit more about some of the activities that we do to train others in using the CSD. So first up on our website, we've got quite a lot of resources. So one of the things that we've got is self-guided workshops. These cover lots of different parts of our portfolio and lots of different software components, and they're step-by-step guided instructions. But we know that language can be a barrier, so we also make sure that we've got visual step-by-step instructions too. To complement those self-guided workshops, we've also got how-to videos, again, covering our portfolio, and these are bite-sized short videos, demo style, and help people learn how to use the CSD. But one thing we know is that some people like self-guided learning, other people would prefer in-person learning or tutoring. So we make sure that we are involved with crystallographic schools, conferences, and universities worldwide. So we have sessions to introduce the value of structural data and help users learn from the CSD and the CSD portfolio. One of the important things that we get from this ourselves is that we also better understand the needs of our global community too. Unfortunately, just like the science festivals, the pandemic put a stop to that. So we weren't able to meet people in person, but we did switch, like the rest of the world, to virtual events. So we missed the in-person interaction, but it did mean we had the opportunity to participate in more events, and we were able to reach more people in the world as well, which was fantastic. So we participated in external events, but we also created some CCDC-hosted events too. So one of these was our CCDC virtual workshops. We started those in 2020. We've since run 5 series of workshops, 16 different workshops, and they're all free. They're 90-minute sessions, they're hands-on, guided, and they all follow the same format. So show one, try one, and explore more. And we try and make sure that we maintain engagement, even though we're virtual. So we've got polls, we've got quizzes, and we've got competitions through the sessions too. And our next series is in October, if you've got any students that want to learn more. Through developing these workshops, it also meant that we could convert the content into on-demand training. So we now have modules designed to guide learning and enhance knowledge in our CSDU collection. So these are similar to our virtual workshops, but they're self-paced and available at any time. They follow you watch, you try, and you test, and you can get a completion certificate at the end. We've now got 4 modules with more in the pipeline, and our latest module is programmatic access to the CSD using the CSD Python API. So I have given a quick whistle-stop tour of outreach training and training in the CSD, and now we're going to move on to collaborations and community. But as you'll have seen throughout the talk, most of the things that we do are in collaboration with amazing individuals in the community. And if we go back to our mission is about promoting and advancing chemistry and crystallography for the public benefit. So it's important we try and reach as many people as possible. So to that end, in 2017, we developed the FAIR program. This supports research and education in over 80 nations through free access to the CSD portfolio. It's resulted in lots of publications from our FAIR users, and we've even started to see presentations at international conferences from our FAIR users too. It's growing in size, and I can't wait to see what comes next for our FAIR users. But it isn't just global activities that we do. We also routinely welcome budding and inspiring scientists into the CCDC, so to do PhD CCDC-sponsored projects, paid summer student projects, sabbaticals and placements, and we also welcome emeritus research fellows. You can see some of the outputs from these connections, and some of them often result in more E&O activity or resources as well. And I'm going to embarrass Cameron to say that he's also got a video on CSD subsets from when he was a summer student with CCDC. It's not just our users and individuals we collaborate with or build bridges with. We also collaborate with other data repositories. Our latest collaboration is with the PDB to create a card game called Bound. This is a protein drug binding game. It has a card deck of 60 slides, 6 different categories, and 3 pairs. So we have bacteria and antibiotic, virus and antiviral, and cancer and anti-cancer. And it's really designed to leverage structural data for educational purposes and is designed for about age 12 and up. Alongside the playing cards, we also introduce protein drug binding. We introduce the cards themselves. There's instructions on how to play the game, bonus memory games, and each card links to additional web resources, both hosted by us and the PDB, to really further learning. I do have some cards. If anyone wants to see the cards later, I would be happy to show you. I can't do any card tricks though, sorry. Okay, so I've talked about a lot of different resources and activities that we've been involved with. So I just wanted to give a shout out to where you can find more information or you can find the resources themselves. So on our website, if you go to our website and then go to community and then you go to training and educational resources, you'll see our resources in 3 main categories. So we have software training, we have teaching and learning, and we have our outreach activities. So do check it out if there's anything of interest. So we've hopefully taught others something along the way, but we've also learned a lot too. So we've learned that crystallography and structural science is an incredibly powerful tool to engage students in science. But we know that there's no one way to learn or to teach. So we need to be adaptable. We've learned that virtual events and resources provide new opportunities, but we also still think it's important to engage in person when we can, particularly when there's views like this. Most importantly, we've learned that we are so incredibly lucky to have such an amazing, vibrant community that collaborate with us and that continue to inspire us. And I know you're all waiting for the answer for the question, why has your chocolate bar become grainy and no longer snaps? Obviously, the answer is in the structure and is due to polymorphism. So just like ritonavir, we can see that for chocolate, solid state is important too. So with that, I wanted to thank you for listening and thank everyone that has contributed to these resources over the years. Thank you.
Thank you so much. All right, we have time for a couple quick questions.
Not a question, I'm Maggie Lingenfelder from EPFL. It's more like thank you, because I think these activities you are doing are really important for the community, and I'm really amazed to see everything you do. And the question is more like, how can we collaborate if we want to support these activities?
There's lots of different ways you can collaborate. Just speak to me afterwards, and I would say the thank you is lovely, but all of these activities are often done in collaboration, so it's really a thank you to the community. So I look forward to chatting about how we can collaborate.
Sure, thank you so much. Really nice presentation.
Okay, if there are no other questions, I'll just really quickly also say thank you. That is really, really a great talk. And so let's thank Suze one more time.
Okay, our next speaker is Christian Goeb from Rigaku. He's an application scientist, and he's been there since 2019. His background is in supramolecular coordination chemistry, and he'll be telling us about electron diffraction with their new instrument, Synergy ED.
Thank you very much for the nice introduction, and thank you, organizing committee. Panche, it was a very lovely conference. It is nice to meet in person again after this long online conferences that we have. Yeah, so as you know, we have a new toy in our fleet. Yeah, so the Synergy ED, this is what I will talk about today. I try to keep it a little more on the instrumentation side today. Yeah, so it's very rare case that we can see all instruments along next to each other. Just to summarize from where we came earlier is basically the fine focus seal tube instruments, the Crystalab Mini with a molybdenum source. It's a benchtop instrument. It is often used in teaching, but also you can do very nice crystal structure analysis with it. It takes rather large crystals, 300 micrometers. So the goal for us is basically there is a barrier from where we cannot measure single crystals with X-ray diffraction anymore, which is around 1 micrometer, basically. Those can still be measured on the strong rotating anode sources that we have. For the electrons, basically 1 micron is the upper barrier. We heard it today a couple of times. X-ray diffraction and electron diffraction are complementary techniques, and it is very nice to combine them together for powder applications, for instance. Just to give an example how that the size difference basically is going from a crystal that is like 300 or 400 micrometers. The comparison could be Lake Ohrid. The length of that lake is like 36 kilometers, and if we look at a crow's boat that is 25 meters, this is roughly the size of the crystals that we are looking at. Yeah, in the middle of 2020, Rigaku teamed up with Carroll. They are even older company than we are. So they have a great expertise in electron microscopy, and our instrument is based on one of their TEMs, but it's optimized for diffraction condition and not for the imaging. Yeah, we combine it with our Hypix detector, an HPAD detector optimized for electron diffraction, and everything is driven together by using Chris Alice Pro. Yeah, the hardware looks like this. It is a column from Carroll, 200 kV lab 6 source. The optics are optimized for electron diffraction purposes. The Hypix ED is optimized for electron diffraction. It is radiation hard. Our colleagues in Japan use it already since 2 years without a beam stop. It works very well, tiny pixels and no dark currents in it. Yeah, the sample stage, you can move it in X, Y, and Z direction, and of course you have a tilt axis. Cryo option is available if you want to do low temperature measurements to reduce the radiation damage that you have. Yeah, Chris Alice Pro just allows the operation of the electron diffractometer. And what are the basic differences that we have when we look on a traditional TEM? Basically, everything that distorts the beam strongly has to be removed. So what we did, for instance, in a standard TEM, you would have like these condenser lenses here that are removed, and the goal in the end is to have a very nice parallel beam around your sample. Yeah, so the lenses are adapted. We have a high contrast pole piece, and in the end, we have a very parallel beam. The switching between the settings for imaging and diffraction, they can be switched very fast. And it's very stable, and of course you have a high rotation angle, plus minus 90 degrees. Of course, when your sample holder stands vertically, you have a shadowing from your grid. So effectively, you can use maybe something like plus minus 60 before you see a shadow. Ute Kolb already introduced this very nicely. So in principle, you have your filament or lab 6 for us. The lens system here is omitted. You have the electron beam in purple here. You have a CL aperture that cuts down the beam. Then you illuminate. This is a little over-exaggerated. Maybe the beam is not that big. You illuminate multiple crystals. Of course, you get multiple diffraction from this. So what you then do is you have another aperture and a selected area aperture after your diffraction, and you select basically from which grain in the end you want to have your diffraction. Yeah, and this is how it looks. If you only have the CL aperture in place, you have quite a wide field that you illuminate. And when you change to the diffraction mode, the SA aperture comes in, and you only see diffraction from the single grain that you have. We sample preparation. We had it a couple of times. If the crystals are large enough, you should go for X-ray diffraction, or you grind it down. What we normally do is we take just 2 microscopy slides with the powder in between, slide them along, and then you can either just tap your grid into the powder, or a nice way is also to put them in a small Eppendorf vial, shake it, and then remove the excess powder that is on it. On the right-hand side, you just saw like how the sample holder is removed from the stage, and now it goes back in. You put it in, switch on the vacuum, pump it down, like in a regular microscope. How does the actual scanning look? So right now we are in the visual mode. Basically, it's point and click in the end. You center on your sample, make a slide, or check first, does it diffract at all, yes or no? Then you tilt your sample and recenter it to align for the Z height, in principle. So this video is double speed. If your sample is sensitive towards radiation, you can either put a beam blank in between, or you measure at low temperatures. Correct. Yeah. So when the sample is centered, then there is just one button here on the bottom. It says diffraction experiment, and then you set it up like any other data collection in Chrysalis Pro. Elements must be given the scan angle, in this case, exposure time, and then basically it goes. The pipeline that we have for X-ray diffraction also works here, of course. Chrysalis will index your reflections and integrate them, find the unit cell, and at some point AutoChem will start with the structure solution. And this all runs in parallel, and a single data collection does not take longer, much more than 3 minutes or something like this. The most time you will spend on data processing in the end. Yeah, so almost finished. So in a second we should see here tyrosine coming up. Yeah. Correct. So in the background runs shell XT, shell XD, XE. You can also have a charge flipping. Yeah, so it's anisotropically refined, hydrogen atoms are attached, and so on, as you would do it for regular single crystal experiments. How beam sensitive are the samples typically? So this chart was taken from Lukas Palatinos during the last IOCR. In principle, the dose that you apply to your crystal throughout the measurement is something around 2 electrons per square angstrom. And of course, the dose rate can be adjusted on the instrument. It's variable. In Chrysalis Pro, we have a plugin that allows you to merge data as well. It's a very simple interface. Normally, you would go for, you should compare a bit the unit cell parameters. From here, it's already very simple to find outliers. Other indicators would be looking at I over sigmas, R-ins, and other data quality parameters. Just add them to a list and then make a composite data set that you again have to scale. To get above 80% completeness, normally we merge 2 to 3 crystals. In triclinic case, orthorhombic normally already has good completeness for structure solution and refinement. Hydrogen atoms also come out very well as you see. The problem is sometimes you are not able to get full completeness of your data set. This is due to the fact that sometimes your plate-like crystals, they just stay flat on the grid. So a nice paper on how to get rid of preferred orientation is from Tim Grüne in Nature Communications. Basically what he does is he just takes a brush and brushes over the grid. And then the carbon film just coils around and you have crystals in various orientations. Yeah, so since we do the collaboration with Geol, we have now 209 measurements. And the majority that we have is basically triclinic, monoclinic, and orthorhombic. And most of them are either organic or organometallic. So this goes into MOF chemistry, coordination chemistry, organic compounds, APIs, salts, co-crystals alike. As you see, we have unit cells with quite a lot of atoms in them. Also, the unit cell axes are quite long. Because we have an adapted lens after the sample, we could, in principle, change the virtual camera length. So we are not limited, I would say, up to 500 angstrom in unit cell, what we can do. Probably more is also possible. Yeah, R factors in the refinement later on, if you come from the X-ray diffraction side, you have to adjust yourself a little bit. Generally, they are higher, of course. And dynamical refinement is a good thing, but it's time-consuming, of course. Depends on the question that you have on your analytical problem. Yeah, elements that we analyze basically from all rows, we have it already. Lanthanides as well as transition metals. The samples are generally, they are MOFs. They can be small molecules, APIs, chiral compounds. One of the very nice applications is when somebody is looking into pesticides or metabolites where you generally have very little sample content. Yeah, coordination complexes, battery anode material, inorganic solids, this is all possible. And I want to highlight one of the publications that we had with a customer, Neil Champness. He does this rotaxane chemistry. Molecular weight is roughly 3,500 Daltons. And I just want to highlight that in principle, it was possible with the electron diffractometer to outcompete the diamond light source in principle. So you may see that I/sigma is much better for the diamond light source, but also the resolution is different. In principle, when the structure came out from diamond light source, a lot of restraints needed to be applied, like defixes, SADI or flat. On such a large molecule, it's basically unavoidable, probably, if you measure from diamond light source, but in our case, only same distance restraints were needed. Yeah, furthermore, PF6 was completely missing. They did not see the anion, but we could show that actually the sample is charged. Another thing, so last week the installation of Synergy ED at our office was completed. It's up and running, and you are welcome to see it and test it, of course. What challenges do we still have? I said already, dynamic diffraction is difficult. Absolute structure determination can be done, of course, but one has to be a little sensitive towards what they are doing, so dynamical refinement is needed. In Chris Alice, we have a button. We can transform the frames into TIFF images with proper headers that can be read into PETs. And after integration in PETs, one could do the dynamical refinement in YANA. Yes. So how does that look? If you take a commercial sample of L-tyrosine and refine it dynamically, you get a very nice R1, below 10%. If you take the other handiness of the molecule, you see it's 12%, and that's in principle how you would determine which handiness is correct in your sample. And with this, I would like to thank you again. You are very welcome to talk, ask questions. Thank you very much.
Okay, I think we probably have time for a couple quick questions.
Thank you very much for your beautiful talk. So 3D ED electron diffraction method is very nice. So I would like to know the reliable R factor for as a value as a guide for ED. I mean, for example, R factor is 20% is okay for ED method.
Probably this is something that we observe. Yeah, as you may remember, let me just bring up this one chart here one more time. So we middle out around the 0.2, as you see. R factors are not really reliable to my knowledge. So I process a lot of data sets. I did not find yet when it's very good. The thicker your crystal, the stronger will be the dynamic effect on it. So thinner crystals tend to have smaller R values in the end. Yeah.
Nice talk, Christian. Thank you. What are the requirements, or are the requirements for data quality different for dynamical refinement as opposed to kinematic?
Mm-hmm. So dynamical refinement you can only do on single grains, right? The better the single data set is, the better will be your dynamical refinement. Right. Yeah. I would say if you want to do dynamical refinement, it should be a thin crystal, so the dynamical effects are not strong. Yeah.
Okay. Thank you.
Mm.
Okay, if there are no more questions, let's thank Christian again. Okay, and as was mentioned by my wonderful co-chair Tom, we have one additional talk this afternoon. This will be Christian Yandel, who from Eldeco. Is that right? Probably, maybe. We'll find out. Eldeco, and he will be speaking on structure determination of nano-sized crystals using electron diffraction.
All right, sorry for the small technical difficulties. So yeah, first, thanks to the organizers for this great conference and the opportunity to speak here. So I do not want to bother you with too much details about the company that I work for, which is Eldeco. So we are all centered around electron diffraction. We have designed our own electron diffractometer and now offer all kinds of services around this. Of course, we have some great help in this from our scientific advisory board, who we are very grateful to, among others, Ute Kolb, who we have already heard today. As there have been quite a few talks about electron diffraction, I want to keep the intro very short. So we've already seen this, the material science tetrahedron, and basically all items that we see here are ultimately connected to structure, which is why we all are so interested in structure determination. Now, why ED for structure determination? So just a very quick remark to the terminologies. People use ED, micro-ED, and 3D ED more or less synonymously. Some people will disagree, But yeah, I think that's fine. So yeah, the main reason for using electron diffraction is, of course, you can measure crystals much smaller than anything you could ever measure with X-rays. And this does not only mean you have access to crystal structures you could not ever get with X-rays, but you can also sometimes shortcut the crystallization process, measure a product right away out of the synthesis as a powder, and don't spend months or longer trying to get crystals of suitable size. All right, so how does the instrumentation look like? We've already seen this. So you need an electron source, you need a way to rotate your crystal, and you need some way of detection. So how most people are doing this, they take a transmission electron microscope where there's already a beam, then add a stage to move the crystal, and usually you have to add a special detector because the imaging detectors are not ideal. How would this now look if you design an electron diffractometer from scratch? So now this here is the LDCO design. So again, it's basically inspired by a single crystal X-ray diffractometer. So it is now a horizontal beam. We have a lanthanum hexaboride source, like most people use, some electron optics, and same as on a single crystal X-ray diffractometer, we have a goniometer, which gives us 4 translation movements and also 1 rotation axis. So it's basically phi scans, which we also do in single crystal X-ray diffraction. Then there are some custom attachments possible, like cryo, for example. And in the end, of course, you need detectors, so detectors for imaging, and also a detector for diffraction. And in the end, this is, of course, all processed by software. So sample preparation, all you have to do is basically disperse a powder on a standard TEM grid, which you then can, in the device, move to any place. You can center any spot on this grid and measure the crystals there. So we use STEM imaging, so scanning transmission electron microscopy, to have as little dose on our crystals as possible for imaging. And then you simply navigate with these pictures to the crystals you're interested in. And yeah, can measure them. So here are just some screenshots. So the standard procedure for a measurement would be you look for a promising crystal, you can take a single diffraction image and assess the quality of it. Is it single crystalline, maybe twinned, maybe polycrystalline, and then you would move on. If this diffraction image looks good, you would center the crystal so it remains in the beam during the whole rotation, during a continuous rotation measurement, and then you can start the measurement. So you can go up a maximum rotation angle to around 160 degrees, so minus 80 to plus 80. Above that, you will always hit the grid, and you only also get these 160 if you're pretty lucky that your crystal is exactly in the middle of a mesh, so you don't get shadowing by the grid. But 120 is easily doable in most cases. All right. So I could show a video here, which I will skip for the sake of time. If you're interested, feel free to come by, and I can show this to you. Now let's look into some interesting examples. So one publication that was at the beginning of, I would say, the new era of electron diffraction by Tim Grüne from the PSI. So what they did, they modified a transmission electron microscope, turned it into an electron diffractometer, and this took them around 2 to 3 hours. Then they could just simply take powder from a commercial capsule, measure it in the matrix, and determine the crystal structure and the polymorph of the API that was present, so in this case, paracetamol. So next advances, so this is already from a dedicated electron diffractometer. So it's also just from a measurement from one single crystal in continuous rotation mode. But now the setup time of the device is drastically reduced to just a few minutes. And measurements in generally are very quick. So in this case, it was only 60 seconds. Sometimes you might need a few minutes for one scan, and a total rotation around 120 degrees. Get pretty accurate unit cell data. And then, of course, can also solve the structure. This is metaxalone. It was from the very early days of LDCO. So yeah, the R factors are not great at this stage, but the instrument has much been improved since. So if we now go to some real applications, so this is work we did in cooperation with Mihaela Popp from TerraCrystal. So we were looking for a new polymorph of fibuxostat. 2 are already known, and we were indeed able to find a third one. We determined the structure both by X-ray diffraction and electron diffraction. Of course, the main advantage of electron diffraction is you could take a particle directly from the vial, and it worked. Whereas for single crystal X-ray diffraction, it took more than 1 month to grow crystals of suitable size. So this is a significant acceleration in structure determination. Here on the bottom right, you see an overlay of the 2 structures, so they are virtually identical, thus proving that electron diffraction does indeed give reliable structural results. Another interesting thing about electron diffraction is you can select single particles in a mixture. So this is very nice if you want to identify impurities in phase mixtures, which can be very challenging by powder XRD because of the overlap with your main species. So in this case, it's a pharma sample. Unfortunately, I cannot show the API. But yeah, we noticed there's some crystals with different morphology, also different diffraction patterns, looking a little bit fiber-like. And indeed, we also found a very suspiciously small unit cell and could identify this as a polyethylene contamination, which probably got in somewhere in the production process. Also, another sample. So these were pentacene nanocrystals. So we measured a small bunch of them. Most of them, we found the standard cell expected for pentacene, so this is the literature-reported structure. But we also found 1 crystal with a different unit cell and could indeed solve the structure. So this is pentacene dione, so an oxidation product. Now, something that is unique for electron diffraction, you can actually get localized information from your samples if you use the lateral resolution of your beam. So the smaller your beam in this case, of course, the better your resolution will be. So this was all done by one of our advisory board members, Mauro Gemmi. So for example, if you have mineral samples, this is a very nice tool to select certain grains. If you have intergrowth, it might also be very helpful if you have micro-twinning. And of course, if you have crystals with a little bit of impurities on them, you can always just select the best spot of it. So an application example of this is the structure determination of orthocetamol, so an isomer of paracetamol, which has been known for a very long time, but the structure has not been known, well, until recently, when it was solved with electron diffraction. So the issue in this case is it just doesn't want to form nice single crystals. You always get an intergrowth of small domains, but if you have an electron beam, you can just select 1 small single crystalline area, and then the structure solution is rather straightforward. Okay, something that has been touched already is absolute structure determination. I cannot go into too many details here. So there was a joint webinar with Lucas Palatinos. If you're interested, I can make the link available to you, so just contact me. Via dynamical refinement. So this is different from the classical method of using the 3DL pass and determining a flag parameter. If you do it with dynamical refinement, it's actually based on effectively using multiple beams, because every diffracted beam acts as another primary beam in dynamical diffraction. And thus you can just determine the enantiomers via the R-value difference. So this is an example of arioterone acetate. So the very cool thing about this is it is very robust. So even if you just take the rough primary solution that you get for the structure, you always already get a significant difference in the R values. Of course, it gets more significant if you proceed with refinement, get a more refined model, but you already have the right solution from the beginning. And yeah, if you do it with several runs from the crystals, you definitely see variations, but it is pretty consistent. So this means you can actually shortcut for very complicated structures where dynamical refinement is prohibitively time-consuming. So you could just take a kinematically refined model, keep the structural parameters fixed, and then only find the specific parameters for dynamical refinement, which is what we did in this simple histidine example. And even if we do this, the structure refinement is very quick in this case, and we still get a significant difference, so 2% in the R1 value, around 4% in the weighted R2. Okay, another application example. So MOFs can be tough to crystallize because the crystallization happens already during synthesis, so you won't always get crystals of suitable size for X-ray diffraction. So here's just one example. ZIF8 is of course already known, but you get a pretty nice structure. Despite the limited resolution of just 1.2 angstroms, we could refine it to an R value of around 12%, which is pretty nice for dynamical refinement. Another important application can be the location of hydrogen atoms in co-crystals, because you're often interested if it really is a co-crystal or a salt in pharmaceutical samples. So we've seen a nice example already from Jessica. So we have a rather similar outcome here. So unfortunately, I cannot show the API because it's confidential. But anyway, the important thing here is the fumaric acid. We can see a clear positive residual electron density. And we can indeed do a free refinement of the hydrogen position in this structure, get a reasonable U-iso. Of course, we don't get a very accurate bond length in this case, but I think it's pretty all right for just kinematical refinement. And as an additional confirmation, if you look at the packing in the end, you will realize that this is the only position that makes sense for hydrogen bonding, so this is always nice as an additional confirmation that you did everything right. Okay, now as a final example, because there are always some concerns about the quality of electron diffraction data. So we asked ourselves, how good can a kinematical refinement be in the end? So we took this example of triphenylbenzene, which is already like medium-sized organic compounds, and tried how low we can get it here. And with our best data set, we were indeed able to drop the R1 value below 10%, which some people kind of consider as the sonic wall for quality, at least comparable to X-ray data. So yes, I hope I could have convinced you that there have been great advances in electron diffraction instrumentation and also data evaluation in the last years. If you compare it to the example of Ute Kolb, when it took a whole PhD for just one single structure. So it is a lot easier now, a lot more accessible, and the results are, of course, also a lot better. So I can highly recommend that you try it out. And with this, I want to thank all our collaborators, and I want to thank you for your attention.
Okay, are there any questions for Christian? Oh, there's one.
Very nice talk. You showed some nice work by Marugami with the small beam and looking at different microstructures. How big is your beam, and was that work done on an Eldeco instrument or Maru's microscope?
Yeah, so this is one of the examples that was not done on an Eldeco instrument. This was done by Mauro Gemmi on his TM. So we currently use a beam of 750 nanometer size, but we can go lower if it is necessary.
Is it on? Oh, yeah. Could you go back to that slide where you compared the, I think it was the enantiomers, the R values?
So the histidine one or the example?
Yeah, that one. Maybe I missed it, but I didn't quite understand. So you've got different experiments that you did. So were those separate experiments?
Yes. So whenever you do an electron diffraction experiment, you usually measure multiple crystals. Because it might be necessary to merge data in the end. So you just want to make sure you have at least one good data set and other data sets to add if your completeness is not high enough from just one run. But you have to be careful. You cannot merge data for dynamic refinement. So these are all different crystals from the same batch.
Yeah, it's just, so that's random sort of error that you're getting from the R values, right? But they seem to follow the same trend. So I just wanted to know how is it following the same trend for a totally random selection?
You should not really look at this trend. It's just different experiments. Of course, some give better R factors in the end, some give slightly worse R factors in the end. But the important thing is that there's a significant difference between the two enantiomers in all of the cases.
Okay, thanks.
thank you, Christian, for this nice talk. With regards to the location of the hydrogen atoms, have you tested how far your method can do when you have a partial proton transfer between two molecules?
So unfortunately, we have not had a nice example to test this for, but it's something I would be very interested in trying out.
Okay, well, thank you very much. Let's thank Christian one more time. And that's going to conclude the crystals and methods session for this afternoon. We have 2 great plenaries coming up, so everyone get ready. And one quick announcement, if you were a speaker in the crystals and methods section, after the second plenary, please come up to the front so we can take a nice group photo. But otherwise, on to the plenaries. Thank you. Yeah, let's thank all the speakers in today's session once more. Thank you.
So, my name is Consiglia Tedesco, and it's an honor for me to introduce you Professor Masako Kato. And Professor Masako Kato graduated the Department of Chemistry at Nagoya University, and she obtained the PhD from the same institution. Later on, she worked at the Institute of Molecular Science and also at Kyoto University. She joined the Department of Chemistry at Nara Women's University as an assistant professor in 1989 and was promoted associate professor in 1996. From 2006 to 2021, she had been professor at the Faculty of Science of Hokkaido University. And in April 21, she joined the Kwansei Gakuin University, where she actually works. And while being emeritus at the Hokkaido University, she will talk about photofunctional soft crystals based on platinum complex. And now, with no further ado, I would like to invite Professor Kato to show her beautiful work.
Thank you very much for your kind introduction, Professor Tedesco. I'm Masako Kato from Kwansei Gakuin University. First of all, I would like to express my sincere thanks to Professor Naomo for the kind invitation to this nice symposium. And I'm very happy to have this opportunity to visit such a fantastic place of Macedonia. So, thanks to the organizers' nice arrangement, I had a good time here and wonderful experiences. To be honest, this morning we Japanese took a PCR test here, because we need the certificate of PCR test negative to get back to Japan. So we have just received the results, all negative. So we can go back to Japan, maybe tomorrow. But we lost the reason to stay here. Okay. Anyway, it is my greatest honor to deliver a plenary lecture here. So, so thanks so much, Spence. Okay, so today I would like to talk about photo-functional soft crystals based on platinum-2 complexes. And in this symposium this week, I heard a lot of nice organic crystals that have flexibility and stimulus responsiveness. So I learned a lot about soft crystals. And in my talk today, I'd like to focus on the photo-functional soft crystals. And my talk, studies in my talk today have been done with my collaborator with Hokkaido University because I moved to Kansai Gakuin University from Hokkaido University last April. So my talk is almost my talk. Most of my talk is for what have been done in the Hokkaido University. Okay, so this is the outline of my talk today. First, I would like to introduce our soft crystal project in Japan. We have promoted it for 5 years. And next, I'd like to talk about photofunctional soft crystals based on platinum-2 complexes. My group has developed in the project. So these are divided into 2 parts. One is the platinum complexes exhibiting assembly-induced luminescence. And the other one is luminescent platinum complexes controlled by counter anions. Okay? So let me start with the first topic. What are soft crystals? We use the word soft crystals for the one of Kakenhi project for scientific research on innovative area supported by Japanese government. This was a 5-year project. We started it in 2017, and we have just ended in the end of March, this March 2022. Fiscal year, the end of the fiscal year of 2021. Okay, so we developed, we promoted the project intensively to develop soft science and photo functions of flexible response systems with high order. Okay, so more specifically, what are soft crystals? I think the participant in this symposium, the word is not surprising at all because organic crystals or molecular crystals are essentially soft and flexible compared to the inorganic materials, metal crystals, or covalent crystals such as diamond. So, but I'd like to show you our soft crystals. As I said, we focus on the photo function of the soft crystals. And here I'd like to show you our movie on soft crystals. I think it is convenient for you to get an overview on soft crystals quickly, better than my explanation. So it's open on YouTube, but please enjoy the movie for a while. It's a 10 minutes movie, okay? So let's start.
These are novel functional materials that have a high structural order, like crystals, and a response to gentle stimuli, like liquid crystals. These materials are key to exploring new frontiers of science, and they are called soft crystals. In 2002, a new platinum compound was discovered. The crystal structure of this compound is changed on exposure to alcohol vapor and reverts by chloroform vapor, showing remarkable luminescence changes. This behavior is called vapochromism. The gentle stimulus of vapor induces the color change by the change in the interaction between platinum ions. In 2008, mechanochromism was discovered in a gold complex whose luminescence color was changed by a gentle grinding stimulus. The mechanical stimulus induces an interaction between the gold ions, which provides a crystal amorphous transition. In 2013, a new material was discovered whose crystal color changed when it touched another crystal. In 2014, the superelasticity of an organic crystal was discovered for the first time. In 2016, the shape memory effect was discovered in an organic crystal whose shape could be recovered by heating. Vapor, mechanical force, heat, and others. In this materials group, microscopic structures can be changed by gentle macroscopic stimuli, accompanying visible changes in color, luminescence, and/or deformation. Liquid, gel, liquid crystals, and crystals. As the structural order increases, structural changes tend to become difficult because the activation energy increases. However, the group of materials we discovered shows phase transitions by gentle stimuli, while the structural order is maintained. We named these materials soft crystals. Various soft crystals have been discovered, some by Japanese researchers. Researchers from various fields have formed an interdisciplinary research group to develop a novel scientific area. This project focuses on 3 aspects, which include the development of soft crystals through molecular design and synthesis, soft crystals with a novel structure and morphology, and soft crystals with superior physical properties and functions. Researchers are actively conducting collaborative research. In recent years, our group has discovered new soft crystals. The superplasticity of an organic crystal was found for the first time. Fluorochromism of a superelastic organic crystal was also found. Phase transition experiments were conducted by the mechanical stimulus of cutting single crystals in a vapor atmosphere. We confirmed a thermosalient phenomenon in which crystals jump by decreasing or increasing the temperature. We are analyzing the crystal packing structure and conducting research on intermolecular energies. We are attempting to understand the soft crystals phenomena by using scientific approaches. Using a high-energy accelerator, the molecular structure changes were analyzed by synchrotron radiation X-ray and pulsed lasers. X-ray single crystal analyses were conducted by rotating single crystals that showed a strong luminescence. And in a platinum complex, real-time observations were performed for the transition from amorphous to single crystal in ethanol vapor. Vapochromic crystallization of the platinum complex was analyzed by super-resolution structured illumination microscopy. The time dependence of a single particle was monitored in 3 dimensions to elucidate the mechanism. A new luminescence measurement system that grinds samples by rotation was developed to evaluate the mechanochromism quantitatively. Theoretical calculations were undertaken to understand the mechanism of superelastic organic crystal phase transition in detail. By using molecular dynamics simulations, we theoretically predict phase transitions that can store and release electricity through heating and deformation. We are creating new functions by using soft crystals. For the vapochromic platinum complexes, luminescence was controlled over red-blue by changing a substituent on the ligand. The vapor-induced single crystal to single crystal phase transition was realized and the dynamics were evaluated. Luminescent molecular crystals contain rare earth elements such as europium or terbium. Luminescence can be seen by dropping a steel ball onto these crystals, which is called triboluminescence, in which the force of exfoliation of molecular layers is converted to luminescence. By heating a stable dioxetane crystal, we achieved a crystalline state chemiluminescence, which has the same chemi-excitation process as firefly bioluminescence. We are conducting research to convert heat to luminescence energy in crystals. We developed solid-state chemical reactions using mechanochemistry. Without solvent, organic synthesis was achieved by heating only. In diamonds, the crystal lattice size is approximately 0.1 nanometers, and diamonds are extremely hard. Molecular crystals have a lattice size of approximately 1 nanometer, and thus they are soft. The softness is enhanced with an increase in lattice size, but it is difficult to form the crystal structure. We succeeded in preparing crystal structures with a lattice size of 100 nanometers. Various structural colors can be achieved with gentle pressure. We are targeting a technological innovation based on the properties of soft crystals. By using a ruthenium complex hybridized with DNA, a quick response electrochemiluminescence device based on alternating current driving was developed. We are developing soft crystal-based applications. Compared with hard crystals, which have strong bonds between atoms, soft crystals have weak molecular interactions, and thus the phase transition energy is small. Furthermore, compared with soft materials such as liquid crystals, soft crystals show a high structural order. We are creating a new scientific area of soft crystals by combining new findings and knowledge. Our group is active internationally. We held an international symposium in 2018 and 2019. One of our young researchers went to Belgium and developed a new measurement system to observe molecular behaviors in response to a rotational stimulus. Another researcher studied in the USA and identified the mechanism that links molecular rotation in crystals with luminescence. In this new scientific area, through flexible collaborations between researchers from various fields, we aim for creative innovation. Soft crystals will be new science.
Okay, thank you. Did you enjoy the movie? I hope you like it. In the movie, there was a cut of Professor Alicia Garvey's laboratory. Thank you for your cooperation. I appreciate it. And so in this slide, I summarized the characteristic phenomena of the soft crystals. And the point, soft crystals, yeah, you heard already, but the point is that we developed the material. Soft crystals exhibit that remarkable visual changes such as color and luminescence in response to gentle stimuli, including the vapochromism, mechanochromism, superelasticity, and so on. So we have developed such a kind of materials in this project. And next, I'd like to talk about our recent achievement in my group. So those are mainly platinum to complex, luminescent platinum complexes. Okay, so let me move on the second part. From here, our study, our work, okay, my work. So that is the platinum to complexes exhibiting assembly-induced luminescence. And the invariant platinum complex adopt square planar geometry, and the complexes exhibit characteristic luminescence when they are aligned. So by using this property, we developed various luminescent and chromic platinum complexes. As a typical example, I'll show you that simple platinum complexes pairing bipyridine and 2-cyanide ligand. The complex itself is colorless and non-emissive, but the complex units are stacked like this. The red crystals are produced, and they exhibit intense red luminescence. For the red form, platinum-platinum distance, as you can see, is found to be 3.34 angstrom at room temperature, which is short enough to generate platinum-platinum electronic interactions. And interestingly, the color change occurs from red to yellow on exposure to water vapor. As you can see, the little bit deformed structures, stacking structures for the red-yellow form. Water molecules are included here and here. And yellow form reverts to the red form by releasing water molecules. So this is a phenomena of vapochromism. Vapochromism is known as a phenomenon of reversible color change induced by gas or vapor. The phenomenon has attracted much attention for the easy sensing of environment. And I think the vapochromism is also scientifically very interesting because it is the emergence of the interaction between solid and gas. And the vapochromism becomes much more attractive if the luminescence color change occurs, like platinum complex assembly. So, the origin of the color luminescence of the assembled platinum complexes can be roughly described by this schematic MO diagrams. When the platinum complexes, two platinum complexes are stacked with short platinum-platinum contact like this, the overlapping of these square orbitals should generate large splitting MOs, D sigma and D sigma star. As a result, D sigma star becomes a HOMO, and the transition from the D sigma star to pi star orbital of the ligand occurs in the visible region as MMLCT transition, metal-metal to ligand charge transfer. And of course, the emission can occur from the triplet, corresponding triplet MMLCT state. And from this diagram, you can see the MMLCT transition energy decreases with the increasing platinum-platinum distance. This means you can control the color sensitively by changing the platinum-platinum interactions. But unfortunately, the color region is not so large for this type of self-assembled system. Usually red to yellow, or at most red to blue. Red to green, red green. So in order to improve the color tunability as well as emission efficiency, we have developed a new series of platinum complexes recently using the N-heterocyclic carbene like this. So we have the various colored intense luminescence of red-blue color were obtained, synthesized. And by changing the substituent R is important from methyl, ethyl, isopropyl, and tertiary butyl. So the point is all the complexes exhibit triplet MMLCT emission with very high quantum yield, more than 0.5 at room temperature. So this slide shows the emission and excitation spectra of the complexes. All four complexes exhibit non-structured emission spectra, and we can assign these spectra as emission from the triplet MMLCT state. Particularly, the blue for tertiary butyl form is remarkable for the blue triplet MMLCT. This is the first example of the blue MMLCT. And in fact, you can see a structured emission spectra from the triplet pi star state for the dilute solution at 77 Kelvin. So this is completely different from the solid state emission. And these results indicate the alignment in the crystal is very important for the color control. This shows the crystal structure of these complexes. you can see a stacking structure for all for complexes. But structural manner are a little bit different each other. If you take the averaged platinum-platinum distance, the increasing PT-PT distance can be observed from metal, also methyl, ethyl, isopropyl to tertiary butyl substituted form. And it's very corresponding to the color change. So to investigate further the softness of the crystals, we next measured the temperature dependence of emission spectra. And as shown here, four complexes exhibited a little bit different features. For methyl substituted form, you can see a large red shift with decreasing temperature from room temperature to 77 Kelvin. This tendency, this trend is normal for the triplet MMLCT emission. And you can see similar but smaller red shift were observed for ethyl substituted form and isopropyl substituted form. But in the case of tertiary butyl form, there are no emission spectral shift was observed. So the question arises, why do those complexes exhibit different temperature dependence? So to get the answer, we next determined all the crystal structure at the different temperature. And the results are summarized in this slide. This graph shows we took a horizontal axis is averaged platinum distance, R average. And vertical axis stands for the emission energy estimated at the emission spectral maximum. So, as I said in the previous slide, higher energy corresponds to the weakening of the platinum-platinum interactions. So let's check the data. For red dot shows the temperature dependence of methyl substituted form. This shows, as shown here, the temperature dependence exhibits good correlation between emission energy and platinum-platinum distance, like this. And you can where the slope decreases from methyl, ethyl, isopropyl, like this. And in the case of tertiary butyl form, there's no shift was observed. Also, the platinum distance changes, but the emission spectra did not change. So maybe we thought that this distance, this distance are a limit of the platinum-platinum interaction overlapping. But considering the stacking structure, tertiary butyl form has a rather deformed structure. So the excited state, we think the excited state is localized in a dimer area. But in the case of the other complexes, methyl, ethyl, isopropyl forms, the excited state can extend it to the trimer or more, depending on the temperature. So we obtained that kind of correlation for these complexes. Okay, so tertiary butyl form, blue emitting tertiary butyl form is a really interesting system. And we found another feature that is vapochromism. We observed the reversible stepwise single crystal to single crystal transformation induced by vapor. And as shown here, blue emitted crystals of tertiary butyl form include water molecules in the crystal water as polyhydrate. And the sample is stable in a sealed tube, but if you dry the sample in vacuum, the color change occurred blue to yellow-green. This is found to be anhydrous form. And on exposure to water vapor, the yellow-green form returned to blue emitted form. And interesting point, this is a vapochromic behavior, but interesting point is all the process proceeded keeping the single crystallinity in this case. So we investigate the dynamics of vapochromic SSC transformation of the complex, using in situ measurement with controlled vapor pressure. And we found the green emitting form, anhydrous form, changed to rehydrate form by to hydrate form. Yeah, stepwise transformation we observed. And interestingly, the stacking form changes from parallel stacking to oblique stacking by intermediate stacking. So this is an interesting example of the vapochromism. Okay? And one problem of the vapochromic behavior of the crystalline materials is slow response. It is due to the slow diffusion of the vapor molecules in crystals. So aiming at the rapid vapor response, we took another strategy here. This is to use mesoporous organosilica shown here, called BPPMO. BPPMO has a honeycomb structure with mesopore framework constructed with silicate and bipyridine units connected with coordination bond. So the BPPMO, I would say the BPPMO ligand is a huge ligand, a kind of a huge ligand with periodic arrangement of BP and mesopore for organic chemists. So we successfully prepared platinum complex immobilized BPPMO like this. And we called this PTPMO. Platinum, cyclometalated platinum units are connected in the BPPMO. Okay? And this shows the emission spectra of PTPMO. And as shown in black line, broad emission spectra was observed for 12% loaded platinum per silicon. So we thought that platinum assembly was prepared in the PTPMO. Actually, the 1% silicon sample shows the structured emission spectra similar to the typical pi star emission for the model complexes. So the 12% PTPMO is an important ratio for the platinum to make a platinum complex assembly. But unfortunately, the emission spectra is very, very weak at room temperature for this sample. So these spectra are taken at 77 Kelvin. But, however, very interestingly, when the PTPMO was exposed to methanol vapor, the large emission spectra, red emission spectra appeared like this. Let's check the short movie here. Sample on the spatula is turned to red soon over the methanol vapor. Okay, so it exhibits red luminescence like this under the UV light. Yeah, this is a real-time movie, so in 20 seconds, we observe the luminescence of the platinum from the platinum complexes. Yeah, so rapid response was realized in this system. And we observed my nanocrystals, there was the nanocrystals on the PTPMO like this, by the same measurement. We determined the nanocrystals by mass spectrometry and found the platinum complex was produced on the PTPMO. This means platinum silicon bond scission occurs by the methanol vapor exposure. It's amazing, but we confirmed the formation of the platinum complex by using the deuterated methanol exposure. And of course, before methanol vapor exposure, there's no peak was observed. So that this shows the platinum complex was formed by methanol vapor exposure and accumulated on the BPPMO surface. Okay, the complex, the structure of the complex determined by the crystal structure, and the emission spectra we confirmed. Emission spectra is the same as that of the PTPMO red form. So, in this slide, mechanistic scheme of vapochromic behavior of PTPMO was summarized like this. I'll skip the details, but first, in this system, fast and repeatable vapochromic response has been achieved by the nanocrystal formation on BPPMO effectively. Okay? This is a summary of the second part. And triplet mmLCT emission color of PT N-heterocyclic carbon complexes was tuned from red to blue without changing the emission origin. The color change can be explained by the difference in the delocalization of the excitation in the assembled structure. Vapor-induced reversible SCSC transformation also observed. And in the second, first we use the PMO, and fast and repeatable vapochromic response has been achieved based on this, the nanocrystal formation of the assembled platinum complex on the periodic mesoporous organosilicate, VPPMO. Okay? And let's move on to the third part. In this part, I'd like to show you the luminescent platinum complexes controlled by the counter ions. In here, I'd like to focus on the surroundings of the luminescent platinum complexes. The control of the surroundings, in other words, the crystal space, is another important factor for the solid-state luminescence. In particular, divariant platinum complexes are very sensitive because the complex takes a square planar geometry. And intermolecular interaction causes the non-radiative deactivation, like an aromatic fluorophore. But you can generate a new emission state by using intermolecular interactions, such as metal-metal interaction, as I said in the previous part. And hydrogen bond pi-pi interaction, coordination bond, also very important to expand structural diversity and functional versatility. In addition, I'd like to focus on the counter ions. We can make new luminescent materials using counter ions. So, one example, good example, is shown here. This is a cyclometalated platinum anionic platinum complex. This complex is exhibit various different features depending on the counter cations. Potassium cation, potassium salt shows yellow luminescent like this. But by substituting the potassium with the tetranormal butyl ammonium cation, you can get green emission with high quantum yield, emission quantum yield. So the normal tetrabutyl ammonium cation, such as a bulky cation, is important to make a highly luminescent solid. On the other hand, by changing the potassium cation by methyl ethyl imidazolium cation, you can get liquid, ionic liquid, luminescent ionic liquid, like this. So I'll discuss the ionic liquid later, and so before that, I'd like to show you the powder, crystalline powder, two sorts of the crystalline powder, because the crystal structure are available for the solid-state materials. So this shows the emission spectra of potassium and tetranormal butyl ammonium salts. This shows the structured emission. As you know already, the pi-pi star emission of the ligand. And this shows the monomer state it was realized. But in the case of potassium salt, you can see a broad emission shown in blue. So let's check the crystal structure. This is the crystal structure of potassium salt. You can see a beautiful arrangement of the complex units. Platinum atoms are indicated by the purple ball, and the red ball shows the potassium cation. And by extracting this part, you can see a dimeric form of the platinum complex units with short platinum-platinum distance. And potassium are supported to anionic units. And this is the reason for the yellow luminescence. Probably it's a triplet MMLCT emission. On the other hand, in the case of the tetranormal butylammonium salt, you can see a completely different crystal structure. Anionic platinum units are shown here and here, here. And tetranormal butylammonium cation are located over the complex anion. So by looking this part from the lateral side, you can see platinum complex anion are located in a discrete space. Two cations are covered over up and down of the platinum anion. Thus, the intense luminescence can be realized in a discrete and condensed confined space of the platinum complex anion. Okay, by using this strategy, using the tetranormal butylammonium cation, we prepared another platinum complex with high emission quantum efficiency. And this shows the platinum and heterocyclic carbon platinum complexes with different pi extension. You can see a pi star emissions with different colors. Okay? So, depending on the, sorry, let's go through. And let's check the ionic liquid next. So we prepared the ionic liquid, platinum complex ionic liquid by using methyl ethyl imidazolium cation. And it, as shown here, it is a yellow luminescent sticky liquid at room temperature. And at low temperature, this complex exhibits green luminescence. But unfortunately, this complex did not crystallize at all, and we observed that glass liquid transition at -10 degrees C. So next, we use another cations like this. This is trihexyl tetradecyl phosphonium cation. And we got the interesting materials showing the supercooled liquid crystal transition. We get the crystal of the complex. It exhibits yellow luminescence, intense yellow luminescence. And this shows the phase transition behavior. The crystals melt at around 54 53 degrees C. And, but in the cooling process, there's no change occurs. And around here, green glass transition was observed around minus 40 degrees C. This means supercooled state appears at room temperature. And in the heating process, we observed the small exothermic peak. This means the crystallization occurs and melt again at 50 degrees C. All right, like this. So, supercooled liquid exhibit no luminescence, and crystal exhibit very intense green luminescence. So we can change the state. These are bistable state, but using this phenomena, on-off switching of luminescence was realized in these systems. And we also found this ionic liquid exhibit mechanically induced crystallization. This slide, this graph shows time course of the apparent emission quantum yield of the thin film we prepared like this. And after mechanostress, it is clear that the crystallization occurs quickly, although without mechanostress, the changes slowly. So by using this phenomena, it is a kind of demonstration. If you scratch the ionic liquid film, the trace exhibit green luminescence, and just heating around 40 degrees C, the luminescence disappeared, and like this. All right. So this is a summary of the third part, luminescent, regarding the luminescent platinum complexes controlled by the counter ions. First, luminescence properties of anionic platinum complexes can be controlled by the counter cations. Highly luminescent crystals are realized by the formation of isolated spaces using a bulky cation, while some chromic luminescent ionic liquid was realized using the asymmetric cations. And in the second, asymmetric phosphonium ion of the complex anion exhibits mechano-triggered luminescence on-off switching at room temperature, so, which is based on the control of the supercooled liquid phase and bright luminescent crystal phase. Okay, so my talk is almost finished. This is acknowledgement. In this slide, I will show you the collaborator. As I said in the beginning, the studies in my talk today has been done with my collaborator at Hokkaido University Cognition Chemistry Laboratory. I appreciate their hard work. And I also thank Professor Murayama's group for the measurement of emission lifetimes at very low temperature. And Dr. Inagaki and Dr. Maekawa at the Toyota Central R&D Laboratory kindly offered the BPPMO. I'd like to thank again. And some crystal determination were helped by the Rigaku Corporation, Dr. Kikuchi. Thank you very much. And I'd like to all the members of the soft crystals. I'd like to thank all the members of soft crystals. Okay, this is a photo taken in the first domestic symposium of soft crystal in 2017. After that, more than 100 researchers joined our group, our project. So I'd like to thank all the members for their collaboration, and I hope the project has finished, but I hope the soft crystals science develop much more in the future. Okay, so this is the campus of Kansei Gakuin University. Now I have a small lab here, and that's all. Thank you very much for your kind attention. Thank you.
Thank you, Professor Kato, for this beautiful, for showing us these beautiful results, and the session is open for questions.
Thank you very much. It's really beautiful introduction to soft crystals. I'm not in the field, so for me it was all new, and it's really interesting. And I think this material seems to be really inspired for actuation, to connect the molecular scale with the macro scale, right? And I was wondering what is, if people have already explored these kind of materials on surfaces or on films.
Surface or film? Yeah, some people doing the such kind of studies. My group also make a thin film, some of them, and try to measure the response. Maybe, of course, you know the thin film. In the using thin film, the rapid response is expected, and it's a good way to actual material device toward the device. Yes, thank you.
Yes, and the other question is like, why most of the examples you use platinum as a coordination center? Can you give some rationale why you focus on platinum specifically, or have you explored other metals?
So, are you asking the platinum complex? We use the platinum complex for the surface one. For making a thin film?
Yes, but I mean, the example you show are using platinum as the center. So what is special about platinum? Why not using other coordination centers?
Except the platinum metals?
Yes.
Oh, yeah. For the luminescent material, other luminescent materials, copper is one of the interesting metal centers.
Right, because it's cheaper, right? Also.
Yes, exactly.
Thank you.
Hi. Oh, sorry. Can I ask? Yeah. Thank you for the talk. I had a curiosity about, so this is an emission from triplet state, so this is our phosphorescent system. I was wondering if you have, I mean, how is the time behavior of these emissions, how long it's staying, and then also in the last system you showed the emissive material is the one that has no interaction between the metal, am I right? Can you
yes, so that you are asking the lifetime of the metal complexes, platinum complexes,
yes,
triplet state. Yeah, usually depending on the materials, but the platinum complexes, assembled luminescent platinum complexes has a lifetime of around several hundreds of nanoseconds at room temperature.
Okay.
Because usually organic, for the organic materials, the triplet state has a very long lifetime, but using heavy metal atoms, the decay time becomes very short.
Okay, thank you. And so for the second question, like, is it correct when you add when you intercalate with large bulky? I'm here.
I can't find it.
Sorry. When you intercalate with big cation, you kind of decouple the platinum, right? Is it correct? In the last example, you showed the one that is more emissive is the one that has a bulkier cation.
Yeah.
So it means that the metal center do not fill each other in this case, but still they are emissive.
Sorry, what do you mean?
Maybe I can ask you better after, so I can explain my question better. Thank you. I'll ask you after the
okay, thank you.
Thank you.
If there are no other questions, I would like to thank again Professor Kato. And
thank you very much.
Speaker, we have a quick announcement. If you have not confirmed your transportation with the travel agency here, please, he should have sent you emails. If you didn't get an email yet, check your maybe spam folder, everything. Make sure you reply, confirm you have received the email. Confirm your time and date. Yeah. In the email, they will specify the time and date for pickup, but you just say confirmed if it's correct, okay? Then know what to do, yeah, okay? Okay. So we have our last plenary lecture here. It's my great pleasure to introduce our speaker, Professor Lam Barber. He's already well known to most participants here. Also, Alan, this morning, he did an excellent job summarizing some of Lan's research highlights. His milestone achievements, particularly around these porous molecular solids. So I'm going to mostly focus on his professional career development. So Lan obtained his PhD from the University of Cape Town, where he investigated thermodynamic and structural aspects of solvate formation and decomposition. After a postdoctoral fellowship with Jerry Atwood at the University of Missouri, Columbia, he was appointed to a faculty position at the University of Stellenbosch in South Africa, where he continues to pursue his interest in solid-state supramolecular chemistry. And his interests include various solid-state phenomena with particular emphasis on the design and the characterization of porous materials for inclusion chemistry, such as chemical separations and gas sorption. He has served as associate editor of the 9-volume major reference work, Comprehensive Supramolecular Chemistry, the 2017 second edition, and also the New Journal of Chemistry from 2016 to 2019. And more recently, associate editor of the Crystal Growth and Design since 2020. I look forward to a live discussion led by Elaine on this recent progress and particularly future outlook of crystal engineering.
Thanks, Calvin, for that nice introduction. In fact, I think I wrote that, didn't I? Before I start, I really just want to thank Tomče and the team for organizing this really fantastic meeting in a fantastic venue. Tomče, you guys have done such a great job. And something I really noticed at the last meeting that Mike was involved in organizing, the one in 2019 in New York City, was that he managed to draw in people who don't traditionally come to the ICOS conference, and you've continued to do that, and I think that's great. I think we need to be able to talk to each other and grow the community. So thanks again for doing that. So I got a big upgrade in this conference because in the original program I was down for a 20-minute talk on my research, and Mark Spackman was supposed to be giving this final plenary, but he had to pull out for some reason, and Tomče emailed me. I don't know if I was the first person he emailed, but he emailed me and upgraded me by 3. So thank you, Tomče. Okay, so what Tomče asked me to do is to not talk about my research, but to give an overview of the current state of the art of the field and also some future outlook. So, I'm not going to talk specifically about the organic solid state, but of course what I'll talk about is very relevant to organic solid state. So I want to talk instead about crystal engineering as a whole, but of course we fall under that. So, okay, and this is not working. Okay, so of course if we're going to talk about crystal engineering, then, of course, we have to ask ourselves the question, what is crystal engineering? And I think this is no surprise to you, what's coming next, and I think everybody here knows who Gautam is. And more than 30 years ago, he came up with this very succinct description of crystal engineering, and when I look at that, I think he pretty much nailed it. I wouldn't change very much in this definition. Maybe you don't agree with me, but I think 30 plus years later, I think this is pretty much still what we're into. So the important words here are intermolecular interactions, crystal packing, and of course, utilizing that kind of understanding in order to actually design solids that might be useful to us. So when I talk about crystal engineering, that's what I mean. Now, crystal engineering, of course, is part of engineering, and so we have to think about what engineers think about. And so I think this is the typical approach of an engineer when they think about various materials. Does it move, yes or no? If it moves, should it move? And if it does move, then no problem. So these in crystal engineering are what we might refer to as active properties. And I'll get more into that in a few slides' time. And then, of course, if it doesn't move, it might have passive properties, and if it doesn't move and it shouldn't, again, no problem. So in crystal engineering, we're dealing with both kinds of materials. Okay, so these are some of the topical areas in crystal engineering, and you notice I underlined the word some because it's not comprehensive. Again, this talk is very biased towards the kinds of things that interest me. I've tried to be as inclusive as possible, but this is a big community, and you may come up with your own way to present something like this. But if we think about passive properties, well, something like pharmaceutical crystallization. Okay, so we're not asking the crystals to do anything, we're not asking them to move. What we really want to do is to optimize efficacy. In other words, dissolution rates, whether or not you can tablet them, and that kind of thing. So those would be passive properties. Then, of course, we have porous materials. Again, passive properties, we want to absorb things into the material, and we want to be able to do separations or catalysis or storing gas and so on. And then, of course, related to that is this very beautiful innovation from Makoto Fujita's group, where he was able to use these passive properties to determine the structures. Now, you all know about this work, so I'm not going to go into it, but use these passive properties to determine the structures of materials that are hard to crystallize or hard to obtain in bulk. So those are just some example of passive properties, and if we think about active properties, well, these are things we might base devices on. So these are crystals that might have electronic, magnetic, optical, or mechanical properties. We might also add thermal to that, and maybe you can add to the list as well. And then there's solid-state reactivity, so in other words, topochemical synthesis. And then on top of that, we also have very advanced computational methods now. So things like structure and property prediction, which we're going to see a lot more of, and data mining and utilization. So these are really the topics that we think about in crystal engineering, and in many cases we study, a particular group will actually cross over and study various aspects of these. So this is what I'm supposed to be talking about today. Where are we now, and where are we actually headed? Well, let's look at where we are now. These are some very well-known examples of crystals that have really changed the world as we know it. Of course, they're the pharmaceuticals, and of course, the properties of the crystals are central to how well the pharmaceuticals will work in the roles we need them to play. Then there's electronics based on silicon, some more electronics based on quartz crystal oscillators, and we all have, you might not know it, or maybe you do, but we all have many, many of these in our various devices. For instance, if you have a digital watch that has the word quartz on it, it means there's a quartz crystal in there, and it's cut in such a way that when it's stimulated electrically, it beats 32,768 times a second. Okay? And then it also contains a circuit, and that circuit divides this oscillation up 15 times. If you know your 2 times table, you know that 32,768 is 2 to the power of 15. So you divide that into 2 15 times, and you get exactly 1 hertz. And then, of course, we have the zeolites, which have been incredibly important for loads of different applications that I'm sure I don't even have to list here. Okay, so we're after some useful properties. And what I really want to address now is how good are we at predicting these things? Can we predict what's going to be useful in the end? Because many of us here simply work on what we work with because it interests us. Okay, so we find it intellectually stimulating, but people will always ask us, what's it good for? Now, how good are we at actually predicting what something's good for? Well, are we good at predicting where something is going to end up? For instance, would the people who developed that have predicted that we'd end up there? What about the telephone? Would we have gone from there to there, camera from there to there, and what about flight? I think the technology here was not easy to visualize by the people who developed these rather crude devices. And even further to that, would people even have predicted 30 years ago that you could combine these 3 different devices into one? So we're not that good, I think, at predicting where things are going to go.
So let's look at somebody who we think ought to have been very good at predicting where technology would go. Well, we know that he was instrumental in developing the gramophone, but this is a quote from Edison. "The phonograph has no commercial value at all." Okay, so the guy invents it, but he says, you're probably not going to make money out of this. What about cars? So this is a car from 1886. That's how far cars had developed by 1909. So we're looking at 23 years worth of development over here. And in Scientific American, somebody wrote that the automobile has practically reached the limit of its development, is suggested by the fact that during the past year, no improvements of a radical nature have been introduced. Okay, so by 1909, they said that's pretty much it. I mean, cars are not going to get any better than that. Computers, of course, are a good subject for bad predictions. So this is a photograph of a computer. This is the ENIAC computer. You can see ENIAC is the acronym for this over here. And so what did people predict about computing power in the future? Well, in Popular Mechanics in 1949, somebody wrote, where a calculator on the ENIAC is equipped with 18,000 vacuum valves and weighs 30 tons, computers in the future may have only 1,000 valves and weigh only 1.5 tons. So a very optimistic prediction of where computing technology was going to go. And the reason they couldn't predict where it actually ended up is because they didn't anticipate the development of other technologies. So here's a picture of a vacuum valve, the valves that they're referring to over here. In the late 1940s, that was replaced by the transistor, and over the years, transistors have become smaller and smaller. Okay, so that obviously revolutionized this field. And indeed, in 2006, Intel released the first chip that contained more than 1 billion transistors. So in other words, more than 1 billion of the equivalent of this in a little package like that. And in your cell phone, in your smartphone, you have around 200 billion transistors. So again, not very good at predicting where things are going to go. Okay, so this is the question I was asked to answer, and what is the future of crystal engineering? Okay, so in the last week, I haven't been doing this. I don't have a crystal ball, so I don't know the answer to that question, and if I knew what the next big thing in crystal engineering was going to be, perhaps I wouldn't be telling you about that. I'd be doing it myself. But I don't have one of these crystal balls. I also don't have a magic 8-ball that I can just ask a direct question of. So, how should I be approaching this? I also don't want to be this guy. Now, if you're older than 50, you probably know what this is about. If you're younger than 50, or if you haven't seen the movie The Graduate, then you can't consider yourself to be fully educated. Okay? This is a classic scene from that movie. This is a very young Dustin Hoffman who's just graduated from university and considering job options, and somebody's about to take him aside and give him some advice about the future. Let's see if this will play.
I just want to say one word to you. Just one word. Yes, sir. Are you listening? Yes, sir. Plastics.
Oops. Let's see. Nope, gone too far. So, what's the best way to approach this? Well, the best way to approach this is to actually outsource the opinions. So, I've approached various people who I consider to be friends and whose opinions I trust, and importantly, these people are all also younger than me. We have PhD students here, early career researchers, some mid-career researchers. Panchi, I'm not sure where you are in that, but we'll call you mid-career. Postdocs, and some people who are even starting to fantasize about retirement. So I've asked these various people for some of their opinions, and what I want to do is to compile these and see if we can reach some sort of consensus of where the field is going. I also want to acknowledge my colleague Delia, who suggested a lot of these people and who also provided some valuable discussion about these questions. So the next part is a bit text-heavy, and I couldn't really see how else to do this. I'm not a big fan of slides with a lot of text on them. I like lots of nice pictures. But I think under the circumstances, this was unavoidable. But please, I'm not asking you to read all of this. I'll do it for you. Okay, so Travis Holman, when I asked him, what is the future of crystal engineering, or in your particular field, what do you see as the state of the art, and so on. So some people gave very specific answers about their field, and some people gave broader answers. So I'll go through some of these. So this is just the wrong distance for me. I'll have to put these on. So Travis says, concomitant progress in many areas of organic solid-state chemistry. So by that he means molecular solid-state reactivity as being state-of-the-art, pharmaceutical material science, we know that, and smart materials with many physical-chemical properties. For instance, he's particularly, if you know Travis, you know he's partial to porous molecular materials. He also feels that the state-of-the-art is studying dynamic processes like phase transformation phenomena. In other words, single crystal transformations and so on. And he also feels that there's a need for some better experimental methods for key structural and physico-chemical information that we can get from these materials. So he's talking about in situ characterization methods. So in other words, methods that we have developed over the past and methods that we could still develop in the future to help us to understand various phenomena. And then obtaining information about the less crystalline regions of organic materials. And of course, he pointed out the growing power of computational methods and crystal structure / property prediction methodologies. And that's going to come up over and over again. So I think that's telling us something. All right, I'll try to compete with the weather. Alan, who is a PhD student in my lab, has been, I think, to every talk as far as I know, and he was at the GRC a couple of weeks ago and was very engaged there as well. And so I think he's picked up a lot over the last 3 weeks. So he talked about extracting meaningful information from large data sets. So multivariate analysis of data sets and looking at complex systems influenced by a number of different variables, and also applying machine learning for crystal structure prediction. So it's coming up again, crystal structure prediction. Also sustainable chemistry. This is something that's also going to come up over and over again. So we're talking here about mechanochemistry. We've heard a lot about that during this conference. So solvent-free synthesis and producing bulk materials in phase purity. And then once again, machine learning. Smart adaptive materials. I suppose we're talking about devices here. So feedback loops, self-correcting crystals that respond to external stimuli. Memory states, materials that are tuned to adopt specific states, but change to a desired state under the correct stimulus. I'll say I've never really given a talk where I had to read the whole thing, but these are the opinions that were sent to me, so I've pretty much copied and pasted most of it with some slight shortening of what people said. So Ivana talked about engineered materials without long-range order and correspondingly increased use of paired distribution functions, talking about properties like chiral separation, magnetism, and so on, the kinds of properties that we expect from crystal engineered materials and predictions. Crystal structure and properties prediction, so here it comes up yet again for engineered materials. It'll become more and more a routine part of crystal engineering. Sureshan was more specific. He talked about topochemistry, and that's one of the things I asked people to do as well, and that is to focus also on their particular area of interest. He's pointed out this has come a very long way in the last 50 years. The number of reactions is still limited in comparison to solution state reactions. It has a special place in producing unique products, often those not possible through the solution state, and also to be able to do reactions selectively. And the green part is avoiding catalysts and solvents, and you can also avoid things like different purification methods. He felt in the future some of the important developments also in that field would be to go greener, so there's a huge demand for green synthetic protocols, so we need to develop new kinds of topochemical reactions, and what about the use of novel stimuli for topochemical reactions? In other words, currently we use light and heat, but what about other stimuli, the kinds of stimuli that people have been talking about here? So things like pressure or sound waves, which might need to be investigated as well. Formation of crystalline polymers, in other words, to get function from these crystals, so strong lightweight materials, atmospheric water harvesting, CO2 absorption. And he felt that in the future, some of the important developments would be to look at high-dimensional, 2- or 3-dimensional crystal polymers, and in possibly using these for gas separation and molecular filtering. Also, the marriage of polymorphism and topochemistry, I think that this has not been studied in great detail yet. So in other words, can we tune the product of the reaction through polymorphism, either by phase changes or just simply growing the same components in different ways? And then the synthesis of different polymorphic forms of polymers where different crystalline forms of a polymer would give different properties. Also, tapping mechanical responses from topochemical reactions, in other words, doing the topochemical reaction, having that cause a change in the crystal structure, lattice dimensions, which can generate strain, and then manifest as mechanical responses. Okay, Kristen, she said that even though this is not her area, once again, she's recognized that there's a lot of promise with crystal structure prediction. So it's coming up again. She felt that there needs to be more of a pairing of theoreticians and experimentalists, and that we need to target specific crystal form with chosen properties via crystal structure prediction, followed by making it in the lab is an incredibly exciting avenue for obtaining organic solids with ideal properties. Then she felt that crystal engineering has already demonstrated this to some extent, but we should expect more advances in the coming years, of course. Panche also weighed in. He felt that we should work towards establishing organic crystals as a distinct class of engineering materials, increase cohesion and support within the community. He felt that it's still a little bit too fragmented and quite a small community, and so that's why I'm so glad to see Panche pulling in more people into these meetings so that we can communicate better with each other. I think there's no surprise here, applications. So in other words, to convince others, including engineers, that crystals matter, we need to show that they can actually be applied. We should provide a balance between the focus on the materials and the methods to analyze them. So we need improved technologies, new ideas, of course, and we need to look to the future as always. Kathy Edkins, I think most of you know her. She's in pharmaceutical sciences. And so she commented specifically on pharma and the role of crystal engineering in pharma. And she says the next best thing, or the next big thing, will be prediction of crystallization experiments, be it based on experimental data or on computational algorithms. So computational comes up again. And she says a lot of good work has been done, but it is by no means trivial. If we can unlock the crystallization experiment so that we can dial in the crystalline phase that we want without having to do the trial and error crystallization screening, in other words, the current state of the art, we'll be a step closer. Jason also weighed in, felt that the state of the art is rational design of crystalline systems, theories that accurately and reliably predict crystallization outcomes. So here it comes again, especially binary or higher order solids. The ability of theory to guide the synthesis of metastable materials as opposed to brute force trial and error. It would be incredibly exciting if students could routinely perform crystallizations in silico prior to trying them out in the lab. And that will come up later in something that Aurora also said. There are really exciting advances being made in the computational chemistry of crystalline systems. However, these methods still remain largely inaccessible to non-experts. Again, something that Aurora has weighed in on. So unfortunately, Aurora is not here right now. But she gave quite a lot of suggestions. So obviously, she started with crystal structure prediction, talked about cloud computing, about how that could enable the prediction of more complex compounds that require a lot of computer time, develop better methods to simulate molecular crystals. DFT-D is good, but electron correlation is poorly modeled. So a next level of accuracy up should be achieved in the next decade, enabling better modeling in flexible molecules. And in fact, she talked about this a few days ago. Further automation, make the technique accessible to non-experts. So that's, Jason, that's the answer to your question as well. So this is something that Aurora feels quite strongly about as well, is to make this way more accessible than it currently is. And then move from structure to property. And I have a slide coming after this. So Graham Day has already been doing some very innovative work in this area. And then also to be able to predict kinetics of crystallization of hypothetical structures. Consider thermal effects. Some of those maxima are not actually maxima when you include temperature. So this is what she was referring to. So this is a relatively recent article by Graham Day's group in collaboration with Andy Cooper. So this was in Nature, functional materials discovery using energy structure function relationships. So in other words, pulling function into the computer predictions as well. Okay, to continue with what Aurora suggested, we need to crack nucleation, she feels. Learn more about what happens at the molecular level, the initial stages of molecular aggregation, conformation during aggregate, I guess she means aggregation, speciation, modeling needs to catch up too. How can we study nucleation experimentally to supplement those calculations? Again, in situ methods come up, higher resolution. And she says, we're still far from predicting crystal growth rates in different solvents accurately and accessibly. Unless we know how to do this, we will never be able to predict outcome of crystallizations. And Tomislav, as you can imagine, Tomislav really had a lot to say, which is why I'm saving him for almost the last. So, in general, in terms of the field, he said we must keep pushing crystal engineering and solid-state supramolecular chemistry forward to be recognized as a central area of modern materials science and chemistry. So, Banche, echoing what you said as well. In other words, the field needs to become more visible, I think, in modern chemical sciences. Then, of course, mechanochemistry. He talked about two very big initiatives in mechanochemistry that's really going to push the field forward. So there's the EU cost action on mechanochemistry for sustainable industry, involving many, many different institutions and a lot of researchers. And in parallel to that, there's also the NSF Center for Mechanical Control of Chemistry, coordinated by James Battius and Ashley Martini. And on this, Tomislav commented that large collaborative international and interdisciplinary centers focused on mechanochemistry on both sides of the Atlantic is a strong message of the importance of mechanochemistry to the future of chemical research and manufacturing. He also wanted to draw attention to this article from Chemistry World, 10 chemical innovations that will change our world. And the fifth in that list is mechanochemistry and reactive extrusion. So mechanochemistry is really being recognized as a really important field to move things forward. He also wanted to give a shout out regarding some highlights that he considered are really important in the field. I don't know if Francisca is still here, but he felt that she's done some fantastic things in situ measurements. James Mack on catalysis by surfaces in mechanochemistry. Lars Borchert and Jose Hernandez on synthesis. Stuart James, who was the first to show that you can synthesize MOFs mechanochemically rather. Ito for using the piezoelectric effect to drive mechanochemical catalysis. So he wanted to draw attention to those as really important recent developments that are really state-of-the-art. I'm sure many of you already know this, that Thomas Lab is moving from McGill to Birmingham, and so this was an announcement on the Birmingham University website. So soon in Birmingham, he writes, we will see the starting of an incubator center for the development of mechanochemical methodologies. So I think it's a case of watch this space. I think Thomas Lab has already achieved so much, and it's just going to get bigger and better. He also wanted to draw your attention, if you're interested in this particular field, that there is an upcoming Faraday discussion, and the details of that are on here, but I think this will be quite easy to find if you don't already know about this. I also asked Satoshi Takamizawa, and he's done some really beautiful work with single crystals as well. He said we need to consider some questions. In other words, what are the preconceived ideas that we need to get past? How complex or how simple should the conditions be in order for us to be convinced that a phenomenon is universal? How can we progress from crystals, which are extremely inconvenient in terms of their use as materials? Then we have Jonathan Steed. In fact, I spent last week with John between the Gordon conference and this meeting here, and he wanted me to draw attention to this recent ChemCom article that he published, where he talked about 21st century developments in the understanding and control of molecular solids. So again, if you're not aware of this article, and he feels that not enough people are aware of it, he says he was hoping he'd have more citations by now, but it really hasn't happened yet, so I told him I'd promote his article. I'm just going to take a selection of highlights. Of course, the article has a lot more than just what I'm going to show here, but I took a selection that I think really represents what was easier for me to put on the slide in terms of how much text I needed. He notes there's a shift over the past 20 years to co-crystals and co-amorphous materials. This is particularly with regard to pharmaceuticals. There are also recent developments in increasing throughput and control, influencing methodology or altering key properties such as dissolution rate, bioavailability, processability, stability, and compressibility. Clearly also to do with pharmaceuticals. An explosion in the application of mechanochemistry and liquid-assisted grinding methods to the study of molecular solid form. Growth in understanding nucleation and growth mechanisms. And there's been tremendous progress in computational crystal structure prediction methodologies. So here it comes up again. So a lot of progress and also a lot more progress to be made. So that's the end of those very text-heavy slides. I'm sorry about that, but as I said, I really don't see any other way I could have done that. So this is really a summary. I've taken, I think, the points that have come up most often. So prediction and control of structure and properties, I think, is what people feel lies in the future. So we've made tremendous progress in prediction of structure, but now we need to tackle properties as well. Of course, sustainable technologies, so that relates to things like mechanochemistry and solid-state reactivity. Innovations in characterization and methodology, so in other words, we're seeing innovations in instrumentation all the time, so the sky's the limit there, and also in the development of in situ techniques. We need to find new applications for our materials, and we need to promote our field a bit better. Okay, so in terms of prediction, because this has come up over and over again, and I'm sure once again many people here are very familiar with this quote. This was by John Maddox, who was editor-in-chief of Nature for a very long time. And he said, one of the continuing scandals in the physical sciences is that it remains in general impossible to predict the structure of even the simplest crystalline solids from a knowledge of their chemical composition. So that was rather a long time ago. And we know that a huge amount of progress has been made in that field. There's been a lot of interest because of pharmaceuticals in particular. Computing power has grown so much over the years, and very clever algorithms have been developed. So we know that this is no longer true. So let's look at a particular case, so pharmaceutical crystals. But this could apply to whatever your personal interest is, even if it's not pharmaceutical crystals. So pharmaceutical crystals, well, if we study them, we have to study the crystallization process, and that involves things like mechanochemistry and seeding and so on. So we actually have to produce the crystals. That's the first step. And I'm just putting this here to show that I know that that's not all there is to it. There's a lot more to it than just that, but I just want to keep the slide relatively simple. Then, of course, we have to progress to structure. And we have various methods of looking at structure. We have different diffraction techniques and imaging techniques and so on. And from structure, we can elucidate things like interactions and packing modes and so on. And then, of course, we can break the structural types down into various things where we have concepts like solvates or salts and polymorphism and so on. So we have to think about structure as well. And then, of course, we need to move on to the next step, especially in pharmaceutical sciences, and that is properties, so things like dissolution rates and morphology and tableting, et cetera, et cetera. And then there is the characterization. So in other words, the various methods with which we can characterize both structure and the properties of these materials. So this is where prediction comes into it again. So we've seen that people feel that we need to be able to predict the actual crystallization experiment. We need to be able to predict structure, and we need to be able to predict properties. So this concept of prediction comes up over and over again. Okay, so I'm almost at the end of my talk now. So this is my acknowledgement slide once again. So in case you didn't catch that the first time around, so these are all the people who weighed in on this, and various other people who provided some advice for this presentation. Again, if you're interested in the field and you don't already know about this particular webinar series, this is a webinar series hosted by myself and John Steed. That is us not hosting the webinar. It's called Talking Crystal Growth and Design. It's a monthly webinar, and you can see some of the recent speakers over here. We had Francisca in April, and in May we had Susan Reitzel-Edens. We had Susan Bourne last month, and coming up in a couple of weeks' time we have Mike Zavorotko, who I think is going to give the talk that I probably should have given here. And that is why crystals will save the world. So I'm looking forward to seeing his take on this. So please, if you're not already aware of this webinar series and you want a monthly shot in the arm on state of the art in this particular field, please tune into this webinar. Okay, so what do I think? I've told you what other people think, but what is it that I actually think? Well, I pretty much agree with everything that I've put up here. Sure, we do need better prediction of structure and properties. I mean, yes, absolutely. I agree with that 100%. But I'm also a little worried that if we get too good at that, are we still going to do experiments in the lab? So let's not stop exploring crystals and their properties in the lab. Let's not all sit in front of computers and say we don't need to go into the lab at all. Because with prediction, you've got a particular target in mind and you want to find that target. But how many of us have actually ended up doing some completely different research because whatever we're doing didn't work, but something much more interesting happened because we were working in the lab? So that's my take on it. So yes, absolutely, let's try to predict things, but let's not get ourselves out of the lab. Now, We've reached the stage of the talk where I finish up and then you ask me questions. I don't even know how much time we have. How much do we have?
We have a few questions.
Okay. Well, we've reached that time now where you would ask me questions, but in truth, it doesn't matter what I think. I want to know what you think. So I'm going to turn this around on you and invite people to weigh in on this. I know that this has been a very biased presentation. It's been based on, the people I know, work that I'm somewhat familiar with. I know some of you are coming from a completely different direction over here, so I invite you to make a comment on what I probably should have included and didn't, and so on, or where do you think this is going? So thank you, and please do that.
Thank you, Len. So the question is out. He's challenging all of you. Okay.
Thank you for the wonderful talk. I love the way you include the opinions of different people. I think that's wonderful. And I'm going to break the ice by saying you miss the bio-inspired materials. And I think that's a nice way to connect these structured properties, going the other way around. So coming inspired from the properties of biological system and then look into the structure. So that will be kind of a loop that I think is really worthwhile exploring in the future. That's my 5 cents.
Thank you. I obviously need some friends in that area.
I think the thing you didn't cover very well, I think, was the interconnectivity of it all. So it's not about structure and properties. It's not about crystallization. It's not about property. It's not about how the process goes on. It's about how they all interact. And in my view, you can't hope to be claiming crystal engineering, speaking as an engineer, unless you can do it. And the fact is we can't. So if I give a task that involves solid form to my third-year design group and say, design it, they can't. There's no de novo capability. If I tell them to design a distillation column, they can do it with ease and enormous precision. So when we get to solids, we have to be able to design it. And what we are doing is having a lot of fun doing material science and solid-state chemistry. The second related thing is that there is a kind of feeling that crystallization is magic, and that's because this community is not rooted in crystallization. But there is an organic crystallization community, and we meet also. We meet in 2 months' time at CJOM 14 in Brussels. Now those two, we've been organizing these two meetings, ICOS and CJOM, normally every other year, so they're there. But in fact, the crossover between those two groups is not strong. And yet, so that expertise there is there. So one example, can we really solve crystal structures using CSP without dealing with nucleation? Is that feasible? So how can you predict crystal structures based on their bulk structures when you know that when they form, they're tiny and the surface free energy is enormous? So I think there is a synergy. I think there's a lot of, but there is a real need to get the communities together. And I feel at the moment we're rather siloed. I come here for curiosity as a crystallization scientist. I always enjoy it. It's a fantastic meeting, lovely. And then I go to a core meeting later on to do the things I do research on. I don't know if that helps.
You touched on a very important set of points over there, and that's exactly why I said to Panche that this is what we need to do more of in these meetings, and that is to bring people together who need to talk to each other, exactly as you've said. And in terms of cracking nucleation, that's something that Aurora very specifically mentioned, has to be a part of crystal structure prediction. So yes, bunch of good points. Thank you.
I guess I got the microphone here. Also, a great presentation, Len. Thank you. One dimension that we don't talk enough about that I think would be really fun, very challenging, is composition. Can we increase the number of components in a crystal and really go crazy with the size of a unit cell? I saw really, can you have a crystal that has 10 components and your unit cell all of a sudden, is, 40 nanometers. I think that would be a lot of fun to explore, just increase the compositional complexity, see if that can even be done.
So you're talking about co-crystals, but co-crystals are...
Multi-crystals,
Yeah.
More than 2, 3, 4 components, but really go crazy with the number of components. See if you can still find, periodicity. And if I can continue quickly, another one that we just don't talk about is quasi-crystals. What's there, How do we make more? How do we find more? I think that would be a lot of fun too.
Yeah. And in terms of co-crystals, how many times do people do crystallization experiments when you throw, 10 different components in the same vial and see what happens?
We don't do it, right?
Yeah.
Okay, we take two more questions. Panchi and...
I start while setting.
Okay, thank you for the wonderful presentation, Len. It was a great talk and really overarching. And I think I'm going to refer to the first point that I mentioned in my outline there. And that is, I think, really we have to work on representing crystals as a special class of compounds. When I talk to engineers, and I say that I work in a solid-state chemistry, I get asked, is it this solid-state physics? No, I said it's a solid-state chemistry. They're generally not aware of crystals as being different and being special. We in this community understand they are special. We have softness, we have order, and that's a very special combination of properties. But when you talk to physicists and engineers, they would say, okay, so what's so special about it? What you can do with that? And I think that we have to promote our field and our materials beyond this community that we work in. It's extremely important if we want to expand in numbers and quality and quantity, I think.
I think the kinds of crystals that we typically deal with are of a scale that many other fields find quite awkward to deal with. I'm not I don't know many mechanical engineers or structural engineers, but I guess, they deal with a scale that is completely different from what we're looking at. And I think devices are probably pretty central. With devices, you're looking at quite a range of scale. But I think, maybe the engineers just, find the scale to be very awkward for what they think about.
One comment regarding the promoting this art community art field, and Professor Carroll's 10 Minutes movie is an excellent example of that. So we should have more of it. Yeah. Okay. You can ask a question.
Yeah. No, I just wanted, from a computational perspective, comment on the fact that there were many, let's say, reference to the nucleation process, but just as a reminder, this is a very personal opinion, but the complexity is extreme because you will need to, the number of degrees of freedom is huge that you have to take into account, and so it's very hard to find a method that will be accurate and consider all these degrees of freedom. So even if you had a very good method, the free energy is probably changing with the number of particles, so you would have to explore very big, there's even an unset sampling technique, so that will try to fix part of this will probably be not sufficient to cover all the possible states. So I think it's really challenging from computational perspective to approach this, but it's good to start.
Also from an experimental point of view, I think it's very
absolutely
difficult.
Yeah. Thank you very much for the talk anyway.
We take the last question from Craig. And sorry, I had to cut off the other questions because it's kind of late for dinner. So you can, during dinner, can talk to Len or you send him an email. Yeah, Craig?
I think Panche brings up an important point. But on the reverse side of the coin is there is a paucity of solid-state physics in this meeting. The unique thing about solids is their collective interaction, and yet very few people in this group exploit the collective nature of excitations in solids. And I really urge people to bone up a little bit more on their solid-state physics. After all, when organic superconductors were discovered, it was physicists who explained them.
I agree with you completely, and I think that's why I made that comment in the beginning, because You know, I've been to quite a few ICAS conferences, and it was very much a community of like-minded people who are in the same field as me. And when it was in New York City 3 years ago, Mike really brought in a lot of people from other areas, and we need to do more of this. And Panche, you've done even more, and clearly this needs to continue in this kind of meeting.
Great. So let's thank Len for the wonderful lecture. Okay. So I like to invite our chairman for this conference to give the closing remarks. But before that, I want to invite all of you to join me to thank him for the wonderful job he did.
All right, so I know that I'm standing between you and your dinner, and I'm going to try to be as brief as possible. But I really, I have to express that I feel a mixture of emotions, both joy and sadness, primarily. I'm very happy because I saw a beautiful science presented in the past 10 days. I was impressed by the diversity and the depth of the talks that were covered. But I also feel sad that we have to finish with this conference and we have to go back, unfortunately. And I hope that you can bring some nice memories from this 50th anniversary of this conference series. It's a kind of a gold anniversary for the ICOS series of meetings. So I will try to be brief, and within the spirit of the past conferences, I will try to cover what have we learned from this conference. A number of things. So we learned that crystals can be like polymers that can bend, oscillate, and twist. We looked back to the good old topochemical principles where it all started about 50 years ago. We learned that crystals can get really angry and they can explode when we hit them by hammer. We learned how bonds work and how rings stack. We got to know more about the marriage between the crystallography and the NMR, which is becoming increasingly important in this community. And then we learned that if you're tired using X-rays, you can use electrons instead to get those stubborn crystals to cooperate with you. We also heard about many facets of the seemingly simple but really complex process of nucleation, which is apparently a very important part of the process of getting crystals in order to study them. We saw that if you cannot make crystals, perhaps you can calculate the properties or how to make it. Also, we saw that molecules can talk to each other and congregate on surfaces, which is also a very important part of the research in this community. We even heard about plants that can make crystals, and also that water can be super cool. We saw that we can put crystals to a good use as waveguides, switches, and electronic devices, which was mentioned also in the previous talk as one of our priorities as a final goal of making and studying these materials. As always in this conference series, we always look at the polymorphism, which after so much work and so much research still remains an enigmatic process and phenomenon. We also transported ourselves briefly on Titan and dipped into lakes that were made of methane and ethane, unlike the beautiful Ohrid Lake here. We heard about how tablets can be made or not, and also the rise of the mechanochemistry as a very important direction in this field. We also saw that crystals do not always look like a diamond, but can also look like flowers, and they come in all sorts of beautiful shapes and sizes. And at the end, we also learned that CCDC is much more than a repository for structures. We can learn a lot from there. But what I think were the two central questions that were asked and answered in this conference were After half of century of organic chemistry research were the two simple questions. First, we started with where did we come from, and that was beautifully covered by the lecture by Craig, and where are we going, which was equally beautifully covered by lecture by Len. I do apologize also to those participants that because of the visa restrictions were not able to participate in person, and I do thank them for their online participation. They were with us both online and in spirit. I also would like to apologize for technical glitches such as slow connections, ear-piercing tour guide experience on the boat, changing laptops, falling laptops, and such. I think all of that makes us actually feel that we attend a real event as opposed to of online meetings that we got used to in the past couple of years, where the main questions asked were, can you hear me, or are you muted, or you're muted, and so forth. So, all right, so here I would like to actually go to acknowledge the contributions of the people and others who were involved in this meeting. So first I would like to thank session chairs and co-chairs with whose helps we actually could select the amazing cohort of speakers. Then, of course, the ICOS advisory board who helped us select the prize winners. The organizing team that did an amazing job by selecting our venue and other details. And also the local organizing committee that helped us organize this on site. And finally, I would also like to thank all of you that traveled so far in the times of pandemic, restricted funding, and also a big mess with the European airports. Some of you really had a very difficult times to get here. So I would here like to refer also to our main goal with this conference, which is also the main theme, is that I feel that we need to build bridges, that we need to continue building these bridges within the community and not walls. And I think we have accomplished this with this conference. And what do these bridges mean? Well, they mean new collaborations, they mean new ideas, they mean new networks, and finally they mean new personal friendships. Now, in times of post-pandemic world and in times of increased political divisiveness and polarization on a global scale, more than ever before, we as a research community need to stay strong and united. We need to move on, we need to grow, and we need to expand. We need to build onto the past, but we also have to look into the future. And so I hope that you will leave this country with good memories, new friendships, and we hope that you will come soon back, perhaps not for science, but maybe for a vacation, to relax and to enjoy the abundant nature and the good food. So with that, I would like to wish you a safe trip home, and thank you for honoring us with your presence at this conference. Thank you. And I would like to invite Luca with his announcement on the poster awards.
So here, the real deal, the poster awards, of course, because I want to first say that while, of course, the talks and lectures that we heard in these days, they were, of course, amazing. But the posters and the level of the poster, the science that was expressed during the poster session, I think the level was amazing. And indeed, it was very, very difficult to selection it, as usual, the winners of these posters. So before even announcing the winners, the real winners, I would say a round of applause for all the posters. I think the future of the field is bright. So we have 9 poster awards. So it's pretty rich this year, thanks to the sponsors. First of all, the Royal Society of Chemistry, and in particular chemical science. They are sponsoring 4 vouchers, £100, that I will personally send to the winners to study a little more, if you're not studying enough already, by selecting books from the Royal Society. So the first winner is Emma Kuntrapakam from the Weizmann Institute of Science for her amazing work on organic crystal cages. Please, please, don't be shy. The award and a picture, of course, for Twitter. Okay. Here we are. Congratulations. We are going with the second winner. Is Cameron J.G. Wilson for his very nice work on voids under pressure. Congratulations. It's a long haul, so it takes time. Third prize is for Alyssa Thornton from Georgetown University. Please. Some biogenic crystals. We are trying to cover all topics. From Ball Python. Very nice work. Here we are. That side for pictures. These days, if you don't take a picture, it doesn't even, not even happen, right? Whatever we are doing. So, last, from the Royal Society of Chemistry, Yuki Agiwara. I'm sorry about the pronunciation. For his photoisomerization and photothermal effect studies from Japan. And now we move to 4 other prizes, this time from IUCR. They are offering a 50% discount on the fees for open access, so please publish as soon as possible there in their journals. So we start with Veronica Kras from Manchester, please. Beautiful studies on polymorphism. And then we move with Kristin Krukel-Berzina, if he's here, yes, from Latvian Institute of Organic Synthesis, for her studies on cyclodextrin metal organic frameworks. Again, I'm sorry for my pronunciation. Then we are going to the Eastern Europe, Tomislav Stolar, for his work on mechanochemical synthesis of hydrogen bonding networks and frameworks. And the Waseda University is on fire. We have also Shodaya Zebe for his works on polymorph-induced diversification and crystal actuation based on photoisomerization and photothermal effects. Oh, wow. If it's positive, I don't know if we can give the prize in general. No, okay. You want to take the prize for him? Yeah? Okay, so we will wait for him. We will wait for him, yes. Okay, I'll put it here. And last but not least, it's the second edition of the Joel Bernstein Memorial Poster Award. It's an important prize for all of us because Joel Bernstein, of course, was a central member of our community. So the winner will get a $500 check. So this is the real deal. And I'm pleased to announce that this year's winner, after Durga Prasakarotu actually, so you have to keep up the legacy, is Alan Eaby for his work on water absorption. Congratulations. The fake check, here we are. And that's it. Oh, we have the winner, yes. Come on, round of applause for Shodaya Azebe. And that's it. Thank you all. And now for the closing remarks.
And now the important question, where do we go next? So I'll give you a spoiler alert here. We are going to Mexico, and I would like to invite Miguel to tell us something about the new ICOS site.
Well, I'm really here just to represent Braulio Rodriguez Molina, he's going to be the real host. But I will be happy to support him. I think Braulio's proposal is to host ICOS in the Riviera Maya. So that means it would be somewhere, it could be in Cancun or close to Cancun. They're really all across the coast. There's many places that one can go. Large hotels, small boutique hotels. And it's an area that is very easily accessible. There are many flights from many parts in the United States. There are some European connections like London, Madrid, I think Manchester. And so it is an easy place to get to. And it is quite a beautiful place. It is, crystalline waters, blue waters, as you can see. Bring your, if we'll make it happen, which I hope we will, bring your snorkeling and diving gear. There's just amazing snorkeling and diving over there. There's a coral reef to go to. The zone is extremely rich from a cultural perspective, as there's a wealth of Mayan influence in the area, which starts with a number of buildings and cities. So one of the most interesting all Mayan cities is Chichen Itza, which is within 2 hours drive from Cancun, maybe 3 hours drive. So everything is really accessible. And the food, you get to really try, the food that evolved from the Mayan and Spanish influence in the area. So it should be a really sensational place to continue the conversation for all of us at ICOS. And so I think the plan would be that we will skip the IUCR meeting. So we will probably plan for being in Cancun in 3 years rather than in 2 years, so that we can get into a proper cycle. So I figure that in 3 years now, we will have to hold Braulio to make a sensational meeting to organize something truly spectacular for all of us. So hope to see you all there.
that, I think we can conclude. Have a safe trip home and enjoy your dinner. Thank you so much.